Hello everybody, welcome to our course on advanced algorithms and complexity. As the first unit in this course, we're going to talk about network flow algorithms, and in particular in this very first lecture, we're just going to give an example of a problem to sort of give you a feel for what types of things we're going to be talking about in this unit. So, to set things up, suppose that you're a disaster relief manager, and you're trying to, among other things, you have this city and you want to know how quickly could it be evacuated in the case of an emergency. Well, to do this, you have to sort of look at the roads leading out of the city, and so you see that there's the main highway out that will handle 5,000 cars an hour. Of course, this isn't the only road leading out of the city. There are some secondary highways that can each handle 2,000 cars an hour. Of course, things are a little bit more complicated than that. These other roads, they each bifurcate into two halves. Each of these halves can handle 1,000 cars an hour, so you're maybe okay so far. But it turns out that two of those halves merge together a little ways down into just a single road that can only handle 1,000 cars an hour. And so you can imagine that in real life there are many more roads than this in your full road network, but this is sort of a toy example. And we'd like to know, given that this is the network, how quickly can we evacuate? Well, it's not hard to start playing around with this. We can take 5,000 cars an hour and send them out along the main road. We can send another 1,000 cars an hour along this sort of northern path here. Another 1,000 cars an hour can go along sort of up on the northern road and then split off and join in on the merged road. And finally, another 1,000 cars an hour can go off on the third highway. Now, putting this all together, we have a total of 8,000 cars an hour that we can evacuate. But we'd like to know, is this the best that we can do, or can you do better? Well, if you play around with this a little bit, there's no sort of obvious way to make an improvement, and you might suspect that this is the best you can do. And in fact, you'd be correct. One way to show this is that if you draw a river, suppose that there was a river where this blue line is on the diagram, you'll note that there are only 4 bridges that cross that river. And the total capacity of all the bridges is only 8,000 cars an hour. So if only 8,000 cars an hour can cross this river, and you need to cross the river to get out of the city, only 8,000 cars an hour can evacuate the city. And that proves that this plan that we have for evacuation is really the best you can do. It's bottlenecked at the river. You can't do any faster. So network flow problems are problems that will allow us to study things like this problem. And this is what we're going to be talking about in this unit. And next lecture, what we're going to do is we're going to take a little bit of a more careful look at this problem. We're going to come up with sort of a formal framework to discuss this kind of issue. And then we're going to discuss some examples of where these sorts of problems might show up in real life. So that's what you have to look forward to in the next lecture. I hope to see you then. Hello everybody, welcome back to our network flows unit. Today we're going to be talking a little bit about sort of formal definitions and sort of getting a concrete definition of our problem, and then some examples of sort of what sorts of problems fall into this category. So remember, last time we discussed the disaster management problem. Today what we're going to do is we're going to have a sort of formal framework for talking about this problem and some similar problems. So to begin with, we're going to want to define what a network is. A network should be thought about like this network of roads that we saw in this previous example. So a network is a directed graph G representing all the roads, but with some additional information. Each edge E is assigned a positive real number called its capacity. This is how much traffic can be handled by that road. Additionally, one or more vertex is labeled as a source. This is the city. This is the place where the traffic is coming from. And then one or more vertex is labeled a sink, which is sort of the edges of the graph where everything's going to. So flow goes from sources to sinks along these edges that each have a capacity. So, with the example from last time, we have this network of roads. We can turn it into a graph where the city is a node, each of the intersections gives us another vertex, and then we have some extra vertices sort of at the ends where the cars escape to. The city itself is the source of our flow. The 4 exits give us sinks, labeled T here. And each of the edges has a capacity which says how many cars an hour can drive along that road. Fair enough. The next thing that we want to be able to discuss are flows. We want to be able to talk about flows of traffic through this network and talk about what's a valid flow and what isn't. And before we get into any more detail on that, in the last example, we actually talked about sort of exactly which routes different cars take. 1,000 cars traveled this route, another 1,000 traveled this route, and so on and so forth. But this is a little bit more complicated than we want to do. Rather than talking about where each individual car goes, we're instead just going to concern ourselves with the total number of cars, the total amount of flow along each edge. So, in particular, we're just going to figure out how much flow goes along each edge, but this, of course, needs to satisfy a couple of conditions. It can't just be any number we like. The first of these is rate limitation. For any edge E, for one thing, the flow along that edge needs to be non-negative. You can't send a negative number of cars along this road. And secondly, the flow needs to be at most the capacity of the edge. You can't run more cars along the road than the total capacity that the road fits. The second thing is a little bit more subtle. It's conservation of flow. The idea here is that if a car drives into an intersection, it then eventually needs to drive out of the intersection. And what this says is that at any vertex, except for sources where flow gets created and sinks where flow gets destroyed, it needs to be the case that the total flow of cars into that vertex is the same as the total flow coming out of that vertex. So for every vertex, the sum over all edges pointing into the vertex of the flow is the same as the sum over all edges going out of that vertex of the flow along that edge. And so, putting this together, formally we define a flow on a network is just an assignment of a real number, f sub e, to each edge e, such that these two conditions hold. For each edge e, the flow on that edge is between 0 and the capacity of the edge. And for all vertices v except for sources and sinks, the total flow into that vertex is the same as the total flow out of that vertex. So that's what a flow is. So, for example, in our example from last time, we have all of these cars traveling in various directions. And on each road, we can compute the total amount of flow, the total number of cars flowing along that road. So there are 5,000 along the main highway. The northern highway going up has 2,000 cars an hour, half of them going one way, half of them splitting off the other way. And for each road, you just label how many cars an hour are traveling along that road. And if you look at this for a while, you can actually determine that yes, these satisfy the properties that we want. No road has more flow than its capacity, and flow is conserved at each of these three vertices that aren't sources or sinks. So, to make sure that we're all on the same page here, we have a network listed up above, and then three possible assignments of flow. Which of these three are valid flows for the given network? Well, you look at these for a while, you compare it to the definitions, and you'll find out that C is the only valid flow. A has the problem that it doesn't conserve flow at the denoted vertex. It has 6 units of flow going into that vertex, but 7 units of flow coming out. B conserves flow everywhere, but the edge that's highlighted has 6 units of flow, whereas the capacity is 5. On the other hand, if you look at diagram C, everything works out. Flow is conserved, nothing goes above capacity. It's all great. Okay, so this is what a network flow is, but network flows are actually very useful to study because they actually model a large number of real-life phenomena. We've already talked about flows of goods or people along a transportation network, which fit very cleanly into this model. But you can also look at flows of electricity along a power grid, or flows of water through pipes, or even flows of information through a communications network. All of these are going to be examples of network flows in which this sort of formalism that we've developed will be useful for analyzing problems. Now, what types of problems are we going to be studying? Well, the big one that you want to know is the size of a flow. You want to really know how much stuff is actually flowing. How many cars are actually evacuating the city? How many can we get to evacuate the city? And for this, we need to define the size of a flow. And it turns out this can be computed by looking only at the sources. And the idea is that any flow, it gets created at the source, they sort of drive until they hit the sink, and then they go away. But if we can just measure how much flow is coming out of the sources, that will tell us how much there is in total. So, given a flow f, we define its size to be the sum of all edges that leave a source of the flow coming out of that source, minus the sum over all edges going into a source of the total flow through those edges. And so it's the total flow going out of sources minus the total flow going into sources. That's the size of the flow. Now, it turns out you can equally well compute this by looking only at sinks. The lemma says the size of the flow is equal to the sum of flow going into a sink minus the sum of flow going out of a sink. And the argument here is pretty nice, and we'll be seeing similar things a lot. So the thing to note is that if you take the sum over all vertices of the total flow going into that vertex minus the total flow going out of that vertex, that's actually 0. Because each edge, some flow leaves a vertex, but then goes into another vertex. And so the two terms cancel out. On the other hand, if we take vertices that aren't sources or sinks, by conservation of flow, that inner term is 0. So this is the same as the sum only over sources and sinks of the total flow into that vertex minus the total flow out of that vertex. Now, if we look at the sum only over sources of the flow into the vertex minus the flow out of the vertex, that's minus the size of the flow. And the other term is just the flow into sinks minus the flow out of sinks. And since this sum is 0, the total flow into a sink minus the total flow out of a sink is the same as the size of the flow, which is what we were trying to prove. Okay, so that's what the size of a flow is. The big problem that we're going to be trying to solve, and we'll really be discussing how do you solve this problem for the next several lectures, is how much flow can you fit through a network. Formally, this is called the max flow problem. The input should be a network G, so a graph with these capacities and some designated sources and sinks. And the output should be a flow F for this graph G, such that the size of the flow F is as large as possible. And this is the problem that we're going to be spending the next several lectures on. So come back next lecture and we'll start talking about some of the tools that will be useful in designing these algorithms. So I'll see you then. Hello everybody, welcome back to our network flows unit. Today we're going to be talking about some tools that are actually very useful. A tool called the residual network for coming up with new flows or adding a little bit of flow to an existing flow. And so remember, last time we sort of formally defined these things. We defined what a network was and defined what a flow on this network was, and then defined the max flow problem, which is the one we're working towards solving. And there's a very basic technique for solving max flow that is basically what we're going to be sort of working towards for the next bunch of lectures. And the idea is to build up your flow a little bit at a time. And this is really sort of what we did in our original example in the first lecture, where we sort of routed a bunch of cars along one road and then routed some more cars along another road and so on and so forth, and built up the final flow as sort of the sum of a bunch of little flows. So how do we do this in practice? Well, suppose that we have the following network. Here, all the edges have capacity 1 for simplicity. And what we can do is we can just add flows together a little bit at a time. We can note, hey, we can send a unit of flow along this top path, and if we just have a unit of flow along each of these edges, everything balances. But after we do that, we can send another unit of flow along the bottom path, and then another unit of flow along the middle. And once we've done this, we now have a maximum flow, but we built it up in sort of nice, convenient little pieces. Okay, so let's consider another example. This one's actually a little bit simpler. We have our network here. The maximum flow is 2, as we've shown here. But we're going to try and add flow incrementally. So let's start by adding flow along this path. It's a perfectly valid path. We can route a unit of flow through it. And now we want to try and add our second unit of flow. And there's a bit of a problem. We can't readily add a second unit. If we've already used up these edges, the remaining edges just don't connect to each other. We can't actually get the flow to work. Now, it turns out there's a way around this, which of course there is, since the maximum flow is 2. And it involves sort of routing flow along this blue path, which is a little bit weird, since we can't actually do that. We can't actually send flow down along the middle edge, since there wasn't an edge there. But if you think about it in the right way, you can think of sending flow down this middle edge as canceling out the flow that we'd currently sent in the up direction. If the flow going up and the flow going down are thought to cancel each other, then once we add these two flows together, we just get this flow, which is perfectly valid because there's no flow running along the middle edge. And so, sort of the moral of this story is that if you want to be able to appropriately add your little bit of flow, sometimes it's not enough to just add flow along new edges, but sometimes you also have to let your flow cancel flow along existing edges. So, given a network G and a flow F, what we're going to do is construct what's called the residual network, G sub F. And this is a new network that sort of represents the places where flow can be added to F. But this includes not just edges where there's sort of more room for extra flow to go along that edge, but also places where we could cancel out existing flows. So, to define this formally for each edge E of our graph, our residual graph, our residual network, is going to have edges. Well, it's going to have an edge along E, and the capacity is going to be the capacity of the edge, the original capacity of the edge, minus the flow along that edge. And the point is, this is the amount of remaining capacity that we have. Of course, if the flow is equal to the capacity, we can sort of ignore this edge because it would have no capacity. We also need to have an edge opposite E with capacity equal to the flow along E, because this will represent the amount of flow that we can cancel going in the other direction. So, for example, up top we have the following we have a network and it has a flow assigned to it. There are various units of flow assigned to various edges. Down below will give us the residual network. So if you look at the edge on the left, for example, well, we used up all 5 units of its flow. So what does this mean? Well, we've got no edge left pointing down because there's no extra flow that we can push in that direction. However, we do have a new edge pointing up with 5 units of flow, saying there are 5 units of flow going the other way that we might cancel out later. If you look at the top edge, we used 5 out of 7 total units of flow. So there are 2 units of flow left. So there's this one edge up top with 2 units of flow. And then there's this additional edge going the opposite direction, representing the 5 units of flow that can still be canceled. And so we do that also for all of the other edges of the graph, and this gives us the residual network. So if we look at what this does to our previous example, we have this graph, we route flow like this. Now, we can't add to it directly, but if you look at the residual network, we're actually going to have an edge going back in the opposite direction from each of these. And in this residual graph, there is actually a path that supports a unit of flow. It involves this middle edge, which says that we're canceling out flow along the middle. Okay, so given a network G and a flow F, any flow G on the residual graph, it turns out, can be added to F to get a new flow on the original graph. So the point is that if you have flow along the edge in the same direction that you had in the original graph, that's saying you should add that much flow along that edge. However, if you've got flow sort of in one of these opposite direction pointing edges, that's saying that that much stuff should be canceled from the flow that you had before along that edge. So just to make it clear, let's look at this problem. So we have a network with a flow on it F in sort of this upper left corner. Down below it, we show what the residual network is corresponding to that flow. Now in the upper right, we have a flow little g for the residual network. And the question is, if we want to compute the sum of the flows, F plus g, what is the flow of F plus g along this highlighted edge from source to sink? Well, what do we get? The original flow along that edge was 2. We need to add the flow of g along that same edge, so that's 4 extra units of flow. And we need to subtract off the flow in sort of the canceling direction. So that's plus 4 minus 2. That's a total of 4 units of flow from S to T in the residual. And you can compute the other edges, and yes, F plus G does give you a valid flow for the original network. In fact, the theorem is as follows. If you have a graph G and a flow F, and then have any flow you like, G, on the residual network, a few things happen. Firstly, F plus G is always a flow on the original network, which is nice. If you want to look at the size of the flow, the size of F plus G is just the size of F plus the size of G. And finally, and importantly, any flow on the original network you can always get by finding some appropriate residual flow and adding it to F. Now, the proof of this is actually not that hard. If you want to look at conservation of flow of F and conservation of flow of G, if you combine them, imply that you have conservation of flow on F plus G. Next, if you want to look at the total flow F plus G sends through any edge, well, the flow it sends through edge E is equal to, at most, the flow of F along that edge plus the flow of G along that edge, which is at most the flow of F plus the capacity of that edge in the residual. But that capacity is just the original capacity minus the flow that you sent from F, and so that's just the capacity of our original network. On the other hand, you can't end up with negative flow along an edge because G isn't allowed to cancel more flow along that edge than you had originally. And so putting these together, F plus G has to be a flow. Next, if you look at the flow of F plus G out of a source, this can be shown to be the flow of F out of that source plus the flow of G out of that source. So combining this, the sum of the size of the sum of the flows is the sum of the sizes. And finally, if you're given any flow H for our original network, it's not hard to construct a G that's somehow H minus F that's a flow on the residual graph. And so you can then write H as F plus G for some appropriate flow on the residual graph. So in summary, flows on the residual network sort of exactly correspond to ways to add flow to our original F. And this is very useful because our big picture idea for our algorithm is going to be start with some flow and then add little bits of flow. And the residual graph will tell us exactly how we can add little bits of flow. So that's all that we have for this lecture. Come back next time and we'll talk a little bit about how to show that we actually have the best flow when we do. Hello everybody, welcome back to our unit on flows and networks. Today we're going to be talking a little bit about sort of how to bound the size of our flows. And in particular, we've got this problem. In order to find max flows, we're going to need a way to verify that the flows that we have are actually optimal. So in particular, what we're going to do is we're going to need techniques for bounding the size of a maximum flow. And it turns out we actually had a way to do this. So in our original example, we said we had the city we're trying to evacuate, and if we have a river at a particular location, if you just look at the total amount of capacity of all the roads that cross the river, this gave us an upper bound on the rate at which we could evacuate the city, because everyone evacuating the city needs to cross the river at some point. And this is going to be our basic idea for bounding max flows. The idea is we want to find a bottleneck in the flow. We want to sort of find some region where in order to cross from one side of this bottleneck to the other, there's not a lot of capacity. And the total capacity across this bottleneck will give us a bound on the flow. So to make this a little bit more rigorous, we're going to define a cut. So given the network G, a cut, this is going to be a set of vertices of G. And you should think of these as sort of the set of vertices on the sort of the source side of the river, on the same side of the river as the city. So this is a set of vertices such that C contains all of the sources of our graph and none of the sinks. Now the size of the cut is given by the total capacity of all edges that leave the cut, go from inside the cut to outside the cut. It's just the sum of all that capacity. And so, for example, in this network that we had corresponding to our city evacuation problem, we can define a cut that contains these four vertices. And the size of the cut, well, is the sum of the capacities of these four roads, which ends up being 8,000. Okay, so to make sure we're all on the same page, here's a pretty simple network. There's a cut, which is this blue square that contains four vertices on the inside. What's the size of this cut? Well, you just have to look at which edges cross from inside the cut to outside the cut. These have capacities 1 and 2 and 3, and so you add those up and you get 6 as the answer. Okay, so the important thing though is that your cuts provide upper bounds on the size of the flow in the network. In particular, for any flow F and any cut C, the size of F is at most the size of C. And this was sort of exactly the argument that we had. Any piece of flow needs to cross the cut. There's only so much capacity that lets you cross the cut, and so that's an upper bound on the flow. Now, to make this rigorous, let's give a proof. The flow is the sum over sources of the total flow out of that vertex minus the total flow into that vertex. Now, for vertices that aren't a source or sink, this term is 0. So we can extend this to a sum over all vertices inside our cut of the flow out of that vertex minus the flow into that vertex. On the other hand, you'll note that, if you have an edge that stays within the cut, it comes out of one vertex and into another and cancels out of this sum. So this is the same as the sum over edges that leave the cut of the flow through that edge, minus the sum over edges that go into the cut of the flow through that edge. Now, of course, the flow of edges leaving the cut, that's at most the capacity of the edge. The flow of edges into the cut is at least 0. And so this thing is at most the sum over edges that leave the cut of the capacity of that edge, which is exactly the size of the cut. So this proves the theorem. And what this says is that if you have any cut C, that gives you an upper bound on the maximum flow. The size of the maximum flow is at most the size of the cut. Now, it's good we've got some upper bounds, but the question is this good enough? There are lots of ways to prove upper bounds. What we really want is a sharp upper bound, one that's good enough that once we've found a maximum flow, we'll have a matching upper bound that will tell us that you actually can't do any better than this. And somewhat surprisingly, bounds of this form are actually good enough. So the big theorem here is known as the max flow min cut theorem. For any network G, the maximum over flows of the size of the flow is equal to the minimum over cuts of the size of the cut. In other words, there's always going to be a cut that's small enough to give the correct upper bound on maximum flows. So to prove this theorem, let's start with a very special case. What happens when the maximum flow is equal to 0? If this is the case, it has to be the case that there's no path from source to sink. If there were any path from a source to a sink, then you could ride a little bit of flow along that path, and your max flow would be positive. So what we're going to do is we're going to let C be the set of vertices that are reachable from sources. And it turns out there can't be any edges out of C at all, because if there was an edge that left C, then that would, wherever you ended up, that would also be reachable from the source, and it should be in C as well. Now, since there are no edges leaving C, the size of the cut has to be 0. Now, in the general case, we can do something similar. We're going to let F now be a maximum flow for G, and then we're going to look at the residual graph. Now, if the residual graph, which is a way to talk about ways of adding flow to F, if that had any flow that you could put in it, F couldn't be a max flow. So the residual graph has max flow 0. And what that means is that there's a cut C with size 0 in this residual graph. And I claim that this cut C has size exactly equal to the size of our flow F. And the proof isn't hard. The size of F for any cut is actually the total flow out of that cut minus the total flow into that cut. But if C has size 0 in the residual graph, that means that all the edges leaving the cut need to have been completely saturated. They need to have used the full capacity. And the edges coming into C had to have no flow, because otherwise the residual graph would have an edge pointing in the opposite direction. And so the size is just the total sum over edges leaving C of their capacity minus the sum over edges into C of 0, which is just the size of the cut. And so what we found is we found a flow F and a cut C where the size of the flow is equal to the size of the cut. Now, by the previous lemma, you can't have any flows bigger than that cut or any cuts smaller than that flow. And so this is the maximum flow, and it's equal to the minimum cut size. So in summary, you can always check whether or not a flow is maximal by seeing if there's a matching cut. In particular, F is going to be a max flow if and only if there's no source to sink path in the residual graph. And this is a key criteria that we'll be using in our algorithm that we'll be discussing next time. So I hope to see you for the next lecture. Hello everybody, welcome back to our Flows in Networks unit. Today we're actually going to finally give an algorithm to compute maximum flows. So the idea of this algorithm is very much along the lines that we've sort of been hinting at the entire time. We're going to start with zero flow in our network, sort of the trivial flow, no flow along any edge. And we're going to repeatedly add a tiny bit of flow, sort of building up the flow a little bit at a time, until we reach a state where it's impossible to add any more flow, and then we'll be done. So how do we add flow? You have some flow F. We then compute the residual network, GF, and this really does represent the ways in which flow can be added. So any new flow that we would have would be of the form F plus G, where G is a flow in our residual network. So if we want to replace F by a slightly larger flow, all we need is a slightly positive flow in the residual network. And to do that, all we want to do is see if there's a source to sink path in this network. So what happens if there's no path? If there's no source to sink path in our residual network, then the set of vertices that we can reach from the source defines a cut of size 0. That says there's no flow in the residual of positive size, and so any flow F plus G has size at most the size of F, and F is a maximum flow. And so if that's the case, we're done. We already have a maximum flow and we can just stop. Now if there is a path, it turns out we can always add flow along that path. What you do is if you add x units of flow to each edge along that path, well, you have conservation of flow. There's x units in and x units out of each vertex on that path. And as long as x is at most the minimum capacity of any of these edges in the residual graph, this is actually a flow in the residual network. So if we do this, we find some flow G for our residual network where the size of G is bigger than 0. Then when we replace F by F plus G, we found a new flow where the size of F plus G is strictly bigger than the size of F. We found a flow that's slightly bigger than the one we had before. So to make this formal, we've produced what's known as the Ford-Fulkerson algorithm for max flow. You start by letting F be the trivial flow, and then you repeat the following. You compute the residual graph for F. You then try and find an S to T path, P, in this residual graph. If there is no such path, we know that we already have a max flow, so we can just return F. Otherwise, what we're going to do is we're going to let X be the minimum capacity of any edge along this path in the residual network. We're going to let G be a flow where G assigns X units of flow to each edge along this path. And then we're going to let F be F plus G. And when we do this, we increased our flow by a little bit, and we just keep repeating until we can't increase our flow anymore. So, for example, we've got the network here. Here's our residual network. How much flow do we end up adding in one step? Well, to figure this out, you have to do two things. You first have to find your S to T path, which is this one. And then you say, well, how much capacity are there on the edges? Which edge has minimum capacity? And that's this edge of capacity 4. And so in this case, you'd route 4 units of flow on your first step. But to really see how this algorithm works, let's take the following example. So we have a graph up top. Initially, we have no flow running through that graph. So the graph below is the residual, is the same network that we started with. And now what we want to do is we want to find paths in the residual network. So here's an S to T path. The minimum capacity along this path is 5. So we route 5 units of flow along each of these edges. Now, this updates the residual. We have we've got a new edge. We've got an edge that wasn't there before. Whatever. We now want to, again, find an S to T path in the residual graph. This one works out pretty well. Again, The minimum capacity of these edges is 5, so we route 5 more units of flow along each of those edges, and we update the residual graph again. Once again, we find an S to T path in the residual graph. This one works pretty well. The minimum capacity here on these edges is 2, so we route 2 more units of flow along each of those edges. And at this point, once we've updated the residual, you'll note there's no S to T path. In fact, there's a cut right here that prevents us from routing any more flow. And so, given that cut, you can actually see that this flow, which routes 12 total units of flow, is actually a maximum flow, and so we're done. So, before we get into analyzing the runtime of this algorithm, there's an important point to make. We should note that if all the capacities that we have are integers in our original network, then all the flows that we produce are also integer, because every time we try and augment our flow along some path, we look at the smallest capacity, which is always an integer, and so we put an integer amount of flow everywhere, and everything remains integer if we started with integers. And there's an interesting lemma that we get out of this, which actually will prove useful to us later, that says if you have a network G with integer capacities, there's always a maximum flow with integer flow rates. And you can get it just by using the Ford-Fulkerson algorithm. Okay, but now let's look at the analysis. And for this analysis to work, I'm going to have to assume that all capacities are integers. Now, what does this algorithm do? Every time through this loop, we compute the residual graph, and then we try and find a path P in it. And each of these run an O of number of edges time. Now, every time we do that, we increase the total flow by a little bit, in fact, by at least 1. So the number of times we do it is at most the total flow on our graph. So our total runtime is bounded by the number of edges in our graph times the size of the maximum flow. Now, this is a little bit weird as a runtime because it depends not just on sort of the structure of the graph that we're working on, but also the capacities of the edges and the size of the maximum flow. This leads us to a problem where, potentially at least, if we have numerically very, very large capacities in our graph, it could actually take us a very, very long time to compute the flow. One other thing I should note about this algorithm is that it's not quite a full algorithm. What it says is at every step I need to find some source to sink path in our residual. Now, there might be many valid paths to choose from, and the Ford-Fulkerson algorithm, as I've stated it, doesn't really tell you which one to use. Now, you might just want to run depth first search because it's very fast, but maybe that's not the best way to do it. And as we'll see a little bit later, in fact, finding the right way to pick these augmenting paths can actually have a substantial impact on the runtime of the algorithm. But that's for a little bit later. That's all for our lecture today. Next time we'll talk a little bit more about the runtime of this particular algorithm. So I hope to see you then. Hello everybody, welcome back to our network flows unit. Today we're going to be talking about sort of an example of an algorithm of a network on which the Ford-Fulkerson algorithm might not be very efficient. So last time we had this great algorithm for max flow called the Ford-Fulkerson algorithm. The runtime was O of the number of edges of the graph times the size of the maximum flow. Now, this is potentially very bad if the size of the flow is large. On the other hand, this is sort of a theoretical problem at this point. We don't know for sure whether or not this is ever actually a problem. So today we're going to consider the following example. Here's a graph. Some of the capacities are pretty large. A bunch of them have 1 million capacity. And then there's one edge with only capacity 1. So the max flow here is big. We can route 1 million units of flow over the top and another 1 million over the bottom. So the max flow for this graph is 2 million. Fine. Let's look at possible executions of the Ford-Fulkerson algorithm on this graph. In particular, one in particular. So we start with no flow. We have a residual graph. Let's look for a source to sink path. Here's one. What's the minimum capacity on this path? Well, it's 1 coming from that middle edge. So we're going to route 1 unit of flow along that path. Update the residual, find a source to sink path. Here's one. 1 unit of capacity along the middle edge, so we route 1 more unit of flow along this path. Update the residual, find a path, 1 more unit of flow, residual, 1 more unit of flow, and we can keep going like this for a while. So the question here is, if we keep iterating the Ford-Fulkerson algorithm like this, how many iterations will it actually take to compute a maximum flow, if assuming that it keeps finding augmenting paths according to this pattern? Well, quite a lot, actually. Each step here adds only 1 unit of flow because we keep being limited by this middle edge. In order to find a max flow, we need a total of 2 million total units. So the Ford-Fulkerson algorithm requires something like 2 million iterations before it converges on this graph. And that's a really big number for a graph with only 4 vertices. On the other hand, if you think about it, it doesn't need to be this bad. I mean, here's another perfectly valid execution of the Ford-Fulkerson algorithm on this graph. We've got no flow. Let's find a path in the residual. There's this one. We can route 1 million units of flow along that path. Update the residual. Here's another path. Put 1 million units of flow along that path. And suddenly we've got a cut. We're done. And so there's a big difference between these two different executions of more or less the same algorithm. And what would be really nice is if we had a way to ensure that we always had something that looked more like the latter execution than like the former execution. And next time we're going to be talking about sort of a way to go about this, a sort of principled way of choosing our paths to guarantee that we don't have the type of problem presented by the first of these examples. So that's what we'll be discussing next time. I hope to see you then. Hello everybody, welcome back to our network flows unit. Today we're going to be talking about a new algorithm for network flows, or maybe just a version of the old algorithm that will do a little bit better than what we had previously. So last time we were still talking about the Ford-Fulkerson algorithm for max flow. The runtime in general is O of the number of edges times the size of the flow. And last time we showed that this can actually be very, very slow on graphs with large capacities. And in particular, we had this example, where sort of every time if you routed flow, at least if you were picking the wrong paths, then you just got 1 unit of flow every iteration, and it took millions of iterations to actually finish. Fortunately, though, we know that the Ford-Fulkerson algorithm gives us a choice as to which augmenting path to use. And the hope is that maybe by picking the right path, we can guarantee that our algorithms won't take that long. And so in particular, what we want to do is we want to find sort of a principled way of picking these augmenting paths in order to ensure that our algorithm doesn't run through too many iterations. And one way to do this is via what's known as the Edmonds-Karp algorithm. The idea of the Edmonds-Karp algorithm is as follows. We'd like to use the Ford-Fulkerson algorithm, but we're always going to be using the shortest possible augmenting path. That is, shortest in terms of the number of edges that are being used. And basically all that this means is that if we want to find our augmenting paths, we want to use a breadth-first search rather than a depth-first search. So, for example, if we're trying to run Edmonds-Karp on this example, then we can't use the zigzag path with 3 edges. We're required to pick this augmenting path with only 2 edges instead. After we've done that, there's another path with only 2 edges, and after we've done that, there's nothing left to be done. So at least on this example, the Edmonds-Karp algorithm gives us the good execution rather than the bad one. Now, to really look into how well this works, we need to analyze these augmenting paths. So you have an S to T path. You'll note that when you add your augmenting flow, it always saturates some edge. That is, uses up all of the available flow from that edge. And this is because the way we decided the amount of flow to run along this path was we took the minimum capacity of any of these edges in the residual graph. And so whichever edge had only that much capacity left got saturated. Now, once we add this augmenting flow, we have to modify the residual network. We end up with edges pointing backwards along each of these places because we can now cancel out that flow we just added. And at least the one edge that we ended up saturating, we destroyed that edge because we used up all of the remaining flow. Okay, so we'd like to now analyze the Edmonds-Karp algorithm. And the basic idea is that whenever we have an augmenting path, we always saturate some edge. And we're going to show that we don't have too many different augmenting paths by showing that no edge is saturated too many times. Now, we'll note that this really fails to hold in the bad case that we looked at, because the middle edge kept on being saturated over and over again. It just flipped from pointing up to pointing down in the residual graph over and over again. And this was the real thing that was limiting us to adding 1 unit of flow per iteration. Okay, so that's the idea of our analysis. And the way we're going to show that this works is we're going to start with a critical lemma. The Edmonds-Karp algorithm is very concerned about distances in the residual graph because it looks for short paths there. And so, we'd like to know how these distances change as the algorithm executes. Because as you run your algorithm, your residual graph keeps changing, and so the distances inside the residual graph change. Now, the lemma that we want is the following. As the Edmonds-Karp algorithm executes, if you take any vertex v and look at the distances from the source to v, those distances only get bigger. Similarly, if you look at the distances from v to t, or the distance from s to t, again, those can only increase, never decrease. And the proof is not so bad, but it's a little subtle. So, whenever we have an augmenting path, we introduce a bunch of new edges that point backwards along this augmenting path. Now, the augmenting path, sort of by assumption, was always a shortest path from source to sink. And what that means is that the new edges point from vertices that were further away from S to vertices that are closer to S. And the key observation is that new vertices of that form never give you any faster paths from source to V. And this is because, well, I mean, if I told you someone introduced a great fast one-way highway that went from a city 1,000 miles away from your house to a city 10 miles away from your house, it would not actually be useful for you to get anywhere from home. Now, it would be incredibly useful getting back from this other place, but if you wanted to get to this place 10 miles away, you could just drive 10 miles instead of driving 1,000 miles and taking the new highway. Similarly, these edges that only point from distances farther from S to vertices closer to S, they never help you get 2 places from S any faster than you were before. Now, the saturated edges that got removed might make things become slightly further away than they were before, but the new edges never make anything closer. And that basically completes our proof. The fact that distances at vertices 2t is increased is completely analogous, as is the proof that vertices from S to t increases. So, with that under our belts, the critical lemma now is the following. We want to show that there's a limit on how often edges can be resaturated. And so we have the following lemma. When running the Edmonds-Karp algorithm, if an edge E is saturated, that edge cannot be used again in any augmenting path, at least until the distance between S and T in the residual graph has increased. Now, the proof of this is a little bit subtle. So we're going to first consider this path that caused us to saturate the edge. So the path went from S to U, this had length x, then from U to V, which was our edge, and then from V to T, which had length y. Now this had to be a shortest path, and so the path from S to T had to be x plus y plus 1. Now, when we use that edge again, we use this edge from V back to U, well, we need to have some path from S going to V, then to U, and then from U to T. Now, this has to be a shortest path. Now, what's the distance from S to V? The distance from S to V is at least what the distance from S to V was before, which was x plus 1. Then the distance from V to U is 1, and the distance from U to T is at least what it was before, which is at least y plus 1. So that means when this edge gets used again, the distance from S to T had to be at least x plus 1 plus y plus 1, y plus 1 plus 1, which is at least x plus y plus 3. Which means that when this edge gets used again, it has to be the case that the distance between S and T was bigger than what it was before. And that completes our proof. Once we have this lemma, the rest of this analysis is actually pretty easy. The distance between S and T in the residual graph can only increase, and it's never more than the number of vertices. So it can only increase number of vertices times. Now, between times that it increases, no edge can be saturated more than once, because once it's saturated, you can never use it again. And so between times, we can only have O of E many saturated edges. But each augmenting path has to saturate an edge. You can only have O of E many such paths between increases in this distance between S and T, and that can happen only O of V many times. So there are only O of size of V times size of E many augmenting paths used by this algorithm. Each path here takes only O of E much time, and so the total runtime is at most O of V times E squared. Now, this is maybe not so great, because O of V times E squared, this might be number of vertices to the fifth or number of edges cubed, but it is polynomial, and it has no dependence on, or it sort of doesn't become very, very, very big when our actual size of our flow becomes very, very large. Okay, so one problem to sort of quick review properties of this Edmonds-Karp algorithm. Which of the following are true about the Edmonds-Karp algorithm? 1, that no edge is saturated more than size of V many times. 2, the lengths of the augmenting paths decrease as the algorithm progresses. Or 3, that changing the capacities of edges will not affect the final runtime. Well, it turns out only one of these is true. Edges only become resaturated after the distance between S and T increases, which only happens V many times. However, the lengths of the augmenting paths increase as the algorithm progresses, not decrease. And finally, although the runtime does not have an explicit dependence on the edge capacities, like it did in the Ford-Fulkerson algorithm, they can still affect the runtime. If all the capacities are 0, you don't need to do any augmenting paths. If the capacities are weird, they might make you do a little bit more work than you'd have to do otherwise. But sort of the nice thing about Edmonds-Karp is that there's a bound to how bad it can be. So in summary, if we choose augmenting paths based on length, it removes this sort of at least bad dependence that we had on the numerical sizes of the capacities. We have a runtime that we can write down that we can bound independently of our total flow. And now, max flow is an incredibly well-studied algorithmic problem. There are actually better, more complicated algorithms that we're just not going to get into in this course. The state of the art is a little better than what we had. It's O of number of vertices times number of edges. And if you want to look it up, feel free to look up these more complicated algorithms. But this is all that we're going to do in this course. The next 2 lectures, we're going to sort of talk about some applications of these max flow algorithms to a couple other problems where it's not quite obvious that this is the right thing to do. So, I'll see you next time. Hello everybody, welcome back to our Flows and Networks unit. Today we're going to be talking an interesting problem on image segmentation. There's a problem in image processing, and we'll actually show that there's some surprising connections to this max flow, min-cut type of things that we've been talking about. So the problem we're trying to solve is image segmentation. Given an image, separate the foreground of the image from the background. And we don't want to get too much into image processing, so here's the basic setup. The image is a grid of pixels. We need to decide which pixels are in the foreground and which are in the background. And I don't know much about how you actually process images, but we're going to assume that there's some other program that gives you some sort of idea about which pixels are in the foreground and which are in the background. So, in particular, there's some other algorithm which looks at each pixel and makes a guess as to whether it's foreground or background. It assigns to this pixel 2 numbers, AV, which is sort of a likelihood that it's in the foreground, and a BV, which is the likelihood that it's in the background. So the simple version of this algorithm, the input are these values, A and B, and the output should be a partition of the pixels into foreground and background. So it's the sum over V in the foreground of A sub V plus the sum over v in the background of b sub v is as large as possible. So to be sure that we're on the same page, here's a really simple version. We've got 3 pixels and we've got some a and b values. What's the best possible value that we can get out of this problem? Well, it turns out that this problem is actually not that hard to solve in general. Basically, for any pixel, if you put it in the foreground, you get A points. If you put it in the background, you get B points. So if A is bigger than B, it goes in the foreground. And if B is bigger than A, it goes in the background. So what you do is, well, 1 should go in the background and gives us 4. 2 goes in the foreground and gives us 5. 3 goes in the foreground and gives us 6. And so the answer is 4 and 5 and 6 is 15. Very well. Now, this problem is maybe a little bit too easy, but let's take a little bit more information into account. We sort of expect that nearby pixels should be on the same side of the foreground-background divide. They're not going to be sort of randomly spattered throughout the picture. They tend to be more or less connected regions. So for each pair of pixels, v and w, we're going to introduce a penalty, pvw, for putting v in the foreground and putting w in the background. So the full problem is the following. As input, we take A, B, and P. Again, we want a partition of our pixels into foreground and background. And now we want to maximize the following. The sum of V in the foreground of AV, and the sum of V in the background of BV as before. But now we subtract the sum over all pairs where V is in the foreground and W is in the background of PVW. And now we want this thing to be as large as possible. Now, before we get into too much depth on this, I'm going to do a tiny bit of algebra. I'm going to subtract the sum over all vertices v, all pixels v, of AV plus BV. And the point is that this is a constant that doesn't depend on our foreground-background split, so this doesn't really affect our maximization problem. It just changes the numbers around a bit. We now want to maximize negative the sum over v in the foreground of BV, and then v in the background of AV, and then pairs v in the foreground, w in the background of PVW. Now, instead of maximizing a negative quantity, of course, we can try to minimize this positive quantity. Okay, that changed things around a bit. What do we do now? Well, the thing to note is that we want to split the vertices into 2 sets, and we pay a cost, and the cost is mostly based on sort of the boundary between these 2 sets. Sort of pairs where we break across the boundary, that's where we pay this big penalty. And this looks like kind of a familiar problem. This looks a lot like a minimum cut problem. So to make this all formal, let's try and build a network so that this is a minimum cut problem. The first thing we have to do is add 2 new vertices, a source and a sink. Now, we add edges from a source to a vertex v with capacity AV, and an edge from v to t with capacity BV. We also add an edge from v to w with capacity PVW, and this gives us a network. Now, if we have a cut in this network, the cut contains S and not T, and then some of the other pixels and not some of the others. Now, what's the size of this cut? Well, if V is inside our cut, there's an edge from V to T with capacity BV. If V is not in our cut, there's an edge from S to V with capacity AV. And then if V is in our cut but W isn't, there's an edge from V to W with capacity PVW. But if you stare at this for a bit, you'll note that if we just let the foreground be the things in the cut and the background be the things not in the cut, this is exactly the thing that we're trying to minimize. So the original problem of this image segmentation boils down exactly to solving this minimum cut problem. And now, maybe we don't know directly how to solve min cut, but we know that min cut is equal to max flow. And so we're just going to use our max flow algorithms. We're going to construct this network, compute the maximum flow, and then find the corresponding minimum cut. So the algorithm for image segmentation is really not that hard. You construct the corresponding network G. You then compute a max flow f for G using Edmonds, Karp, or whatever other algorithm you want. We need to find the corresponding flow, so we compute the residual network, and you let C be the collection of vertices reachable from the source in this residual network. Then the foreground should just be the set C, the background should be everything else. That is the optimal solution to our image segmentation problem. And so in summary, we started with this basic problem in image processing. We found a nice mathematical formulation, and then we noted that it looked a lot like minimum cut. And we're able to construct a network, use the relationship between max flow and min cut, and then use our existing maximum flow algorithms to just solve this problem. And so this is one final application of these flow algorithms that we've been discussing. That's really all that we have to say for the moment about these flows and network algorithms. Come back next time, we'll start another unit on linear programming problems, where we'll discuss some problems that are actually somewhat more general than the ones we've been discussing here that turn out to be very useful in practice. So, I hope to see you then. Hello everybody, welcome back to our network flows unit. Today we're going to talk about an application of some of these network flow algorithms we've been discussing to a problem called bipartite matching. So, to get started on this, suppose that you're trying to coordinate housing in a college dormitory. So, what you have is you've got n students and m rooms. Each student is giving you a list of rooms that they consider to be acceptable. And what you'd like to do is place as many students as possible in an acceptable room. Now, of course, there's a limitation here that you can't place more than one student in the same room. Okay, so this is the problem. How do we organize this data? Well, you've got a bunch of students and you've got a bunch of rooms, and there are some pairs of students and rooms where that student is willing to be in that room. And so a great way to organize this data pictorially is by what's known as a bipartite graph. A bipartite graph is just a graph G where the vertex set can be partitioned into two subsets, U and V, students and rooms. There's sort of two types of vertices, such that all edges in the graph are between a vertex of U and a vertex of V. So all the edges connect a student to a room, not a student to a student or a room to a room. And so if we just redraw that graph and call the two sides U and V instead of students and rooms, it's exactly a bipartite graph. So what we'd like to do on this graph is find what's called a matching. We want to find a bunch of pairs of students and rooms. That's a bunch of edges of the graph. But it needs to be the case that each student gets assigned only one room, and each room is assigned to only one student. And that says that no two of these edges that we pick can share an endpoint. So in our example, if you look at the blue edges here, that will give us a matching. We've got a bunch of pairings of students get paired to rooms that they were acceptable to be paired with. And each student is assigned only one room. Each room is assigned to at most one student. Fine. So the big problem we're going to be trying to solve is known as bipartite matching. Given a bipartite graph G, we'd like to find a matching of G that consists of as many edges as possible, and ideally one that pairs up all of the vertices with each other. So just to be sure that we're on the same page, if I give you the following bipartite graph, what's the size, the number of edges in the largest possible matching? Well, you have to play around with it for a bit. You can find that you can actually get matchings of size 3 here, and it takes a while, but you should be able to convince yourself that it's not actually possible to get a matching here of size 4. Fine. So, let's talk about applications. Bipartite matching actually has a bunch of applications. One thing maybe is matchmaking. Suppose you have a bunch of men and women, some pairs of them are attracted to each other, and you would like to sort of pair them off into as many possible couples as possible, such that, nobody's dating more than one person at the same time. Now, we have to be a little bit careful here. If there are gay people, then this doesn't quite fit into the context of bipartite matching, because if there are men attracted to men or women attracted to women, the graph is no longer bipartite. And, there's nothing wrong with this necessarily, but it will make the problem computationally more complicated. Another example that you might want to consider is maybe a scheduling problem. You have sort of a bunch of events that need to be scheduled at different times. Each event has some blocks of time that would work for it, and you need to make sure that no two events get the same time block. Once again, sort of a bipartite matching problem. So, how are we going to solve this problem? The key idea is that there's a connection between this problem and network flows. Sort of what you want to solve in bipartite matching is you want to connect nodes on the left to nodes on the right without putting too many connections through a given node. this sounds sort of like a flow problem, where you want to have flows running from left to right without too much flow running through any given node. So to make this work, you add source nodes and connect them to the left, and have the right nodes connect to a sink node and build up a network. So in particular, we start with our bipartite graph. You direct all of the edges left to right. We're going to add a source and a sink node. We're going to connect the source node to the vertices on the left and connect the vertices on the right to the sink. And we're going to define all the capacity edges of this graph to have capacity 1. This gives us a network associated to our bipartite graph. And it turns out that for every matching in our bipartite graph, there's a corresponding flow on the network. And so, to be formal about this, if G is the bipartite graph and G prime the corresponding network, there's actually a one-to-one correspondence between bipartite matchings on G and integer-valued flows on G prime. And just to prove this, well, if you have a matching, we can produce a flow by running flow through each edge of the matching. Then, to make everything balance out, each vertex of U, which we had flow running through it, we need to have flow coming to that vertex from S. And then that edge goes to some vertex in V, and that needs to extend through the edge to T. And that will give us a flow. Now, if we have a flow and want to go back to a matching, you just look at these middle edges between U and V and say which ones of them have flow, and those edges we use in the matching. Now, we can't have two edges coming out of the same vertex of U because there won't be enough flow going into that vertex. There's only one unit of flow going in at most, and so there can't be two units coming out. And we also can't have two edges sharing the same vertex on V for basically the same reason. And so there's a relationship between bipartite matching and integer-valued flows. However, you'll note that it was a lemma that we proved that you can always find an integer-valued maximum flow. And so our max flow algorithms sort of already work for solving this problem. So this gives us a very simple algorithm for solving bipartite matching. You construct the corresponding network, G prime. You compute a max flow for G prime in such a way that gives you an integer max flow. You then find the corresponding matching and return it. That solves the problem. Now, we could just say that we're done here, but there's something very interesting going on. So max flow min cut related the maximum flow to the minimum cut, which is sort of nice as a theoretical tool. But here, these bipartite graphs, the maximum matching relates to a max flow, and let's see what these cuts relate to. So if we have the network corresponding to a matching and look at a cut in this network, well, this cut contains the source, and it contains some set S of vertices on the left and some set Y of vertices on the right. And we'd like to make this cut as small as possible. Now, if we fix X, the vertices on the right, well, when do they contribute to the cut? Well, vertices in Y, they have edges to T, which produce one edge to the cut. But if you had an edge from X to a vertex not in Y, then that would also give you one edge that breaks the cut. And because of this, it actually can be shown that you can basically afford to just let your elements in V be your elements in Y be exactly the elements on the right-hand side that are connected to by some element of X. Now, if we do that, what edges break the cut? Well, you've got edges from S to elements of U that aren't in X. Now, by the way we constructed these, vertices in X only connect to vertices in Y that are also in the cut. But vertices in Y, they connect to T, and those also give you edges out of the cut. So the total size of the cut is the size of U minus X plus the size of Y. However, you'll note that all edges in G connect to either a vertex in Y or a vertex in U minus X. So one way to find a bound on your matching is by finding a set of vertices such that every edge in your graph connects to one of those vertices. And working this out gives us what's called Koenig's theorem, which says if G is a bipartite graph and K is the size of the maximal matching, then there has to be a set S of only K vertices of the graph, such that each edge in G connects to one of these vertices of S. And you'll note that if you have such a S, that gives you a bound on the maximal matching, because each edge needs to use up one of those vertices, and no two edges can share a vertex. And so Koenig's theorem says that sort of the maximum matching on the graph is the same as the minimum what's called vertex cover, set S of vertices that connect to all edges. So, for example, if we have the following graph, you'll note that these four vertices connect to every single edge in the graph. So that says immediately the maximum matching has size at most 4, and it turns out that in this case it's tight. Now, there's one more special case of Koenig's theorem that's worth mentioning. That's the case where G is a bipartite graph with n vertices on each side. One thing that you might want to do is produce what's called a perfect pairing on G. That is a matching that uses every single vertex on both sides. Now, it's a theorem that if you sort of specialize Koenig's theorem to this case, you can show that there's always a perfect pairing unless there's some set of only m vertices on the left-hand side, such that the total number of vertices that they connect to is strictly less than m. So you can always pair up your n men with your n women, unless there's some collection of m men that pair with a total of fewer than m possible women. And if that's the case, these m men cannot all simultaneously have distinct dates, and so it's clearly not possible to produce your perfect pairing. So in summary, we've got this interesting problem of maximum matching, and we can solve it by reducing it to a problem of finding maximum flows. Furthermore, max flow min cut gives us some interesting characterizations of the sizes of this maximum matching. So that's all I have to say about bipartite matchings. Come back next lecture and we'll talk about one more problem that you can solve using this max flow technology that we've developed. Hello everybody, welcome back to our course on advanced algorithms and complexity. Today we're starting a new unit. We're starting to talk about linear programming problems. And in particular, today we're going to give just a simple example of the sort of problem that we will be trying to solve during this unit. So imagine that you're running a widget factory and you'd like to optimize your production procedures in order to save money. Now, these widgets, you can make them using some combination of machines and workers. Now, you have only 100 machines in stock, so you can't use more than that. But you can hire an unlimited number of workers. However, each machine that you're trying to use requires 2 workers in order to operate it. Additional workers can be building things on their own, but machines that you're using require 2 workers on them. Now, in addition to this, each machine that you use makes a total of 600 widgets a day, and each worker that's not currently involved operating a machine makes 200 widgets a day. Finally, the total demand for widgets is only 100,000 widgets a day. So if you make any more than this, they just won't sell, and that's no good for anybody. So writing these constraints down in a reasonable way, if we let W be the number of workers that we have and M the number of machines, we have a bunch of constraints. The number of workers should be non-negative. The number of machines should be between 0 and 100. The number of workers needs to be at least twice the number of machines. And then finally, 100,000 is at least 200 times the number of unoccupied workers, that's W minus 2M, plus 600 times the number of machines. And so these constraints sort of constrain which allowable combinations we can have. Now, we can try and graph these constraints. So here we've got a plane of possible values of M and W that satisfy these constraints. Now, if we're just starting where M and W both need to be non-negative, we have this quadrant as the allowable values. But when we require that M needs to be at least 100, we're reduced to being in this strip here. When we look at our constraint based on the total demand, we find that M plus W is at most 500, and so we're now constrained to this region. And when we add the final constraint that the workers need to be at least twice the number of machines, we finally come to this diagram of possible configurations of machines and workers that we can use. What's next? Profit. Well, suppose that profits are determined as follows. Each widget that you make earns you $1, but each worker that you're hiring costs you $100 a day. So the total profit that you get then in terms of dollars per day, well, it's number of widgets, 200 workers minus twice machines, plus 600 times number of machines, minus the total salaries you pay to workers, 100 times the number of workers. So that's 100 times the number of workers plus 200 times the number of machines. And if we want to plot that on our graph, we can do it as follows. So these lines that I've drawn are lines of equal profit. There's a line with $30,000 a day, and then $40,000 a day, and then $50,000 a day. And sort of as you go from left to right or from bottom to top, you make more profit. So what we're trying to do now is we're trying to say, well, what can we do to get the most profit? And it turns out the best you can do is at this point here. Note that it's a corner of the allowable region. It's where we have 100 machines and 400 workers, and the total profit is $60,000 a day. Now, it's clear from this diagram that this is the best you can do, but if you actually want to prove it, there's a clever way you can do that. So, two of the constraints that we have, one of them is that the number of machines is at most 100, and another is that 200 times the number of machines plus 200 times the number of workers is at most 100,000. Now, if we take 100 times the first constraint and add it to a half times the second constraint, what you find is that 200 times the number of machines plus 100 times the number of workers has to be at most 60,000. And that says the profit that we make has to be at most 60,000. And so this is a very convenient way to prove that the 60,000 that we could attain is actually the best we can do. So in summary, what we did is we solved this problem where we maximized this function 200m plus 100w subject to the following list of 5 constraints. And this, because the thing we're trying to maximize is a linear function and the constraints we have are linear inequalities, this makes this an example of the type of problem we're going to be looking at, that is a linear program. So come back next lecture and we'll sort of formally define this problem and get us started on our investigation of it. Hello everybody, welcome back to our unit on linear programming. Today what we're going to do is we're sort of going to put everything on sort of a more solid, rigorous basis. So remember last time what we did is we had this factory problem where what we wanted to do is we wanted to maximize in terms of m and w, this 200m plus 100w, this linear expression, subject to the following list of linear inequalities that they had to satisfy. And so, in general, basically just this is what a linear program is. It says we want to find real numbers x1 through xn that satisfy a bunch of linear inequalities, so a11 x1 plus a12 x2 plus dot 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 is at least b1, and then a bunch more of those. And subject to these constraints, we would like a linear objective function, v1 x1 plus v2 x2 plus etc., to be as large or possibly as small as possible. To clean up the notation a bit, we're really going to store this by having a matrix A that encodes sort of the coefficients of all of these inequalities along with vectors b and v. And our output should be a vector x in Rn such that a times x is at least b. And what I mean by this is that if you multiply the matrix A by the vector x, then you get a new vector where the first component of that is bigger than the first component of B, the second component is at least the second component, and so on and so forth. And note that if you just unroll what that means, it's exactly the system of linear inequalities that we had on the previous slide. Now, subject to this constraint, we would like v dot x to be as large or as small as possible. So, linear programming, it turns out, is incredibly useful because there are an extraordinary number of problems that can be put into this framework. To begin with, the factory example that we solved in the last lecture was exactly of this form. Optimize a linear function with respect to some linear inequality constraints. But there's a ton more problems that fit into this. One of them is the diet problem, which was studied by George Stigler in the 1930s and 40s, and intuitively it's a very simple problem. How cheaply can you purchase food for a healthy diet? This is really important if you, say, need to feed an army full of soldiers, for example, and want it to be cheap. So how do you do this? Well, you've got a whole bunch of variables. For every type of food that you could possibly eat, you need to know how many servings per day of that food you're going to have. So you've got a variable x sub bread, x sub milk, x sub apples, so on and so forth. And then you've got a bunch of constraints. Firstly, for each type of food, you need to have a non-negative number of servings of that food. It wouldn't do to have -3 servings of bread a day. And additionally, you need to have enough nutritional content. You need to have sufficiently many calories per day. So how many calories do you have? That's just the number of calories in a serving of bread times the number of servings of bread you eat, plus the number of calories in the serving of milk times the number of servings of milk you eat, plus so on and so forth over every type of food. And this should be at least 2,000, or whatever your minimum calories per day for your diet is. And in addition to this constraint, we have another similar looking constraint for each other nutritional need. Vitamin C, protein, what have you. And so we have a bunch of linear inequalities as our constraints on these variables. And subject to these constraints, we want to minimize our total cost. And the cost of our diet is just the cost of a serving of bread times the number of servings of bread we eat, plus the cost of a serving of milk times the number of servings of milk we eat, and so on and so forth. So we want to minimize a linear function of these variables subject to a bunch of linear inequality constraints. This is a linear program. You can solve it, and it will tell you in some sense the cheapest diet that you can live on. Unfortunately, I should warn you that actually doing this is maybe not the best idea. When you solve this, the solution tends to optimize for like a few very efficient foods for getting calories and protein, and then maybe a few random things to like fill in your other dietary needs very cheaply. But I mean, it might say that you should eat mostly, potatoes and peanut butter, and then like a bunch of vitamin pills or something. And so these tend not to produce diets that you'd actually want to consist entirely on, but maybe if you want to think about what can I do to eat more cheaply, it's something to look at. So another problem that fits very nicely into this linear programming formulation is network flow. It turns out that the network flow problems that we discussed in the last lecture are actually just a special case of linear programming problems. So if you want to solve max flow, you've got a bunch of variables, f sub e, the flow along each edge e, and they satisfy some constraints. For each edge e, f sub e is between 0 and the capacity of the edge. And then for every vertex that's not a source or a sink, you have conservation of flow. So the total flow into that vertex is the same as the total flow out of that vertex. Now, when you first look at this, this might not seem to be an inequality. It's an equality, not an inequality. But you could actually just write it by writing down two linear inequalities. You could say the flow into the vertex is at least the flow out of the vertex, and on the other hand, the flow into the vertex is at most the flow out of the vertex. And so if you just put these two inequalities together, it's equivalent to this one equality. So once we've put these constraints on, we now have an objective function. We'd like to, subject to these constraints, maximize the flow. That's the total flow going out of sources minus the total flow going into sources, which is a nice linear function. And so this max flow problem is just a special case. When you phrase it this way, it's exactly a linear program. Now, a lot of the time when you look at a linear program, it's exactly what I said. You subject to these constraints, there's a unique maximum value which attains the best possible value of the objective function. However, there are a couple of edge cases that you need to keep in mind where things don't quite work out this way. The first is you could actually have a system where there's just no solution. You could have constraints say x is at least 1, y is at least 1, and x plus y is at most 1. If you have this system of constraints, which is graphed here, there's actually no solution. Because if x and y are each at least 1, x plus y needs to be at least 2. And so there's no solution to the system, so you can't even start with trying to find a maximum. It could also be the case that even though your system has solutions, there's no actual optimum. And the way that this could happen is as follows. If you have the system where x is at least 0, y is at least 0, and x minus y is at least 1, there's actually no maximum value for x here. Basically, the region is graphed here, but it's sort of, you could go higher and higher and higher up. X is actually unbounded in the system. And so in some sense, your solution should say that there's no maximum. Now, just to review this, I've got three pretty simple systems here, each with two equations and two unknowns. Now, one of these systems has no solution. One of them has solutions, but no solution with a maximum x value. It's unbounded. And the third one actually does have a unique maximum x value. And so I'd like you to take a little while, think about which one of these is which. Okay, so if we actually graph these three systems, A, it turns out, has no solution. One equation says we're supposed to be bigger than 1. The other one says we have to be less than 0. You can't do both of those. B, if you write it down, does have a unique maximum at, I think, x equals 1.5, as plotted there. It's the red point. And C, although it does have plenty of solutions, if you graph this region, you'll note that if you sort of slide up along this line x equals y, you can make the x value as large as you want. And so there are solutions, but there's no maximum. In any case, that's all that I had to say about sort of this basic introduction to linear programs. Come back next time and we'll start by looking at a special case of dealing with linear equalities rather than inequalities. Hello everybody, welcome back. Today we're talking more about linear programming, or actually we're not. We're looking at sort of a simpler problem first. So linear programming talks about dealing with systems of linear inequalities. Today we're going to look at sort of a simple special case of this, where we look at systems of linear equalities. So, for example, we have the system of linear equalities x plus y equals 5, 2x plus 4y equals 12. And we'd like to be able to solve this for x and y. So, the very general way to do this is by what's known as the method of substitution. You use the first equation to solve for one variable in terms of the others. You then take that variable and substitute it into the other equations. You now have a bunch of equations in n-1 variables, and you recursively solve those. Then once you have the answer to those equations, you substitute them back into the first equation to get the value of the initial variable. Okay, let's see how this works in practice. So, x plus y is 5, 2x plus 4y is 12. Using the first equation, we solve for x as 5 minus y. We substitute that into the second equation, and we find that 12 is equal to 10 plus 2y. Solving that for y, we find out that y equals 1. And substituting back into the first equation, x is equal to 5 minus 1, which is 4. So x equals 4, y equals 1. That's the solution to this system. Now, just to make sure we're on the same page, if we have the system x plus 2y equals 6, and 3x minus y is negative 3, what is the value of x in the solution to that system? Well, the answer is 0 here. So from the first equation, we get x is equal to 6 minus 2y. Substituting into the second, we get that minus 3 is 18 minus 7y. Solving that tells us that y equals 3. So x is equal to 6 minus twice 3, or 0. And that's the answer. Okay, so that was our first example. Let's look at another example. We have a system of linear equations, x plus y plus z equals 5, 2x plus y minus z equals 1. So we solve this by substitution. Great. From the first equation, x is equal to 5 minus y minus z. We substitute that into the second equation, and we solve for y. We find that y is equal to 9 plus 3z. Great. We now know what y is, and we want to solve for z, but we can't. There are no equations left. We've already used the first equation to solve for x and the second to solve for y. We can't solve for z because there's nothing left. But this is actually fine for us. It turns out that any value that we assign z will give us an actual solution. You give me any value for z, we set y equal to 9 plus 3z, and then x is 5 minus y minus z, or minus 4 minus 4z. And any value of z gives us a solution. So there's an entire family of solutions. We can let z be a free variable, and for any value of z, we have a unique solution. So in general, your solution set will not necessarily be a point, but it will be a subspace. You'll have some free variables, and no matter what settings you give those, you'll have your other variables will be functions of your free variables. Now, this subspace has a dimension, which is just the number of free variables, the number of parameters you need to describe a point on it. And generally speaking, each equation that you have gives you one variable in terms of the others. And so generally speaking, the dimension of your set of solutions is going to be the total number of variables minus the number given in terms of others. So the total number of variables minus the number of equations. So generally speaking, if you have n equations and n unknowns, there'll be no free variables left, and you'll have a unique solution. However, if you have n plus 1 equations and n unknowns, the first n of your equations solves for the unique solution, and then the extra equation probably is something that isn't satisfied by that solution. So generally, if you've got too many equations, there are no solutions to the system. However, if you have n minus 1 equations and n unknowns, you generally solve those and you'll still have one free variable left. So generally speaking, you'll have a full dimension 1 subspace. You'll have a line as your solution instead of just a point. Okay, so in summary, we can solve systems of linear equations using the method of substitution. And generally speaking, and this isn't always the case, but generally, each equation reduces the number of degrees of freedom by 1. Now, if all you want to do is solve systems of linear equations, you could basically stop here. But we want to do more than that. So next time what we're going to do is we're going to talk about how to systematize this whole thing and simplify the notation sum to make this into an honest algorithm that we're going to discuss. And so when you want to talk about how to tell your computer to solve systems of linear equations, that is what we're going to talk about in the next lecture. So I'll see you then. Hello everybody, welcome back to our linear programming unit. Today we're going to talk about Gaussian elimination. So the basic idea is that last time we talked about how to solve linear systems by substitution. Today we're going to make it into an algorithm. So remember, last time we could solve systems of linear equations using this method of substitution. And to begin with, we would like to simplify the notation a little bit. Because the way we did it, you had to write down these full equations. X plus y equals 5, 2x plus 4y equals 12. These have variables and addition signs and equality signs and all this mess. The only thing that really matters are the coefficients of these equations. So what we're going to do is we're going to simplify notation and just store these coefficients in what's known as an augmented matrix. That's a matrix with this little bar coming down in the middle of the entries. So here, each row is going to correspond to a single equation, and the entries in that row are going to be the coefficients. So the first row, 1, 1, 5, translates to 1 times x plus 1 times y equals 5. X plus y equals 5. The second row, 2, 4, 12, means that 2x plus 4y equals 12. And so this little matrix is sort of just a convenient way of storing that system of linear equations. Now, one complication that this method runs into is when we're storing things in this matrix, how do we implement substitution? How do we solve for x, for example? There's a real sense in which we can't write a row that corresponds to the equation x equals 5 minus y. Every row corresponds to an equation where x and y are on the same side of the equality, so this sort of doesn't work. On the other hand, the row 1, 1, 5 is almost as good. It corresponds to the equation x plus y equals 5, which is equivalent. The next question we ask ourselves is how do we substitute this into the second equation? Because once again, the immediate thing you get when you substitute has x's and y's on sort of, I guess they're still on the same side, but it's got constants on the wrong side of the equation now. And so you can't substitute directly, but really you can do something almost as good. What you can do is, the substitution was just to get rid of the x's in that second equation. And you can do that by subtracting. If you subtract twice the equation, 2x plus y equals 2 times the equation x plus y equals 5, from the equation 2x plus 4y equals 12, that tells you that 2y equals 2, which is exactly what you would have gotten from substitution. And this corresponds to a very nice operation on the matrix rows. You just subtract twice the first row from the second to get the row corresponding to this guy. Okay, so we're given this augmented matrix, and what we're going to do is we're going to manipulate it. We're going to use what are called basic row operations. These are ways of transforming your matrix to give you an equivalent system of equations. Now the first of these is addition, which is what we just saw. You add or subtract a multiple of one row from another row. So for example, we subtract twice the first row from the second, and 2, 4, 12 becomes 0, 2, 2, which is good. Next off, though, we have that 2y is equal to 2, and we want to change that to y equals 1. So to do that, we need to use scaling. We need to multiply or divide a row by a non-zero constant. And that's just multiplying the equation by a constant, so we should be good. So if we divide the second row by 2, instead of getting 0, 2, 2, it becomes 0, 1, 1, y equals 1. Now, in some sense, these two operations are enough, but for bookkeeping purposes, we might want to reorder the way in which we list the rows. So a final operation is to swap the order of two of the rows. So just list the second row up top and the first row down bottom. This clearly doesn't really affect anything. We're just sort of listing our equations in another order. So these are the three basic row operations. And what we're going to do is we're going to combine them into an algorithm called row reduction, or sometimes Gaussian elimination, where we're going to use these operations to put our matrix in a simple standard form. And the idea is actually very simple. We're just going to simulate the method of substitution. Okay, so let's consider this example. We have a big matrix here. It corresponds to a system of 3 equations in 4 unknowns, which I'll call x, y, z, and w. And we'd like to solve them. So, method of substitution, what do? We use the first equation to solve for the first variable x. And in some sense, this first equation, 2x plus 4y minus 2z equals 2, is already implicitly solves for x in terms of the other variables. But for simplicity, we'd like to rescale it such that the x entry is 1. So we divide the row by 2, and now it says x plus 2y minus z is 1. Or equivalently, x is equal to 1 minus 2y plus z. We now want to substitute that value into the other equations, which we do by adding this row to others to clear out the x entries. So we add the first row to the second, and we subtract twice the first row from the third. And now there are no other entries in that column in any of our other rows. Okay, so now we're done with x. We want to solve for the next variable y using the two other equations. We actually can't use the second equation to solve for y because there's no y in that equation. The entry is 0. But we can use the third equation. So what we're going to do for bookkeeping purposes, we're going to swap the second and third rows, just so that the row we're using to solve for y is up top. We now want to solve for the second variable, by which we mean rescale so that entry is 1. So we divide by minus 2. And now we want to substitute this value into the other equations. So we subtract twice the second row from the first, and actually the third row is okay. Now the thing to note is we can't actually solve for z. The last equation doesn't have z. The first two equations have z terms in them, but we've already used those equations to solve for x and y. So actually what we're going to do here is we're going to skip z and move on to w. We can solve for w in terms of this variable. So we divide the last row by minus 2. We get the equation w equals 0. And we substitute that into the other equation. So we subtract twice the third row from the first, and then add the third row to the second. And now we're actually done. This is basically as simple as our matrix is going to get. But now that we have this, it's actually very easy to read off the solutions. We have this matrix. It corresponds to the equations x plus z is minus 1, y minus z is 1, and w equals 0. And here you can basically read off the solution. For any value of z, we have a solution. X is equal to 1 minus z, y is equal to 1 plus z, and w equals 0. And that's the general solution. Great. So how do we row reduce a matrix in general? What we're going to do is we're just going to take the leftmost non-zero entry. This is the thing we're going to solve for. We swap that row to the very top of the matrix, just for bookkeeping purposes. That leftmost entry we're going to call a pivot. We're going to use it to clear out the other entries in its column. We rescale the row to make that entry 1, because we want to actually solve for that variable. We then subtract that row from all the others to make the other entries in that column 0. Then we've just substituted that into the other equations, and we're going to repeat this. Well, with slight modifications. We want the leftmost non-zero entry not already in a row with a pivot. We then swap that row to be the top of the non-pivot rows. We make the new entry a pivot, we rescale, we clear out the other columns, and we keep repeating until all of the non-zero entries are in pivot rows. And then we're done. Once you have that, it's actually pretty easy to read off the answer. Each row is going to have one pivot entry and maybe a few other non-pivot entries. This will give an equation that writes the pivot variable in terms of a bunch of non-pivot variables. Now, there's a special case. If there's a pivot in the units column, that means that we have the equation 0 equals 1. And if that happens, we have a contradiction, and there are no solutions. But otherwise, the non-pivot variables, the variables corresponding to columns with no pivot in them, these are actually free variables. We can set those to whatever we want, and then once we've done that, each of our rows tells us what the pivot variables should be in terms of the non-pivot variables. And that's it. One final thing to discuss is the runtime of this operation. If you have n equations and m equations and n variables, there are a minimum of n and m pivots. Whenever you find a pivot, you need to subtract a multiple of that row from each other row. Now, each row has n entries that you need to deal with the subtraction for, and there are m rows, so that takes O of nm time. And so the total runtime is O of n times m times the minimum of n and m. And this is pretty good. It's polynomial in n and m. You could maybe expect to do a little bit better, and in fact, there are sophisticated algorithms that do that. But for practical purposes, this is actually a pretty good runtime, and is a very usable algorithm. So that's basically all for our sort of linear algebra sidebar. Next lecture, we're going to go back to talking about linear programs with systems of linear inequalities and how to deal with them. So until next time. Hello everybody, welcome back to our linear programming unit. Today we're going to talk about convex polytopes. In particular, we're going to try to understand what the solution set to the system of linear inequalities that we need to deal with actually looks like. So remember, in a linear program, we're trying to optimize a linear function subject to a bunch of linear inequality constraints. Today we're going to ask the question, what does the region of points defined by these inequalities actually look like? So, for example, this factory example that we looked at way back at the beginning, if you looked at the set of solutions to these 5 inequalities, you got this nice trapezoid here. So the question is, what do things look like in general? Well, another example, if you look at the system where x, y, and z in 3 dimensions are all between 0 and 1, you get the unit cube. And in general, you can get much more complicated looking regions, but you'll always get what's called a convex polytope. And don't worry, we'll unroll this meaning as we go. So the first thing to note is, what does a single linear equation look like? Well, if you look at the linear equality, it defines a hyperplane, an infinite flat surface. Now, if instead you want an inequality, it gives you what you call a half space. It gives you a hyperplane and everything on one side of that hyperplane. So if we want the solutions to a system of linear inequalities, we have a thing defined by a bunch of half spaces. We want the intersection of all of these half spaces. We want everything that's inside all of them, because we want to solve all of the equations. And so we sort of get a thing that's defined by these hyperplanes. In fact, what we'll always get is a polytope. That's a region in Rn that's bounded by finitely many flat surfaces. But in fact, polytopes have a little bit more structure than that. If you think about the cube, not only do we have the 6 faces, but these faces intersect at edges, and those intersect at vertices. And so a polytope in general will have, these surfaces may intersect at lower dimensional facets, like edges, but perhaps of other dimensions, where the 0-dimensional facets are called vertices. But it turns out that not every polytope is actually possible as a solution, as sort of the set of solutions to such a system of linear inequalities. For example, the donut pictured here is a polytope, but it's not a solution to one of these systems, Because if you look at some of these inward pointing faces, well, these faces lie on a hyperplane, but you've got portions of your region on both sides of that hyperplane. Whereas if you have a polytope defined by one of these systems of linear inequalities, each bounding hyperplane is actually coming from one of those linear inequalities, and you can only have points on one side of that hyperplane or the other. So we have this extra condition that everything must be on only one side of each face. And that leads us to the condition of convexity. A region C in Rn is called convex if for each pair of points x and y in C, the line segment connecting x and y is entirely contained in the region C. So the lemma is that any intersection of half spaces, or set of solutions to these systems, is convex. And the proof is not that hard. Our system is defined by ax at least b. We need to show that if 2 points x and y are in this set, then everything on the segment containing between them is also in the set. Well, the line segment you can parameterize as points of the form tx plus 1 minus t times y, where t is a real number between 0 and 1. So the test of that point is in our set. We take a times tx plus 1 minus ty. That's equal to tax plus 1 minus tay. Since x and y are in the set, that's at least tb plus 1 minus tb, which is b. And so every point on the line segment is in our set, so the set is convex. Great. So the theorem is the region defined by a system of linear inequalities is always a convex polytope, which is nice. So to review, we've got three pictures here. Which of these three regions, A, B, C, is a convex polytope? Well, it turns out only B is. So A is not convex because we have this line segment here where the end points are in A, but some of the points in the middle aren't. C is not a convex polytope because there's this region of the boundary here that's sort of a curved region, whereas if it were a polytope, all of the boundary regions would have to be straight lines. B, on the other hand, is actually a convex polytope. Okay, so to conclude this lecture, we're going to actually prove a couple of important lemmas about convex polytopes. So the first one is separation. If you have C to be, in fact, any convex region, and X is a point not in C, then it turns out there's always a hyperplane H that separates X from C, where X is on one side and C is on the other. Now, if C is given by a system of linear inequalities, this is actually easy to prove. Because if X isn't in C, it violates one of these defining inequalities, and that inequality gives you a hyperplane where C is on one side and X is on the other. But in general, you can prove this as well. You start with X. We're going to let Y be the closest point in C to X. And it turns out you can just take the perpendicular bisector of xy. This is, or the hyperplane of points equidistant between x and y. Now, this is clearly a hyperplane. To show that it separates x from c, we're going to suppose that, well, suppose there were some points z and c that were on the wrong side of this hyperplane. Well, z and y are both in c, so everything on the line segment between z and y is also in c. But you can show that there's actually always a point on this segment zy that's closer to x than y was. And this is a contradiction, because by assumption, y was the closest point in C to x, and we've just found a closer one. So that completes the proof. Okay, so the other lemma is about polytopes. Suppose that you have a polytope and there's a linear function on this that you're trying to minimize or maximize. The claim is that it takes its minimum or maximum values on vertices. This is clearly relevant to our linear program because we're exactly trying to minimize and maximize linear functions on these convex polytopes. So we saw this in this original factory example where the maximum was at this vertex, and it turns out that happens in general. Now, to maybe get some intuition for why this is true, we've got our polytope, and this polytope is sort of spanned by the corners. It's got corners and like things in between these corners. But because we have linear functions, like the things in between the corners are never as good as the extreme points, and so the optimum must be at the corners. Now, to actually prove this, the thing to note is that if you have a linear function defined on a line segment, it always takes extreme values at the two endpoints. And we're going to use this to sort of push our point towards the corners and let the values get bigger and bigger. So we start at any point in our polytope, and what you do is you draw a line through it. And you'll note that the biggest value that our linear function takes on this line comes all the way when that line hits an end of the polytope. So it takes the extreme point at the end point of that line, which is on a face of your polytope. Now, once you're on a face or some facet, you can repeat this. You draw a line through that point, and what you know is that the extreme values will be at the end points of this line, and that lets you push it to a lower dimensional facet, and you keep doing this until you end up at a vertex. And so we started at any point, and we kept going until we hit a vertex, and that vertex has at least as large a value as the point we started with. And so the maximum values must be attained at some vertex. So in summary, the region defined by a linear program is always convex. The optimum of this linear program is always attained at a vertex. And finally, if you have a point that's not in the region, you can always separate it from points on the inside by an appropriate hyperplane. So these are some basic facts about linear programs and their solution sets. Come back next time, we'll talk about another interesting property of linear programs called duality. Hello everybody, welcome back to our linear programming unit. Today we're going to talk about an interesting phenomenon in linear programs called duality. So let's recall the first example that we looked at here. We wanted to maximize 200m plus 100w subject to this bunch of equations. Now it turns out we had a very clever way of proving that our optimum was correct once we'd found it. So the best you could do was 60,000, and there was a great way of proving it. We took one constraint, we multiplied it by 100. We took another constraint and we multiplied it by half. We added those together and we got a new constraint that if we satisfied our original constraints, it had to be the case that 200m plus 100w, the thing we were trying to optimize, was at most 60,000. And this is a very interesting and general technique that if you want to bound your objective, you can try and do this by combining the constraints that you have together to prove a bound. So let's see what happens in general. You have a linear program. You say you want to minimize v1x1 plus v2x2 plus ... all the way up to vn xn, subject to a bunch of these linear inequality constraints. a11x1 plus a12x2 plus ... is at least v1, and then etc., etc. So how can we try and do this? Well, if you give me any constant ci bigger than 0, you can take the first constraint and multiply it by c1, and the second constraint and multiply it by c2, and so on and so forth, and add those all up. And what you'll get is a new linear inequality, w1x1 plus w2x2 plus ... is at least t. Here the wi are some combination of the c's. Wi is the sum of cj, aj, and t is the sum of cj, bj. And this is a new inequality. Now, if it's the case that wi is equal to vi for all I, what we have is that v1x1 plus v2x2 plus ... that thing we were trying to minimize, is at least t. And so if we can arrange for wi to be vi for all I, we've proven a lower bound on the thing that we're trying to minimize. So what we'd like to find is a bunch of ci's that are all non-negative, such that vi is the sum of j equals 1 to m of cj, aji for all I, and so that subject to these constraints, t, the sum of cj, bj, is as large as possible. So we like the biggest lower bound we can. Now, the very interesting thing about this is that this system we just wrote down is actually just another linear program. We want to find the c in Rm such that cj, bj, the sum of that, is as large as possible, subject to a bunch of linear inequalities, ci bigger than or equal to 0, and a few linear equalities. vi is the sum of cj times aji. And so, to put this formally, given any linear program, which we call the primal very often, say minimize v dot x subject to ax at least b, there's a dual linear program, which is the linear program where we want to maximize y dot b subject to y transpose A equals v, and that's just another way of rewriting our equality constraints, and y at least 0. And it should be noted that even if your linear program wasn't exactly in this form, you can still write a dual program as sort of the linear program of trying to find a combination of the constraints to bound the thing that you're trying to optimize. And so it's not hard to show that a solution to the dual program bounds the optimum for the primal. Suppose that you have a solution for the dual. You've got a y bigger than or equal to 0, such that y transpose A is equal to v. Then for any x where ax is at least b, well, x dot v is equal to y transpose ax. That's at least y transpose b, which is y dot b. And so y dot b, the solution to the dual, is a lower bound for the solution to the primal. Now, the surprising thing is that not just is this a way that we can get lower bounds, that these two linear programs, they actually have the same solution. If you find the best solution to the dual program, it actually always gives you a tight lower bound for the primal. And so the theorem here is linear programming duality, that says a linear program and its dual have the same numerical answer. And this is incredibly useful. On the one hand, it says if you have a linear program and want to prove that your answer is optimal, you could try and solve the dual to provide a matching upper bound or lower bound. It also means that if all you care about is the numerical answer, you could try to solve the dual program rather than the primal. And often the dual program is easier to solve, and so this makes things more convenient. And even if the dual program isn't easier, often looking at the dual gives you some insight into the solution to the primal. Okay, so that's linear programming. Duality. Let's look at some examples. For example, let's look at the max flow problem. The size of your flow is the total flow going out of a source minus the total flow going into a source. Now, we have a bunch of these conservation of flow equations, and we can add any multiples of those that we like, and the objective stays the same. So when we do that, the thing we're trying to maximize is the same as the sum over all vertices v of some constant c sub v times the total flow out of vertex v minus the total flow into vertex v. Here, c sub s needs to be 1 if s is a source, and c sub t needs to be 0 if t is a sink. But for any other vertex v, we can take c sub v to be anything we like. Okay, so we have this expression. What do we get when we write this down? This is a sum over edges from v to w of the flow along that edge times c sub v minus c sub w. We can now try to bound this above using our capacity constraints. And so the best we can do here, it's not hard to show, is the sum over edges v to w of the capacity of the edge E times the maximum of either c sub v minus c sub w or 0. Okay, so this gives us an upper bound. If we want this upper bound to be as small as possible, it's not hard to show that we should pick our c sub v to always be either 0 or 1. Now, if we do that, let's let script c be the set of vertices where c sub v equals 1. The bound that we prove then reduces to the sum over edges vw, where v is in script c and w isn't, of the capacity of the edge. But you'll note, c is just a cut, and this bound that we proved is just the size of the cut. And so this dual program, in some sense, is just trying to find the minimum cut. Hence, linear programming duality in this special case just gives us the max flow equals min cut theorem. Okay, let's look at this other example, the diet problem. Here we want to minimize the total cost of foods you need to buy, subject to constraints. It needs to meet your various daily requirements for various nutrients, and you need to get a non-negative amount of each type of food. So, we've got the system. What's the dual program look like? Well, okay. So for each nutrient n, we have some multiples, c sub n, of the equation for that nutrient. And then we can add on positive multiples of the constraints that you get a non-negative amount of each type of food. Okay, so when we combine all of those together, we're supposed to get a lower bound on the cost of our diet. And so if you compare coefficients, well, the coefficient we need to end up with for a food f is the cost of that food. And this should be equal to the sum over nutrients n of C sub n times the amount of that nutrient in food F, plus some positive amount that we got by adding whatever multiple we had of the constraint that we got a non-negative amount of that food. So what this says is for each food F, the cost of food F should be at least the sum over nutrients n times the amount of that nutrient showing up in this food. But there's a nice way now of interpreting this C sub n. We can interpret it as a cost in order to buy a unit of nutrient n. And so if there was a market where you could just buy calories at the cost of C sub n, and you could buy protein at the cost of whatever, what the above equations are saying is that for each food, you can't sort of cheat this system. By buying that food, you can't get nutrients more cheaply than you could by buying the nutrients individually. And if the cheapest way to get nutrients is buying them individually, it's pretty clear that the total cost of a balanced diet is at least just the sum over nutrients, so the cost of that nutrient, times the amount of that nutrient that you're required to have in your diet. And so what this linear program tries to do is it tries to find non-negative costs for the various nutrients that satisfy this no food allows you to cheat inequalities, such that the total cost of your diet is as large as possible. Now, there's one interesting observation about the solution. Suppose that we were actually trying to exactly achieve this lower bound. That would mean that you could never afford to buy overpriced foods. You could never afford to buy foods where the cost of that food was strictly bigger than the total cost of all the nutrients that make up that food. You could only buy foods where the cost of the food is exactly the cost of the nutrients in that food. And this gives us is an example of a general phenomena called complementary slackness, where basically what this says is that if you look at the solution to the dual, if you sort of look at which equations you needed to use in the dual program, that tells you about which equations in the primal program need to be tight. So, in particular, complementary slackness is the following theorem. If you give me a primal linear program, minimize v dot x subject to ax at least b, and it's dual, then if you take solutions to these two, if you use a positive multiple of an equation in the dual, if yi is strictly bigger than 0 in the dual, this happens only if the ith equation in the solution to the primal is actually tight. It's actually, the ith inequality is actually an equality in the optimal solution. So to review what this means, let's suppose that we have a linear program defined by these 5 linear inequalities labeled 1, 2, 3, 4, 5 in the diagram below. The allowable region is this gray region, and the red point located is the optimum. Now, suppose that we're looking for solutions of the dual program. Which of these 5 equations might actually be used as sort of positive multiples of those equations in the solution to the dual program? Well, it turns out the only equations that you could actually use are 2 and 4, because complementary slackness says that the only equations that get used in the solution to the dual are ones where that equation is tight in the primal. And in this case, 2 and 4 are the only lines that this solution to the primal actually lies on. And so those are the only equations that could actually be used in the solution to the dual. So, in summary, every linear program has a dual linear program. The solutions to the dual act as bounds on solutions to the primal. And surprisingly, the LP and its dual have the same answer. And this means that the solution to the dual actually gives you a tight bound on the solution to the primal. And additionally, we have this complementary slackness, where knowing the solutions to the dual tells you a lot about where the solution to the primal lies. In fact, it tells you which equations in the solution to the primal need to be tight. So that's basically everything that we have for this lecture. Next lecture, we're going to talk about proofs for these things. So that material is not necessarily required, but if you'd like to see it, it's informative. Hello, everybody. Welcome back to the Linear Programming Unit. Today, we're going to talk about the proofs from the duality lecture. So remember, last time we showed that to each linear program, we could associate a dual program, which was basically attempting to find a non-negative combination of our constraints that put a bound on the objective function. So, in particular, we had the duality theorem, which said the linear program and its dual always have the same numerical answer. Today, we're going to prove that. So before we get into the proof, let's talk a little bit about intuition. So one way to think about this is the region defined by our linear constraints is sort of a well. It's bounded by these linear walls. And you need to minimize, say, a linear constraint. Say you want to minimize the height of a point inside this well. Now, if you understand some physics, one way to do this is you just take a ball that's pulled down by gravity, you drop it into the well, and gravity will pull it down to the lowest point. Now, when it reaches this point, the ball is at rest, and that means the forces acting upon it need to balance. So the force of gravity pulling it down needs to be balanced by the normal forces from the walls pushing it back up. Now, when you write this down, you have a linear combination of these normal vectors pointing orthogonally to these walls has to equal the downwards pointing vector from gravity. And if you work out what this means in terms of the equations, the downward pointing vector, that's the direction in terms of your objective. It points in the direction of your objective. And the normal pointing vectors, those are sort of the vectors that correspond to the equations defining the walls that you're on. And so, if you sort of work out exactly what this means and like put it in terms, it exactly is linear programming duality. You have a solution to the dual program that matches your primal. And if you'll even note which walls you use, only the walls that the ball is actually touching, that actually gives you a taste of why complementary slackness might be true. You only get to use the walls that the ball is actually touching, which are the ones for which your equations are tight. In any case, let's look at an actual proof. So the first thing that we're going to do is, instead of looking at an optimization problem, we're going to look at a solvability problem. We'd like to say, when is there a solution to ax at least b and x dot v at most t? So we claim that there's a solution to the system unless some combination of these constraints yields a contradiction, yields the equation 0 bigger than 1. Of course, if you yield that from a combination of your constraints, it's clear your constraints cannot all simultaneously be satisfied. But it turns out that this is sort of if and only if, and if we can prove this, that will actually be enough to give us the original problem. Because basically the only way we can do that is if combining the constraints not including the last one, we could conclude in a constraint that x dot v needs to be strictly bigger than t. Okay, so let's see how that works. Now, suppose that we have a bunch of constraints, and now we want to look at all possible combinations of these constraints. So C1E1 plus C2E2 plus dot 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 plus CMEM, where the CI's are some non-negative constants. Now, the thing to note is that the set of sort of inequalities that we can derive in this way, the set C, is actually a convex set. Now, what happens if the equation 0 bigger than 1 is not in this set C? Well, you've got a point that's not in a convex set. That means that there has to be a separating hyperplane. Now, what this separating hyperplane is, it's a little bit weird. It's sort of a hyperplane in the set of linear inequalities. But it turns out that from this hyperplane, you can extract a solution to the original system of equations. So this is a little bit abstract, so let's look at something slightly more concrete. We have a system of linear inequalities, all of the form something x plus something y is at least 1, and want to know, is there a solution to this system? Well, we're going to plot these equations. Here we've got a bunch of equations of the form ax plus by is at least 1, and we've plotted all the values of a and b. Now, it's clear that none of these equations is the contradiction 0 bigger than 1. That would be the point at the origin. But we also have to consider linear combinations of these. It turns out the linear combinations of these equations you can get are exactly the gray region here. Now, it's still the case that 0 bigger than 1 is not in this region, but it's a convex region, so there has to be a separating hyperplane. Here we have the separator a plus b is bigger than 0. So what does this mean? Well, it means that all of our equations were of the form ax plus by at least 1, with a plus b being at least 0. Now, what this means, though, is if we take x equals y equals the same big number, ax plus by is equal to a plus b times this big number. Since a plus b is positive and this other number is big, that's actually more than 1. And so we actually have a solution if x equals y is a big number. And in particular, x equals y equals 1 gives us a solution. And so what we were able to do here is we said, well, 0 bigger than 1 is not a linear combination. We have a separating hyperplane. And by looking at the form of this hyperplane, it allowed us to find an actual solution to our system. And this is sort of how it works in general. Okay, so that's the proof of duality. We should also look at complementary slackness. Remember what this said is if we have our linear program and it's dual, then if you have a solution to the dual where yi is strictly bigger than 0, this can happen only if the ith equation in the primal is tight. The proof of this is really actually not that hard. You take a solution x to the primal and a matching solution y to the dual. So the best you can do in the primal is x dot v equals t, but by duality, you get a matching lower bound in the dual. So there's a combination of these linear inequalities ei, so this sum of yi ei yields the inequality x dot v is at least t. Now, each of these equations, ei, those were true equations for that value of x. And the final inequality that we get is actually tight. So we have a sum of a bunch of inequalities that gives us a tight inequality. The only way that that can happen is if the inequalities we used are tight. And so that means for each I, either the inequality ei is tight or yi is equal to 0. And that proves complementary slackness. Okay, so that's all that we have for this lecture. Come back next time and we will go back and start talking about some formulations and different ways of looking at linear programming problems. Hello everybody, welcome back to our unit on linear programming. Today we're going to talk about some sort of different types of linear programming problems, sort of all related but not quite the same. So the point is there are actually several different types of problems that go under the heading of linear programming. Now, the one that we've been talking about so far we might call the full optimization version. Minimize or maximize a linear function subject to a system of linear inequality constraints, or maybe say that the constraints have no solution if they don't. Now, it turns out there are a number of sort of related problems dealing with sort of systems of linear inequalities that you might want to solve that are maybe a little bit easier and will actually be important as when we start coming up with algorithms in the next couple of lectures, they will actually be solving algorithms in this other formulations. So the first one is optimization from a starting point. Given a system of linear inequalities and a vertex of the polytope that they define, optimize a linear function with respect to these constraints. So you're given a place to start. Another version is what we might call solution finding. Given a system of linear inequalities, no objective whatsoever, find some solution to these systems, assuming it exists. This is also somewhat easier. And finally, we can ask just satisfiability. Given a system of linear inequalities, determine whether or not there is a solution. So it turns out that these problems are actually equivalent. If you can solve any one of these, you can solve any others, which is very convenient because the algorithms we'll be looking at will each only solve one of these versions. So first off, it's clear that the full optimization problem is the strongest of these. Using that, you can solve anything else pretty easily. If you have optimization from a starting point, you can just ignore the starting point and solve the problem from scratch. If you're trying to find a solution, well, the optimal solution is a solution. And if you merely want to know if there's a solution, well, you try and run the full optimization. If it outputs a solution, you have the solution. Great. But the nice thing is that you can go the other direction. If you can only solve optimization from a starting point, you can actually do the full optimization. And the problem here is, how do you find the starting point? If you had a starting point, you could run the algorithm and you'd be done. But somehow you need a solution to this system. And there's actually a clever way to do this. You add equations one at a time. So now we have a solution to the first 7 of your equations. We now need to make it a solution to the first 8. For that, we need to say, well, maybe your solution doesn't satisfy this 8th inequality. But what you can do is you can optimize. So not only do we want to satisfy these 7, but we want to make this 8th inequality maybe as true as possible. And that will give you a solution that satisfies all of them. So to see how this works, let's look at an example. We start with this rectangle in a nice corner of it. We now want to add an inequality that chops our rectangle at this line. So what we're going to do is we're going to say, well, we want our sort of point to be as much below this line as possible. That's just a linear optimization question. So we can solve that using our optimization from starting point algorithm. We get that vertex. And what do you know? It's a solution to this bigger system. Next, we want to add this thing as an inequality. So again, we solve our optimization from a starting point. We find a solution. We can now add the additional inequality. We add another one, find a solution. And then finally, we've got all of our equations in the mix. We now need to perform our optimization, and we can do that. So this is basically how you do it. You add one equation at a time. There is a technical point to keep into account. Things are a bit messier if some of these intermediate systems that you're trying to solve don't have optima. They might be sort of one of these unbounded systems where things can get as large as you like. Now, to fix this, I mean, it's not hard. You just need to play around a bit. First, you want to start with n constraints. That means you actually have a single vertex to start at in your system. And then when you're trying to add the constraint v dot x at least t, you don't just maximize v dot x. That would be sort of a problem because that might be unbounded. So what you'll do is you'll add the additional constraint that v dot x is at most t. And this guarantees that v dot x will actually have a maximum at t, and once you find it, that'll be good enough. Okay, so that was that. Let's talk about solution finding now. How do we go from being able to find a solution to finding the best one? We somehow need to guarantee that the solution we found was the best solution. But there's actually a good way to do that. We can use duality. The point is that duality gives you a good way to verify that your solution is optimal by solving the dual program and providing a matching upper bound. So what you want to do is you want to find both a solution to the original program and a matching dual solution. So if you want to minimize v dot x subject to ax at least b, what you can do is you can instead solve this bigger system. Ax at least b, y at least 0, y transpose a at least equal to v. That says x is a solution to the primal and y a solution to the dual. And then we also want x dot v equal to y dot b. So now we have a matching solution to the primal and the dual. The fact that we have the solution to the dual means that you can't do any better in the primal. And so this actually, any solution to this system, if you look at x, that will give an optimal solution to the original problem. Finally, let's talk about satisfiability. How does it help to just know whether or not there is a solution? How is this going to help you find an actual solution? Well, we know that there's always a solution at a vertex of your polytope. And that means that n of these equations that we have are actually tight. Now, all we need to do is figure out which equations are tight, and then you can solve for the intersection of those equations using Gaussian elimination. So how does this work? We have a bunch of linear equations. Here are the lines where we've got the equalities. And the system, the solutions to that system is this hidden triangle here. We want to find a point on this triangle. So what are we going to do? We're going to pick some equation here and say, is there a solution to not only this linear system, but this linear system where that equation is actually an equality? And for this guy, the answer is no, because there's no point in the triangle that also lies on that line. That means we can actually throw out that line. There are no solutions. That line actually doesn't help us at all. Next, we try another one. This guy doesn't work. We throw him out. This guy, yes, there are solutions that are both on inside the triangle and on this line. So we keep that equation around as an equality and then try another one. What about this guy? Is there a solution to this system where we're on both of those lines? No, the intersection of those lines is not a solution, so we keep going. What about these lines? Yeah, if you look at the intersection of those lines, it gives you that point, which is a solution. But now we know that there's a solution at the intersection of those lines. We solve for that intersection with Gaussian elimination, and we're done. And so by just solving a whole bunch of satisfiability questions, we're able to actually resolve this question and actually find a point that satisfies it. So to make sure that we understand this, if we want to find a solution to a linear program with m equations and to n variables, how many times would we have to call the satisfiability algorithm in order for this to work? Well, the answer is we need to do it m times. You need to test each equation once. When you find equations that work, you keep them around, but you don't need to test them again. Those are equalities, and you just keep checking the other ones. Each equation needs to be tested once. That's a total of m times. But you run this satisfiability algorithm m times, and it gives you a solution to actually finding a point. So those are the different formulations. Next time, we're actually going to come back and start looking at honest algorithms for solving linear programs. Hello, everybody. Welcome back to our unit on linear programming. Today, we're finally going to get to an actual algorithm to solve linear programs. In particular, we're going to talk about the simplex method, which is basically the oldest algorithm for solving linear programs. And as it turns out, it's still one of the most efficient. Now, unfortunately, as we'll see, the runtime of this algorithm isn't quite as good as we would like, but it's still pretty reasonable for many contexts. So, first off, remembering our lecture last time, this is going to solve a specific formulation of linear programming. And in particular, it's going to solve optimization from a starting point. So if you want to use this method to solve an actual full optimization problem, you'll have to remember how to do that based on the last lecture. So what's the idea here? We start at some vertex of our polytope, and we know that the optimum is at another vertex. So what we're going to do is we're going to just find a path between vertices that sort of as we go, our objective will get better and better and better until we reach the optimum. So how do vertices work? Well, you get a vertex of your polytope when you look at the intersection of n of the defining equations. When you take n of your defining equations, you make them all tight, they intersect at a vertex, and you can solve for that vertex using Gaussian elimination. Now, if you relax one of these equations, then instead of having a zero-dimensional thing, you have a one-dimensional thing, and you end up with an edge. You get a set of points of the form p plus tw, where t is non-negative. The constraint that you relaxed requires that t now be non-negative. So this gives you an edge, and it continues, t being 0 all the way up to whatever, until you violate some other constraint in your linear program, and then you get another vertex at the other end of the edge. Now, if v dot w is bigger than 0, if you follow this edge, you get a larger value of the objective at the new vertex. So here's the pseudocode for the simplex algorithm. It's actually pretty easy. You start at a vertex p, and you repeat the following. You look over each equation passing through p, and you relax that equation to get an edge. If, when you travel along that edge, it improves your objective, you replace p by the vertex you find at the other end of that edge. And then you break. You go back to for each equation running through p. If, however, there was no improvement, you tried every edge going out of p, none of them did any better, you actually know that you're at the optimal vertex and you return p. Now, to look at what does it mean to go to the other end of this edge, it's basically what we said before. Your vertex p was defined by n equations. You relax one equation, and now the general solution of these n minus 1 equations is a point of the form p plus tw over real numbers t. You solve for this using Gaussian elimination. The inequality that you relaxed requires, say, that t be bigger than or equal to 0. And each other inequality in the system might put other bounds on which t are valid to have solutions to your equation. Now, some of them might put upper bounds on t. They might say t is at most 7 or at most 10 or whatever. And of those upper bounds, you take the smallest of them and call that t naught. Then p plus t naught is the vertex that you will get at the other end of that edge. Now, to show that this is correct, we need to prove the following theorem. If p is a vertex that is not optimal, then there's actually some vertex adjacent to p that does better. And this means that we will keep finding better and better vertices until we find the best one, the optimum, and then we can return that. Now, the proof of this isn't so hard. You've got a vertex p, it's the intersection of n equations, e1 through en. Now, what you'd like to do to prove this is optimal is you want to use sort of the dual program. You want to find a positive linear combination of e1 through en to find an upper bound, x dot v is at most whatever. Now, you, of course, can't always do this, but it's actually going to be the case that you can basically always write x dot v less than or equal to something as some linear combination of these constraints, possibly using negative coefficients. Now, if all the coefficients were positive, of course, we have a matching solution to the dual program. P is optimum. However, if some of the coefficients were negative, you can actually show that if you relax the equation with a negative coefficient, then that actually will give you an edge where if you move along that edge, your optimum gets better. And so that proves the theorem. If we're not at the best point ever, then we can find an edge to follow that does better. Okay, so how long does the simplex algorithm take? Well, basically, taking one step on this path isn't so bad. It's a nice polynomial time thing involving trying a bunch of edges and doing some Gaussian elimination. But we do have to take this path that goes from wherever we started to the optimum. And how long the algorithm takes will depend on how long that path is. And unfortunately, the path might be somewhat long. So we suppose that we have this sort of almost cube-like thing as sort of the polytope defined by this linear system. We're trying to optimize the height. We're trying to go up as far as possible. We start at the marked vertex, and we're going to use the simplex method to travel to other vertices, increasing the height as we go. Now, the question, of course, is what's the longest path that we might need to take? What's the longest number of steps that we might need to take in order for the simplex algorithm to complete on this example? Well, unfortunately, it might take as many as 7 steps to find the optimum, because it's possible that we could take this path as shown that actually passes through every single vertex in the polytope. Now, some paths are better. Some other paths could take as few as 3 steps, but 7's big. And in fact, if you do an n-dimensional version of this, you might have only 2 inequalities that take actually 2 to the n steps to get where you're going. And this really isn't so good. And so it turns out the runtime of simplex is proportional to the path length. Now, the path length in practice is very often very reasonable. However, you can always find there are some unusual examples where the path length is actually exponential. And this means that simplex algorithm sometimes takes quite a long time to finish. Now, there's one other technical problem, and this is degeneracy. So in this analysis, we assume that only n hyperplanes intersected at a vertex. And that's not always the case. For example, in the picture that we have here, we've got a pyramid. And the vertex of that pyramid is on 4 of the defining hyperplanes, even though you're in only 3 dimensions. And if you have some of these degenerate vertices, it's actually a little bit hard to solve the system because we don't know which equation we're supposed to relax in order to follow an edge. We actually have to relax 2 of our equations to get to an edge, and we wouldn't know which ones to use. So there's actually a fix for this, which is not very hard, which is if you take all of your equations and tweak them by just a tiny, tiny bit, this basically doesn't change your solution at all, but it avoids having any of these degenerate intersections. Now, in fact, if you're willing to be a little bit more sophisticated, you can run a version of this fix that doesn't involve actually changing things at all. You can sort of make infinitesimal changes, changes that are sort of only formally there. So you number your constraints, 1, 2, 3, 4, 5, etc. You strengthen the first constraint by epsilon, and the next by epsilon squared, and the next by epsilon cubed, where epsilon is just some incredibly tiny number, sort of so tiny that it just doesn't matter for anything. Then in practice, when you want to solve the system, you don't actually need to change any of your equations. If you're at a degenerate point, you need to keep track of which n equations you are really on, which are really the n equations defining this point. And then when you're traveling along an edge that hits a degenerate point, you need to figure out which is the new equation you're actually adding. And for this, you should always add the lowest numbered constraint at the new corner. So if you hit a new corner that actually has 3 hyperplanes passing through it, you pick the lowest numbered of them to be the real one. Now, when you do this, you in fact might have some edges that pass from a degenerate corner to itself. And this is fine as long as you keep track of which n hyperplanes you're actually on at any given time. and you make sure you only actually use that edge if it improves your objective. If the edge that you followed, which should have had 0 length, was in a direction at least that made things better for you. But when you do this, we have a nice algorithm called the simplex method. It solves linear programs by moving between adjacent vertices trying to hit an optimum. It actually works pretty well in practice, but potentially is exponential time. And if you're really worried about that, come see the next optional lecture that we're doing on the ellipsoid algorithm, which is a much more modern technique for solving linear programs. Hello everybody, welcome back to the linear programming unit. Today we're going to talk about one more algorithm for solving linear programs, namely the ellipsoid algorithm. So remember last time we had the simplex algorithm. This solves linear programs. It works pretty well in most cases, but in some of the time it's actually exponential, which is a problem. Today we're going to talk about the ellipsoid algorithm. This again solves linear programs. It's actually polynomial time in all cases, but it turns out in practice is often not as good as the simplex method. So to begin with, the ellipsoid algorithm solves a particular formulation. It solves the satisfiability version of a linear program. Given the set of constraints, will just tell you whether or not there is a solution. So here's how the algorithm works. The first thing you do is you take all of the equations and relax them by a tiny, tiny bit. You make them a tiny bit more lenient. And if there weren't solutions before, there still won't be solutions. But if there were solutions before, even if beforehand there was only a single point that was a solution, there's now going to be some small positive volume in your set of solutions. Fine. The next thing you do is you bound the set of solutions with a large ball. You find a large ball that either contains all of your solutions or maybe just contains a large fraction of, like some notable fraction of your solutions, assuming that they exist. And this isn't too hard to do by just taking it really, really, really big. Then what you do is you have a ball, or in general an ellipsoid, that contains all of your solutions. What you do is you look at the center of this ellipsoid and say, is that a solution to your equations? On the one hand, it might be a solution to your system, in which case you found a solution, your system is satisfiable, and you're done. On the other hand, it might not be a solution. If it's not a solution, we have a point that is not in a convex region, so you can find a separating hyperplane that separates this center from your region. What this means is that your entire convex region is on that side of the hyperplane. So instead of being contained in your ellipsoid, is actually contained in a half ellipsoid. However, when you have a half ellipsoid, you actually can find a new ellipsoid whose volume is smaller than the one you started with, that contains this entire half ellipsoid. And thus we now have a smaller ellipsoid that also contains your set of solutions. So now what we're going to do is we're going to iterate this. We keep finding smaller and smaller ellipsoids that contain our solution set. And eventually one of two things happens. Either eventually we find that the center of our ellipsoid is actually contained in our solution set, in which case we're done. Or eventually we end up with ellipsoids that are really, really tiny and yet still guaranteed to contain our entire set of solutions. But from step one, when we did this relaxation, we knew that if there were solutions, our set of solutions had some small positive volume. And eventually we'll find ellipsoids that are smaller than that. And therefore, they're too small to contain our solution set if they existed. And then we will know that there must be no solutions. So what's the runtime of this? Well, you have to figure out how many iterations it takes. It's a little bit of a mess. But the runtime of the ellipsoid algorithm is something like O of m plus n squared times n to the fifth times log of nu. Where here n is the dimension of the space that you're working in, m is the number of equations that you're trying to solve, and u is the numerical size of the coefficients. So things to notice about this. One, it's polynomial. Hooray, we have a polynomial time algorithm for solving linear programs, and this is pretty great. However, it's a bad polynomial. It runs in something like n to the 7 time. N to the 7 is really not that great, and there are lots of circumstances where I'd rather take an exponential algorithm, or a mildly exponential algorithm at least, over an n to the 7 algorithm. Finally, we'll note that the runtime actually depends, albeit logarithmically, on the size of the coefficients. And this might be a problem if you have really, really complicated coefficients in your linear program. This sort of affects like how much you can relax your equations and how big the ball needs to be. And if you have these sorts of problems, ellipsoid will run very slowly. Whereas if you're running the simplex method, no matter how big your coefficients are, at least the number of algebraic operations that you need to perform doesn't depend on the size of the coefficients. Now there's one final thing to note about the ellipsoid algorithm. We don't really need that much information about our system of equations, or inequalities. All we really need is what's called a separation oracle. That is, given a point, x, we need to either be able to tell, is x in our system, or is there, if not, we need to find some hyperplane that separates x from our set of solutions. And there are actually some circumstances where you don't have explicit sets of equations, or defining your system, but can produce a separation oracle. And in these cases, you can actually use the ellipsoid algorithm to solve linear programs, even though you don't have an explicit list of finitely many equations. And this is really useful in some cases. So in summary, the ellipsoid algorithm is another way to solve linear programs. It has better worst-case performance than simplex. However, it's usually going to be slower. In practice, it's generally not as good. However, on the plus side, you can run the ellipsoid algorithm only with access to a separation oracle, which is nice, and there are definitely a few contexts where being able to do this is quite useful. In any case, that wraps up our unit on linear programs. I hope you enjoyed it. Come back next time, and Sasha will start talking about complexity theory. And in particular, we'll be talking about various aspects of NP-complete problems. So I hope you come back for that, and I'll see you then.
Hello and welcome to the next module of the Advanced Algorithms and Complexity class. In this module, we are going to meet problems that are computationally very hard. In all previous modules, we considered many efficient algorithms for various computational problems. And by saying efficient, we usually mean polynomial time algorithms. And this is why. Consider 4 algorithms shown here on the slide. The running time of the first algorithm is just n. As usual, by n, we denote just the size of the input. The running time of the second algorithm is n squared, so it is a quadratic time algorithm. And the third one is a cubic time algorithm. And the last one has running time 2 to the n. So here we have polynomial time algorithms, 3 polynomial time algorithms, and the last one is exponential time. The second row here in the table shows the maximum value of n for which the total number of steps performed by the corresponding algorithm stays below than 10 to the 9. Why 10 to the 9? Well, just because this is roughly the estimate for the number of operations performed by modern computers in 1 second. So we are interested in the maximum value of n for which the running time of the corresponding algorithm stays below than 1 second. It is not difficult to compute these values. Well, for the first algorithm, this is 10 to the 9, of course. For the second algorithm, this is 10 to the 4.5. And for the third one, it is 10 to the 3, right? So polynomial time algorithms are able to handle instances of size roughly thousands or even millions. While for exponential time algorithms, the maximum value for which it performs less than 10 to the 9 operations is roughly 30. So it allows us to process only very small instances. Recall that any exponential time function grows faster than any polynomial time function. So for this reason, exponential time algorithms are usually considered as impractical. Note, however, the following thing. Usually, for many computational problems, the corresponding set of all candidate solutions is exponential. Let me illustrate this with a few examples. Assume that we are given an object and our goal is to find an optimal permutation, an optimal, in some sense, permutation of these objects. A naive way to do this would be to go through all possible such permutations and to select an optimal one. The running time of the corresponding algorithm, however, is going to be at least n factorial, because there are n factorial different permutations of n given objects. And n factorial grows even faster than any exponential function, than 2 to the n, for example, which means that the corresponding algorithm is going to be extremely slow. Another example is the following. Assume that we're given an object and we need to split them into two sets. For example, we need to partition the set of vertices of a graph into two sets to find a cut. Then again, a naive way to do this would be to go through all possible partitions into two sets and to select an optimal one. However, there are 2 to the n ways to split the n given objects into two sets. And if we do this naively, the running time of our algorithm is going to be at least 2 to the n. And we know that this is very slow. This only allows us to handle instances of size roughly 30 in less than 1 second. Another example is, assume we need to find a minimum spanning tree in a complete graph. That is, in a graph where we have an edge between every pair of vertices. A naive way to do this would be to go through all possible minimum spanning trees and to select one with minimum weight. However, the total number of spanning trees in a graph on n vertices is n to the n minus 2. Again, this grows even faster than 2 to the n, and this makes the corresponding algorithm completely impractical. So once again, in many cases, an efficient polynomial algorithm is called efficient, in particular because it avoids going through all possible solutions, so candidate solutions, which usually has exponential size. In the rest of this module, we will learn that there are many computational problems that arise frequently in practice, actually, for which we still don't know an efficient, that is, polynomial time algorithm. For such problem, roughly the best we can do is to go naively through all possible candidate solutions and to select the best one. Right? It will turn out also surprisingly that all these seemingly different problems, millions of problems, they are related to each other. Namely, if you design an efficient algorithm, a polynomial time algorithm for at least one of them, this will automatically give you a polynomial time algorithm just for all these problems. At the same time, constructing such an algorithm turns out to be an extremely difficult task. In particular, there is a $1 million prize for constructing such an algorithm or proving that there is no such algorithm. We will now give a formal definition of a search problem. And we will do this by considering the famous Boolean satisfiability problem. The input for this problem is a formula in conjunctive normal form, which is usually abbreviated just as CNF. So a formula in conjunctive normal form is just a set of clauses. In this case, in this example, we have 5 clauses. This is the first one, this is the second one, the third one, the fourth one, and the last one. Each clause is a logical or a disjunction of a few literals. For example, the first one is a disjunction of literals x, y, and z. The second one is a disjunction of x and the negation of y. The third one is a disjunction of y and not z, or a negation of z, and so on. So x, y, and z are Boolean variables. That is, these are variables that take Boolean values. The Boolean values are true and false, and we will usually use 1 instead of true and 0 instead of false. So what this formula tells us is the first clause actually constrains the values of x, y, and z to be so that either x is equal to 1 or y is equal to 1 or z is equal to 1. Right? So this is just x or y or z. The second clause tells us that either x must be true or the negation of y must be true. That is, either x is equal to 1 or y is equal to 0. And so on. For example, the last clause tells us that either x is equal to 0 or y is equal to 0 or z is equal to 0. Then the Boolean satisfiability problem, or just satisfiability problem, which is also abbreviated as SAT usually, is stated as follows. Given a formula in conjunctive normal form, we would like to check whether it is satisfiable or not. That is, whether it is possible to assign Boolean values to all variables so that all clauses are satisfied. If it is possible, we need to output a satisfying assignment. If it is not possible, we need to report that no such assignment exists. Now we give a few examples. In the first example, we are given a formula over two variables x and y. It contains three clauses and it is satisfiable. To satisfy it, we can assign the value 1 to x and the value 0 to y. Let's check that it indeed satisfies all three clauses. Well, in the first clause, x is satisfied, in the second clause, not y is satisfied, in the last clause, x is satisfied, right? In the second example, we illustrate that a formula may have more than just one satisfying assignment. For example, for this formula, there is a satisfying assignment which assigns the value 1 to x, y, and z, and there is another satisfying assignment which is shown here. Okay? For the last formula is unsatisfiable, and probably the most straightforward way to check this is just to list all possible truth assignments to x, y, and z. So there are 8 such assignments. Let me list them all. Then for each of these assignments, we need to check that each of them falsifies at least one clause. For example, the first one falsifies the first clause. When x and y and z are equal to 0, the first clause is falsified, right? For the second one, it falsifies the clause y or not z, right? The third one falsifies the clause x or not y, and so on. So it can be checked that each of these 8 assignments falsifies at least one clause. So another way of showing that this formula is satisfiable is the following. Let's first try to assign the value 0 to x. Then let's take a look at the following clause. So it is x or not y. X is already assigned 0. So the only way to satisfy this clause is to assign the value 0 to y. So setting x to 0 forces us to set y to 0 also. Now let's take a look at this clause. It forces us to set the value 0 to z also. But then we see that this clause is already falsified, right? Which tells us that our initial move, to assign 0 to x, was a wrong move. That we need to assign the value 1 to x. Let's try to do this. If x is equal to 1, let's take a look at the following clause. Not x is already falsified in this clause, so we need to assign the value 1 to z. Now let's take at this clause. Not z is already falsified here, so we need to assign the value 1 to z. To y, I'm sorry. But then this clause is falsified. So no matter how we assign x, it forces us to some other assignments, and in the end, we falsify some clause, which justifies that this formula is unsatisfiable. SAT is a canonical hard problem. It has applications in various branches of computer science. In particular, because many hard combinatorial problems are reduced very easily to the satisfiability problems. Many hard combinatorial problems can be stated very naturally in terms of SAT, and then when a problem is stated in terms of SAT, we can use a so-called SAT solver, which is a program that solves the satisfiability problem. There are many such programs, and there is even an annual competition of SAT solvers. SAT is also a classical example of a so-called search problem. In a search problem, we are given an instance I, or just an input I, and our goal is to find a solution for this instance, a solution S, or to report that there is no such solution. For example, in case of the SAT problem, an instance I is a formula in conjunctive normal form, and S is a satisfying assignment. For this formula, we need to check whether there is a satisfying assignment and to return 1 if it exists, or to report that this formula is unsatisfiable. That is, that there is no satisfying assignment. A natural property to require from a search problem is that we can quickly check whether a given solution S is indeed a solution for I. For example, in case of SAT, it is easy. If we are given a truth assignment of values to all the variables, we can quickly check whether it satisfies all the clauses. Namely, we just scan all the clauses from left to right, and for each clause we check whether it contains a literal that satisfies this clause. Another natural property is that we require the length of S to be bounded by polynomial in the length of I. Right, so we want S to be not very large. We do not want S to have, for example, exponential size in the length of I. In this case, it would require us an exponential time just to write down a solution for the instance I. So once again, the natural property of a search problem is the following. We have an algorithm which checks whether the given solution S is indeed a solution for an instance I in time, which is bounded by polynomial in the length of I only. This also forces the length of S to be bounded by a polynomial of I. In fact, it is convenient to define a search problem through such a very fine algorithm. Namely, we say that a search problem is defined by an algorithm C that takes two parameters as an input, an instance I and a candidate solution S. It should run in time polynomial in I, in the length of I, and we say that S is a solution for the instance I if C of IS returns true. For example, SAT is clearly a search problem. In this case, once again, I is a CNF formula and S is a truth assignment of Boolean values to variables. And this algorithm C just scans all the clauses and checks whether each clause contains a literal that is satisfied by the given assignment S. Of course, its running time is polynomial in the length of the formula. Right? In the next part, we will see a few examples of search problems that arise frequently in practice for which we still don't know polynomial time algorithms. Our first hard problem is the traveling salesman problem. In this case, we're given a graph with n vertices and we assume that it is complete, that we know the distance between any two vertices. Together with this graph, we are given a budget B. And our goal is to find a cycle in this graph that visits each vertex exactly once and has total length at most B. Finding a short cycle visiting all the given points is a usual task solved by delivery companies. For example, this is how an optimal cycle looks like if we need to deliver something into 15 biggest cities in Germany. Another application is drilling holes in circuit boards. Assume that we have a machine that needs to visit some specific places in a circuit board to drill holes in these places. Of course, we would like our machine to visit all these places as fast as possible. And for this, we need to find a cycle that visits all these places whose length is as short as possible. Note the following subtlety. The traveling salesman problem is of course an optimization problem. Usually we are given just a graph, and our goal is to find an optimal cycle that visits each vertex exactly once. That is a cycle of minimum total weight, of minimum total length. At the same time, in our statement of this problem, we also have a budget B, and our goal actually is to check whether there is a cycle that visits every vertex exactly once and that has total length at most B. We did it to ensure that this is a search problem. Indeed, it is very easy to check whether a given solution is indeed a solution. For this, we need to check that what is given to us is a sequence of vertices that forms a cycle that visits each vertex exactly once and has total length at most B. It is easy to do. We just trace this cycle and check that its length is at most B. Right? However, it is not so clear for an optimization version. If you are given a cycle, how are you going to check whether it is optimal or not? Once again, we stated the decision version of the travel and salesman problem to ensure that this is a search problem. At the same time, in terms of algorithms, these two versions of this problem, I mean an optimization version where we need to find an optimal cycle and the decision version where we need to check whether there is a cycle of total length at most b, these two problems are hardly different. Namely, if we have an algorithm that solves an optimization problem, we can of course use it to solve a decision version. If we have an algorithm that finds an optimal cycle, we can of course use it to check whether there is a cycle of length at most b or not. And vice versa, if we have an algorithm that for every b checks whether there is a cycle, of length at most b, we can use it to find the optimal value of b by using binary search. Namely, we first, for example, check whether there is an optimal cycle of length 100. If yes, we check whether there is an optimal cycle of length 50. If there is no such cycle, we then check whether there is a cycle of length at most 75, and so on. So eventually we will find the value of b such that there is a cycle of length b, but there is no cycle of smaller lengths. At this point, we have found the optimal length of a cycle that visits each vertex exactly once. And this is done by calling our algorithm a logarithmic number of times. A naive way to solve the travel and salesman problem is to check all possible n factorial permutations of our vertices. This will give an algorithm whose running time is roughly n factorial. And this is a very quickly growing function. For example, already for n equal to 15, n factorial is about 10 to 12, which means that this algorithm is completely impractical. There is a better algorithm whose running time is still exponential. It is based on dynamic programming, and we will see it later in our class. Its running time is n squared times 2 to the n, where n is the number of vertices. So it is still exponential, but it is much better than n factorial. In fact, we have no better algorithm for this problem, unfortunately. So this is the best upper bound that we can prove. In particular, we have no algorithm that solves this problem in time, for example, 1.99 to the n. At the same time, there are algorithms that solve this problem in practice quite well, namely, even when n is equal to several thousands, it is usually solved by heuristic algorithms. So such algorithms solve practical instances quite well in practice. However, we have no guarantee on the running time of such algorithms. And also there are approximation algorithms for this problem. For such algorithms, we have a guarantee, a theoretical guarantee on the running time. At the same time, what they return is not an optimal solution, but a solution which is not much worse than optimal. For example, an approximation algorithm that we will study later can find in polynomial time a cycle which may not be optimal, but it is guaranteed to be at most 2 times longer than an optimal one. It is instructive to compare the travel and salesman problem with the minimum spanning tree problem. Recall that in the minimum spanning tree problem, we're given a graph, or just a set of cities, and our goal is to connect all these cities to each other by adding n-1 edges of minimum possible total length. For example, the minimum spanning tree for this set of 6 cities might look like as follows. So we added 5 edges to connect all these 6 cities. Now consider the travel and salesman path for the same set of cities. So for a moment, assume that in the travel and salesman problem, we need to find not a cycle, but a path. Okay? Then in this case, the optimal path for this set of 6 cities might look like this. Note that in this case, this path, what we're looking for, an optimal path, is also a tree, right? So this is a tree with five edges that spans all the vertices. This means that the travel and salesman problem is a problem that we get from the minimum spanning tree problem by posing an additional restriction that the tree that we're looking for should be actually a path, right? So this is emphasized here. And by posing this additional restriction to the minimum spanning tree problem, we get a problem for which we know no polynomial time algorithm. So once again, for this problem, for the minimum spanning tree problem, we have an algorithm whose running time is almost linear. For this problem, we have no polynomial time algorithm. We have no algorithm whose running time is quadratic or cubic or something like, or even something like n to the 1000. This is a very difficult problem, resulting from the minimum spanning tree problem by posing some additional small restriction. Our next search problem is the Hamiltonian cycle problem. The input to this problem is a graph, directed or undirected, without weights on edges, and the goal is just to check whether there is a cycle that visits every vertex of this graph exactly once. For example, for this graph, there is such cycle. It is shown here on the slide. It is not difficult to check that it indeed visits every vertex exactly once. And for this reason, in general, this problem is a search problem. Given some sequence of vertices, it is easy to check that each vertex appears in this sequence exactly once, and that there is an edge between any two consecutive vertices in this sequence. The Eulerian cycle problem looks very similar to the Hamiltonian cycle problem. In this problem, we are given a graph again, and our goal is to find a cycle that visits every edge exactly once. So, in the Hamiltonian cycle problem, we need a cycle that visits every vertex exactly once. In the Eulerian cycle problem, we are looking for a cycle that visits every edge exactly once. It turns out that the Eulerian cycle problem can be solved very efficiently. Namely, there is a very simple check whether the input graph is Eulerian or not. That is, whether it contains an Eulerian cycle or not. This is given by the following theorem. So it deals with undirected graph. Assume that we are given an undirected graph, then it contains an Eulerian cycle if and only if it is connected and the degrees of all its vertices is even. We now give two toy examples that in particular will shed some light on how to prove the just mentioned theorem. Our first example is a graph in which there is no Eulerian cycle. That is a non-Eulerian graph. There is no Eulerian cycle in this graph in particular because the degree of this vertex is equal to 3. Let's prove that if the degree of this vertex of a vertex in a graph is equal to 3, then this graph does not have an Eulerian cycle for sure. First, assume that such a cycle existed, and assume that it visited this vertex, let's denote it by V, for example, exactly once. So this is a cycle that visits every edge of our graph exactly once and goes through V exactly once. But in this case, V would have our degree exactly 2, right? There are two edges. We used one of them to go out of V, and we used another of them to come back to this vertex V, right? But in our case, the degree of V is equal to 3. Now assume that there is an Eulerian cycle that visits the vertex V at least 2 times. So let's start our cycle from the vertex V. So we walk through our graph, we get back to V, and then we walk again, and then get back to V again. But since in our cycle we visit each edge exactly once, in this case we see that there are at least 4 edges adjacent to V, right? So which means that either our degree of V is equal to 2 or it is at least 4. And in general, it is not difficult to see that if we have an Eulerian cycle, then the degree of each vertex must be even, because each time when we leave, when we come into some vertex, we need to have a matching edge which we use to go out from this vertex, right? We now show an example of an Eulerian cycle in a graph, and we also show how to find it quickly. Okay, this is the same graph with two vertices added to it. And in this graph, we can see that the degrees of all vertices are even. Namely, the degree of this vertex is 2, the degree of this vertex is 4, this is also 4, this is 6, this is 2, this is 4. So all of them are even, which means, and this graph is connected, which means that this graph contains an Eulerian cycle. Let's try to find it. Well, let's just, for concreteness, let's start from this vertex. And let's just walk through this graph. Okay, we first traverse this edge, then we traverse this edge, then we get back to this vertex. At this point, we return to the vertex for which there are no more unused edges, right? However, there are still some unused edges in our graph. Let's just take, and let me also mark this cycle as the first one. So we constructed some cycle, but still there are some unused edges. Let's just start traversing the unused edges from some vertex, for example, from this one. Okay, we then might traverse this edge and then again get back to the initial vertex, and this is cycle number 2. Okay, there are still some unused cycles, some unused edges. So let's for example, let's start from this vertex and let's traverse another cycle. So this is the third cycle. We are currently constructing the third cycle. So we go here, then here, then we get back here, and then we get back here. So at this point, we used all the edges. However, what we have is not just one single cycle, but a bunch of cycles. But the nice property is that if we have several cycles, it is easy to glue them together into a single cycle. Schematically, it can be shown as follows. So assume that we have some cycle, and we have some other cycle, and then at some other point we have other cycle. Then what we can do is to traverse these cycles as follows. So we first go here, then we go this way, then we go this way, and finally we go this way, right? Let me illustrate how to do this on our example graph. So we first go on this edge, then we use this cycle, then we continue on our first cycle, then we traverse this cycle, the third cycle, and finally we get back to the initial vertex. And this is how, in general, an Eulerian cycle can be constructed. We just walk in the graph, and when we return back to a vertex which has no unused edges, we just start traversing another cycle from some vertex. The fact that it is connected, the fact that the initial graph is connected, ensures that then all the constructed cycles are connected to each other. And then we can glue them easily to construct a single cycle, visiting each edge exactly once. Let's now summarize. We have two similarly looking problems. In the first one, in the Eulerian cycle problem, we need to find a cycle that visits every edge of a given graph exactly once. This problem can be solved efficiently in linear time in the size of the input graph. In the second problem, in the Hamiltonian cycle problem, we are looking for a cycle that visits every vertex of our graph exactly once. For this problem, we have no polynomial time algorithm. Our next problem is also about paths in graphs. It is called the longest path problem. Here we are given a graph, a weighted graph, and two vertices S and T together with a budget B, which is just a number. And our goal is to find a simple path whose total length is at least B. To give a specific example, consider this graph again and consider the following two vertices. The shortest path, assume also that all the weights or all the lengths of the shown edges are equal to 1. Then the shortest path between the following two vertices uses just one edge, and its length is equal to 1. On the other hand, there is a very long simple path here in the graph. It visits all other vertices before going from one vertex to the other one, right? So it turns out that the longest path problem is very difficult. It also looks very similar to the shortest path problem, in which we need to find the shortest path, or if we state its decision version, then we are given a graph and a budget b, and our goal is to find a path whose length is at most b. We know that this problem can be solved very efficiently. For example, if all the weights are equal to 1, that is, the given graph is unweighted, then it can be solved with breadth first search just in linear time. In the longest path problem, we need to find a path of length at least b, and for this problem, we know no polynomial time algorithm. Our next hard search problem deals with integers and linear inequalities. Namely, the problem is called integer linear programming. The input to this problem is a set, or a collection, or a system of linear inequalities, which we present here in matrix form. And our goal is to find integer values for all the variables that satisfy all the inequalities. To give a toy example, consider the following three inequalities. The first one says that x1 should be at least 1/2. The second one says that minus x1 plus 8x2 should be non-negative. And the last one says that minus x1 minus 8 times x2 should be at least minus 8. As usual, we can represent the set of all solutions, all feasible points to this system of linear inequalities as a convex polygon as follows. We first draw a half space that contains all points which satisfy the first inequality. It is shown here as in green. So once again, in the green half space, all the pairs of points x1, x2 satisfy the inequality x1 is at least half. The second, the blue one, half space, contains all the points that satisfy the second inequality. Finally, the red half space, shown here, contains all the points that satisfies the last inequality. In particular, the intersection of these three half spaces, this triangle, contains all the points that satisfy our three inequalities. Recall, however, that what we need to find is an integer solution. That is, we would like x1 and x2 to have integer values. And through this intersection is non-empty, it contains no integer points. So the integer points are here, the closest ones. But none of them is inside this region, right? So it turns out that this additional restriction, namely the restriction that the solution should be integer, gives us a very hard problem. In particular, if we just have a system of linear inequalities and we would like to check whether there is a point that satisfies, whether there is a solution to them, then we can use, for example, simplex method to solve it efficiently in practice. The running time of simplex method is not bounded by polynomials, so in some pathological cases it can have exponential running time, but there are other methods like ellipsoid method or interior point method that have polynomial upper bounds on the running time. So in any case, we can solve systems of linear inequalities efficiently in practice. But if we additionally require that we need the solution to be integer, then we get a very difficult problem for which we have no polynomial algorithm at the moment. Our last hard search problem that we mentioned here deals with graphs again. It is called an independent set problem. Here we are given a graph and a budget b, and our goal is to select at least b vertices such that there is no edge between any pair of selected vertices. For example, in this graph that we've seen before in this lecture, there is an independent set of size 7. So the selected vertices are shown here in red, and it is not difficult to check that there is no edge between a pair of red vertices. And in particular, this implies that an independent set is indeed a search problem. It is easy to check whether a given set of vertices is an independent set and that it has size at least b. It is interesting to note that the problem can be easily solved if the given graph is a tree. Namely, it can be solved by the following simple greedy strategy. Given a tree, if we want to find even just an independent set of maximum size, we can do the following. The first thing to do is let's just take all the leaves into a solution. Then let's remove all the leaves from the tree together with all its parents. And then let's just continue this process. Okay, to prove that this algorithm produces an optimal solution, we need to show that taking all the leaves into our solution is a safe move, that it is consistent with an optimal solution. This is usually done as follows. Assume that there is some optimal solution in which not all the leaves are taken. Okay? Assume that, just for concreteness, assume that this is some optimal solution. Okay? Not all the leaves are taken here because, well, we have this leaf, and this leaf, which is not in a solution. Then we show that it can be transformed into another solution which, without decreasing its size, such that it contains all the leaves. Indeed, let's just take all these marked leaves into a solution. This will probably require us to discard from a solution all its parents, but it will not decrease the size of this solution, right? So what we get is another solution whose size is, in this case, actually the same, but it contains all the leaves, which proves that there always exists an optimal solution which contains all the leaves. And this in turn means that it is safe to take all the leaves. We will see the details of this algorithm later in this class. But in general, once again, if we are given a tree, then we can find an independent set of maximum size in this tree very efficiently in linear time. But at the moment, we have no polynomial algorithm that finds, that even checks whether there is an independent set of size b in the given graph in polynomial time. Now, when we have a formal definition of a search problem, and when we've seen a few examples of such problems, we are ready to state the most important open problem in computer science, the problem about classes P and NP. So recall once again that the search problem is defined by an algorithm C that takes an instance I and the candidate solution S and checks in time polynomial Ni whether S is indeed a solution for I. In other words, we say that S is a solution for I if and only if the corresponding algorithm C of I and S returns true. Then the class NP is defined just as the class of all search problems. The name of this class stands for non-deterministic polynomial time. This essentially means that we can guess a solution and then check its correctness in polynomial time. That is, a solution for a search problem can be verified in polynomial time. The class P, on the other hand, contains all search problems that can be solved in polynomial times. That is, all search problems for which we can find a solution in polynomial time. So to summarize, once again, the class P contains all search problems whose solutions can be found efficiently. This class contains in particular the minimum spanning tree problem, the shortest path problem, the linear programming problem, the independent set on trees problem. The class NP contains all the problems whose solutions can be verified efficiently. That is, given an instance and the solution for this instance, a candidate solution, we can check in polynomial time in the size of this instance whether this is indeed a solution for this instance. This class contains such problem as the travel and settlement problem, the longest path problem, the integer linear programming, and independent set on general graphs. The main open problem in computer science asks whether these two classes are equal, namely whether the class P is equal to the class NP. This is also known as a P versus NP question. The problem is open. Namely, we do not know whether these two classes are equal. And this problem turns out to be very difficult. This is a so-called Millennium Prize problem. There is a $1 million prize from Clay Mathematics Institute for resolving this problem. Note that if P is equal to NP, then all search problems, all the problems for which we can efficiently verify a solution, they can be solved in polynomial time. In other words, for all the problems for which we can efficiently verify a solution, we can also efficiently find a solution. On the other hand, if P is not equal to NP, then there are search problems for which there are no efficient algorithms. So there are problems like, for example, travel and salesman problem, for which we can quickly check whether a given candidate solution is indeed a solution, but there is no polynomial time algorithm for finding such a solution efficiently. At this point, we do not know whether P is equal to NP or not. Whether there are search problems for which there are no polynomial time algorithms. In the next part, at the same time, we will show that all the problems that we mentioned in this lecture, namely the satisfiability problems, the longest path problems, the travel and salesman problems, the integer linear programming problem, are in some sense the most difficult search problems in the class NP. Hello and welcome to the next module of the Advanced Algorithms and Complexity class. This module is devoted to reductions. Reductions allow us to say that one search problem is at least as hard as another search problem. Intuitively, the fact that a search problem A reduces to a search problem B just means that we can use an efficient, namely polynomial time algorithm for the problem B to solve the problem A also in polynomial time. And we can use it just as a black box. Pictorially, the fact that a search problem A reduces to a search problem B means that we have a following pipeline. Assume that we have an instance I of a problem A. Now we are going to design an algorithm that solves the instance I using an algorithm, a polynomial time algorithm for B as a black box. For this reason, it is shown here in a black box. Okay, the first thing to do is that we need to transform an instance I into an instance I of a problem A into an instance of the problem B. We do this by calling an algorithm F. So we feed the instance I of the problem A into the algorithm F, and it gives us the instance F of I of the problem B. We then use the algorithm for B as a black box to solve it efficiently, and it gives us one of two outputs. Either there is no solution for this instance F of I. In this case, we report that there is no solution also for I, for the instance I of the problem A. Otherwise, it gives us a solution S for instance F of I. In this case, we need to transform it back to a solution of I. We do this by using the second algorithm H. And it transforms a solution S of F of I into a solution H of S of the initial instance I. We can now state it formally. Given two search problems A and B, we say that A reduces to B and write A to B if there is a pair of two polynomial time algorithms F and G. The algorithm F transforms any instance of A into an instance F of A of the problem B, such that the following holds. If there is no solution for the instance F of I of the problem B, then there is no solution for the instance I of the problem A. Otherwise, if there is a solution S for the instance F of I, then by applying the algorithm H to this solution S, we get a solution H of S of the initial instance I. Now, when we have a notion of reduction, we can imagine a huge graph containing all search problems. So this graph corresponds to the class NP of all search problems. In this graph, there is a vertex for each search problem, and we put an edge between the search problem A and the search problem B, a directed edge, if the search problem A reduces to search problem B. Okay? Then, by definition, we say that a search problem is NP-complete if all other search problem reduce to it. Pictorially, it looks as follows. So the red vertex here corresponds to an NP-complete search problem. So in some sense, this problem attracts all other search problems. All other search problems reduce to it. Put it otherwise, an algorithm for an NP-complete problem can be used as a polynomial time algorithm for an NP-complete problem can be used as a black box to solve just all other search problems also in polynomial time. It is not at all clear that such NP-complete problems exist in our graph of all NP of all search problems, but we will show that they do exist. And we will show actually that all the search problems that we've seen in the previous modules, namely satisfiability problem, travel and Allison problem, the maximum independent set problem, longest path problem, integer linear programming problem, they are all NP complete. Namely, if you design a polynomial time algorithm for any of them, you will solve just all search problems in polynomial time. In this part, we will discuss a general way of proving that a particular search problem is NP-complete. Well, as you know already, we are going to prove NP-completeness via reductions. And there are two equivalent ways of using reductions. Namely, we say when we know that A reduces to B, we know that if the problem B is easy, namely if there is an efficient, that is polynomial time algorithm for B, then there is also an efficient algorithm for A. This is just by definition, right? If B, we know that A reduces to B, that is, an efficient algorithm for B can be used as a black box for solving A. So if B is easy, if there is such an algorithm, then we can use it to solve A in polynomial time. The second way of using reductions is just a contrapositive of the first item here. If A reduces to B and we know that A is hard, meaning that there is no polynomial time algorithm for this problem, then also there is no polynomial time algorithm for B. Then B is also hard. Indeed, if B was easy, then A was easy, right, as shown in the first item. So B cannot be easy in this case. There cannot be a polynomial time algorithm solving B. When proving NP-completeness of certain search problems, we will use the following basic fact about reductions, namely that reductions do compose. More formally, if a search problem A reduces to search problem B, and in turn search problem B reduces to search problem C, then A reduces to C. Let's prove this formally. The fact that A reduces to B means that we have a pair of polynomial time algorithms, F sub AB and H sub AB. Namely, F transforms any instance of a problem A into an instance of a problem B, and H, AB transforms any solution to problem B back to a solution of problem A. And similarly for the reduction from B to C. Okay, then to construct such a pair of algorithms from to reduce problem A to problem C, we just compose the corresponding functions, the corresponding algorithms. So assume that we have an instance I sub A of the problem A, and we need to get an instance of a problem C. For this, we first apply the algorithm F sub AB to the instance IA. This gives us an instance of the problem B. We then apply the algorithm FBC to the resulting instance of the problem B. This gives us an instance of the problem C. The important thing to note here is that the resulting composed algorithm has polynomial time. To see this, note that assume, for example, that the running time of the algorithm f of AB is for example P of n, and its running time is n cubed, for example, and the running time of the algorithm f sub AB is Q of n, and it is n to the 5. Then the running time of the composed algorithm is P of Q of n. This is P of n to the 5, and this is in turn n to the 5 cubed, which gives us n to the 15. Namely, when you compose two polynomial functions, you get also a polynomial function, which justifies that the running time of this algorithm is also polynomial. To get an algorithm which transforms a solution to C back to a solution of A, you just apply the combination of the corresponding to H algorithms. Namely, when you get a solution S sub C for the problem C, you first apply the algorithm HBC. This gives you a solution back to the problem B. Then you apply the algorithm H of AB to transform it back to a solution of the problem A. Pictorially, this composition of reductions means the following. Whenever we have these two pair of edges in our graph of all problems of the class NP, we also have the following edge, right? So if if A reduces to B and B reduces to C, then A reduces to C. In other words, if there is an edge from A to B and from B to C, then there is an edge from A to C. Yeah, so simple. This allows us to prove NP completeness as follows. If we know that A reduces to B and we know that A is NP complete, then so is the problem B. Then B is also NP complete. Let me prove this pictorially. So this is again our graph. We have two problems A and B, and we know that A reduces to B. We also know that A is NP complete, meaning that A attracts all other problems. In other words, there is an edge from any other problem to A. Now, since there is an edge from any other problem to A, and at the same time there is an edge from A to B, through the composition of reductions, we know that there is an edge from any other problem to B, right? So this is a picture that we have. B also attracts all other problems, so by definition it is also NP complete. Our plan for the rest of this module is the following. We will first show that the independent set problem can be reduced to the vertex cover problem. We will then show that the 3 satisfiability problem reduces to independent set problem. We will then show that satisfiability problem, the general version of satisfiability problem, reduces to its special case, namely to the 3 satisfiability problem. And finally, we will show that all other search problems reduce to that. In particular, the 3 problems shown here above the satisfiability problem. Our first reduction is from the independent set problem to the vertex cover problem. Recall that in the independent set problem we are given a simple undirected graph, unweighted, together with a budget B. And our goal is to find at least B vertices in this graph such that there are no edges between any pair of them. The vertex cover is formulated as follows, the vertex cover problem. We are again given a graph, a simple unweighted undirected graph together with a budget B. And our goal is to find at most B vertices that cover all edges of our graph. That is, any edge of this graph has at least one endpoint in the selected set of at most B vertices. Let's consider a toy example. In this graph we have 8 vertices, and one example of an independent set of this graph is E and C. It is interesting to note that in this case we cannot add any other vertex to this independent set. For example, if we add the vertex B, then we will violate the property that there is no edge between two vertices because there is an edge between B and C. We cannot add F because it is connected to E, we cannot add A because it is connected to E, cannot add H, cannot add D because it is connected to C, and so on. So we cannot extend the independent set EC in this case. Still, there is a larger independent set in this case. It includes vertices A, C, F, and H. It has size 4. It is not difficult to check that it is indeed an independent set, that no 2 red vertices are joined by an edge in this graph. Concerning vertex cover, one vertex cover in this graph has size 6. It includes all vertices except for E and C. It is indeed not difficult to check that for any edge in this graph, at least one of its endpoints is green. For example, for this edge, this endpoint, the vertex G, is selected. For this edge, both of its endpoints are included into the vertex cover. Recall that we are interested in vertex covers of small size, and in this case there is a smaller vertex cover, namely it is the set B, E, G, and D, and again it is not difficult to check that these green vertices touch all the edges of our graph. By reviewing this example, you probably already noticed the following simple property of independent sets of a graph and its vertex covers. I is an independent set of a graph G if and only if its complementary set of vertices is a vertex cover in this graph. Let's prove this formally. So I assume that I is an independent set. This essentially means that there are no edges with both endpoints in the set I. This in turn means that each edge has at least one endpoint in the complementary set, in the V minus I. And this in turn means that V minus I is a vertex cover of a graph, right? For the reverse direction, I assume that V minus I is a vertex cover of a graph. This means that V minus I touches every edge. This again means that for each edge, at least one of its endpoints lies in V minus I. And this means that for no edge, two of its endpoints lie in I, which in turn gives us that I is an independent set of the graph G. This relation allows us to design a very simple reduction from the independent set problem to the vertex cover problem. Namely, to check whether the given graph G contains an independent set of size at least B, we just check whether the same graph G contains a vertex cover of size at most V minus B. We already know that there is an independent set of size at least B if and only if there is a vertex cover of size at most B. So formally, our reduction is specified by two very simple and clearly polynomial time algorithms. The algorithm F needs to transform an instance of the problem independent set to the instance of the vertex cover problem. So we take an input graph G and the budget B, and we leave the graph G untouched, and we replace the budget by V minus B. Then we call an algorithm as a black box, an algorithm for the vertex cover problem on the following instance. If it finds out that there is no vertex cover of size at most V minus B in this graph, then we just report immediately that there is no independent set of size at least B in our initial graph. Otherwise, it returns us some solution S, which is a vertex cover in the graph G of size at most V minus B. By taking the complementary of this set S, we get a vertex cover of size at most B. We now come to a more interesting reduction that connects Boolean logic to graphs. Namely, we're going to reduce the three satisfiability problem to the independent set problem. Recall that in the three satisfiability problem, our input is a formula in 3CNF. That is a collection of clauses. Each clause is a disjunction of at most three literals. And our goal is to check whether it is possible to assign Boolean values to all the variables of the formula F, so that to satisfy all the given clauses. Since we need to reduce this to the independent set problem, our goal is to design a polynomial time algorithm that takes a formula F in 3CNF and outputs a graph G and an integer B such that the input formula F is satisfiable if and only if there is an independent set of size at least B in the graph G. Before designing this reduction, let's recall what does it mean to satisfy a given formula in conjunctive normal form. This essentially means that we need to assign a Boolean value to each variable of the given formula such that each clause contains at least one satisfied literal. To give an example, consider the following formula. It is satisfied by an assignment which assigns the value true or the value 1 to all the variables. Indeed, in the first clause we have just all the literals in the first clause are satisfied. In the second clause, the first literal is satisfied by this truth assignment, and in the last clause, the first literal is also satisfied by this truth assignment. There is another assignment that satisfies the same formula, namely, if we assign the value 1 to x and the value 0 to y and z, we satisfy the first literal in the first clause, we satisfy both literals in the second clause, and we satisfy the last literal in the last clause. This point of view gives us an alternative definition of the satisfiability problem. Namely, to satisfy a given CNF formula, we need to select from each clause of a given formula one literal such that the resulting set of selected literals is consistent, meaning that it doesn't contain a literal L together with its negation. Let me illustrate this on a toy example as usual. Assume that we have a formula consisting of 3 clauses over variables x, y, and z. Well, by a consistent set of literals in this case, we mean, for example, x, and not z. So this is one. So from first clause we select the literal x, from the second one we also select the literal x, and from the third clause we select the literal not z. Note that for this consistent set of literals, we can find the corresponding satisfying assignment. Namely, we assign the value 1 to x and the value 0 to z. Namely, we satisfy all the literals in this set, right? So for this we assign the value 1 to x and the value 0 to z. It is easy to see that this is indeed a satisfying assignment. So in the first clause x is satisfied, in the second clause x is satisfied, in the last clause not z is satisfied. So the value of y doesn't actually matter in this case, right? Alternatively, we can get the following consistent set of literals just by selecting x and from the first clause, x from the second clause, and y from the third clause, right? And another possibility is to select x from the first one, not y from the second one, and not z from the third one. This will give us the following consistent set of literals. Once again, we want this set of literals to be consistent so that we are able to assign a specific value for each literal. So for this, to explain this better, let's consider some inconsistent sets of literals. Assume that from the first clause we select not y, from the second clause we select the negation of y, from the third clause we select not z. So this gives us the following set of literals, which is inconsistent because it contains both y and the negation of y. In this case, we cannot assign the value to y to satisfy all the literals in this clause. Namely, if we assign the value 0 to y, then we falsify this literal y. If we assign the value 1 to y, we falsify this literal in this clause. And this is exactly the reason why we would like our set of selected literals to be consistent. This alternative statement of the satisfiability problem is the main idea, is the main ingredient of our reduction from 3-SAT to the independent set problem. We illustrate the reduction first on a toy example as usual. Given a formula, in this case with 5 clauses over 3 variables x, y, and z, the first step is to introduce for each clause 2 or 3 new vertices labeled with the literals of this clause. In this case, it gives us the following picture. So x, y, and z here correspond to this clause. X and not y here, the 2 new vertices correspond to this clause, and so on. The last 3 vertices correspond to this clause. The next thing to do is to join all the vertices, all the pairs of vertices inside each block. So for 2, 3 clauses, we have 2 triangles here, and for 3, 2 clauses, we have just 3 edges. Okay? Once again, each 3 clause corresponds to a triangle. Each 2 clause, that is clause of length 2, corresponds to a single edge. So all these edges, actually, what we're going to do is to find a large independent set in this graph. And all the newly added edges force us to select into our independent set at most one vertex from each block. For example, we cannot select 2 vertices from this block into an independent set because any 2 of them are joined by an edge. The same is for this block, for example. We can only select just 1 vertex from this block into an independent set because they are connected by an edge. Okay? So selecting a vertex from each of these blocks into an independent set corresponds to selecting a literal from the corresponding clause that is going to be satisfied in this clause. Recall that in each clause we need to select a literal which is going to satisfy this clause. So we mimic this by selecting the corresponding vertex from a block. However, recall that we need to select a consistent set of literals. That is, we do not want to select, for example, both x from some clause and not x from some other clause. To force our set of selected vertices to be labeled with consistent set of literals, we just add all possible edges between all pairs of complementary literals. Namely, whenever we have a vertex labeled with x like this one and not x like this one, we join them by an edge. So we have x here, we have not x here, we join them by an edge. Another pair of vertices is x here and not x here, we also join them by an edge. Then there is another vertex labeled by x, we also join them by an edge. X and this not x, and x and this not x. And we do this for all other pairs of complementary literals. Now the claim is that this graph contains an independent set of size exactly 5, or at least 5, if and only if the initial formula is satisfiable. And it is already clear. So if the formula is satisfiable, this means that we can select a set of for each clause we can select one literal such that the resulting set of literals is consistent. But this also means that from each of these 5 blocks, so this is the first block corresponding to the first clause, this is the second, this is the third one, this is the fourth one, this is the fifth one, we can select exactly the same vertex that corresponds to the selected literal in this formula. Right, so if the formula is satisfiable, then in each block we can select one vertex, and we know that they are not going to be joined by edges because vertices from different blocks are only joined if they are complementary. And we know that our set of literals does not contain complementary literals. So if the formula is satisfiable, then this graph contains an independent set of size 5. Okay? And vice versa, if this graph contains an independent set of size 5, then the formula is satisfiable. Why is that? Well, just because any independent set of size 5 has exactly one vertex in each of these blocks. And we know that the labels of these vertices give us a set of literals which is consistent, which doesn't contain a literal together with its complementary literal. So it gives us a set of literals such that it intersects every clause of our initial formula, which means that it corresponds to a satisfying assignment of the initial formula. To summarize, let's state this reduction formally. The reduction works as follows. Given a formula f in 3 sin f, that is a collection of clauses each of length at most 3, we do the following. We scan the set of clauses from left to right, and for each clause we introduce 3 or 2 or just 1, depending on the number of literals in this clause, 3 vertices, 3 or 2 or 1 vertices, and we label them with literals of this clause, and we join every two of them by an edge. This forces, so we are now constructing a graph G, and this forces every independent set in this graph to contain at most one vertex from each block corresponding to a single clause. Okay? Then we also need to force each independent set to be labeled with a set of literals which is consistent. For this we do the following. We join every pair of vertices in our graph which are labeled with complementary literals. That is, if a vertex is labeled with a literal L, we add new edges that connect it to all vertices which are labeled with the negation of L. Okay? Then what we've just proved on a toy example is the following. The resulting graph G contains an independent set of size B, where B is the number of clauses of the initial formula, if and only if the initial formula is satisfiable. Okay? It remains to note that the running time of the resulting transformation is polynomial. Why is that? Well, just because to construct this graph, we first just scan the formula, which is just a linear, which takes linear time on the size of the formula. It is just big O of the number of clauses. To make it more formal, let's denote M. Let's denote by M the number of clauses in our formula. Then this step takes time big O of M. We just scan the list of clauses. And during this scan, we introduce at most 3 M vertices, and then we need to check every pair of these vertices and to join them by an edge if they are labeled by complementary pair of literals. So the second step clearly takes time at most M squared. In any case, this is polynomial, so the whole transformation takes polynomial time. Formally, we need also to describe an algorithm that transforms any solution to the maximum independent set problem for the resulting graph back to a solution to the 3 satisfiability problem. And we also need to ensure that if there is no solution for the resulting instance of the maximum independent set problem, then there is no solution for the initial problem. But this is not difficult, and we did this already. Namely, if there is a solution for the resulting instance of the maximum independent set problem, namely there is an independent set of size equal to the number of clauses. That means that from each block we can select a vertex such that all the labels of these vertices is consistent. Gives a consistent set of literals. But this also means that this gives a satisfying assignment of the initial formula, right? If on the other hand there is no solution for the resulting instance of the independent set problem, then we know that the initial formula is unsatisfiable. Indeed, if it were satisfiable, if there were a satisfying assignment for the initial formula, then this would give us an independent set in the graph of size equal to the number of clauses, right? Which would contradict to the fact that there is no such independent set in the resulting graph. Our next reduction is from satisfiability problem to 3 satisfiability problem. That is, from a general version of a problem to its special case. To construct such a reduction, we need to design a polynomial time algorithm that takes as input a formula in conjunctive normal form, that is a collection of clauses, and produces an equisatisfiable formula in 3CNF. That is a formula in which each clause has at most 3 literals. By saying equisatisfiable, we mean that the resulting formula is satisfiable if and only if the initial formula is satisfiable. Once again, if the initial formula is f and the resulting formula is f prime, then by saying equisatisfiable, we mean that f is satisfiable if and only if f prime is satisfiable. To construct such a reduction, we need to somehow get rid of all long clauses in our formula. By saying long, we mean clauses that contain more than 3 literals, right? To do this, consider such a long clause and denote by L1 and L2 some two literals of this clause, and denote by A the rest of this clause. So once again, L1 and L2 are two literals of the clause C, which we consider at the moment, and A is a set of all other literals. Now we're going to do the following. Introduce a new fresh variable y and replace the current clause C with the following two clauses. So the first clause contains literals L1, L2, and y. So it is junction of L1, L2, and y. The second clause contains the negation of y and all the other literals, which we denote by a set A. Okay? Then we first of all note an important property. The clause, the first of the two new clauses has length 3. So we are okay with it. We are happy with it. We do not need to get rid of it. At the same time, this clause is shorter than the following one, exactly by one literal, right? So we are going to repeat this procedure while there is at least one long clause. And for sure we will stop at some point, because at each step we reduce some long clause with a shorter one. We now need to prove that the constructed transformation is correct, that the constructed reduction is correct, and that it takes polynomial time. Concerning the running time, it is clear because at each iteration we replace a clause with a shorter one. This means that the total number of iterations is bounded from above by the total number of literals in all the clauses. This is clearly polynomial in the length of an input formula. To prove that the constructed reduction is correct, we are going to show that the initial formula f with a long clause is satisfiable if and only if the resulting formula, where we replaced a long clause with a 3 clause and the shorter clause, is also satisfiable. Okay? To do this, consider these two formulas. So this is f, it contains a long clause, and this is f prime that results from f by replacing this long clause with the following two clauses, L1, L2, and y, where y is a fresh variable and a clause not y or a. Okay, assume now that the formula f is satisfiable and take a satisfying assignment. We are now going to extend it so that it also satisfies the formula f prime. Recall that the only difference between the sets of variables of formulas f and f prime is the variable y. So our goal is to set y so that the resulting assignment satisfies all the clauses of the formula f prime. First of all the remaining clauses of f prime are satisfied by exactly the same assignment that satisfies the formula f. So our goal is to set y so that both the first two clauses are satisfied. I mean, both the first two clauses of the formula f prime. Okay, so to set the variable y, we just check whether the current satisfying assignment of the formula f satisfies one of the literals L1 or L2 or not. So if it satisfies these two literals, we set y to 0. In this case, the first clause of the formula f prime is satisfied by one of L1 or L2. The second clause, on the other hand, is satisfied by the variable y, right? Because we've just assigned the value 0 to y. On the other hand, if L1 or L2 and L2 are falsified by the current satisfying assignment, then at least one of the literals from the set I should be satisfied. In this case, we just set the value of y to 1, right? In this case, the first clause is satisfied by the value of y, while the second clause is satisfied by one of the literals from the set A. Okay? For the reverse direction, note that if we have a satisfying assignment that satisfies the formula f prime, then we can just discard the value of the variable y from this assignment, and then what we get is a satisfying assignment for the formula f. Why is that? Well, for a simple reason. What we need to show is that this clause is satisfied in a formula f, but it must be satisfied because at least one of L1, L2, and all the literals of A should be satisfied. I assume, for the sake of contradiction, then in the current satisfying assignment for f prime, L1 is set to 0, L2 is set to 0, and all the variables, all the literals from the set A are also set to 0. Then there is just no possibility to satisfy these two clauses, because no matter how we assign the value to y, either the first clause or the second clause is going to be unsatisfied. We now proceed to the most interesting reduction in this module. Namely, we are going to show that every search problem, every problem from the class NP reduces to SAT. So for this, actually, we are going to introduce an intermediate problem called circuit SAT, which is also an important computational problem. And we are going to show that any search problem reduces to circuit SAT, and in turn, the circuit SAT problem reduces to the SAT problem. So what is a Boolean circuit? In some sense, it is just a generalization of the Boolean formula. So it is a computational model for computing a Boolean function. An example of a circuit is shown here on the slide. So it is in fact a graph, and with some input nodes. So here we have input nodes marked with variables, and this input node is marked with a Boolean constant 1, and all other nodes are marked by Boolean operations, namely with conjunctions here, disjunctions here, and negations. So when x, y, and z are assigned Boolean values, for example 0, 1, 0, we can compute what is an output of this circuit. To do this, we just apply these Boolean operations to the inputs of each node. The nodes are called gates. For example, the value of this gate is equal to 0, the value, because this is a logical AND of 0 and 1, the value of this gate is equal to 1, because this is a logical OR of 1 and 0. Then the value of this gate is 1, because this is a negation of 0. The value of this gate is equal to 1, because this is a logical OR of 1 and 1. The value of this gate is also 1, because this is an OR of 1 and 1. And finally, the value of this gate is also equal to 1. So when x is equal to 0, y is equal to 1, and z is equal to 0, the output of this circuit is equal to 1. Okay? More formally, a circuit is a directed acyclic graph such that all of its vertices have in degree either 0, 1, or 2. The nodes of in degree 0 are called inputs, and they are marked by Boolean variables or by Boolean constants. Nodes of in degree 1 are labeled with negations, and nodes of in degree 2 are labeled with disjunctions or conjunctions, or with logical ORs and ANDs. Also, there is one node which is labeled as an output. This is a gate of out degree 0. Okay, so a circuit is a computational model. Such a circuit computes in a natural way a function which depends on input Boolean variables. Okay, so we can compute this function exactly because the underlying graph contains no cycles. We can just topologically sort all the gates and compute the value for each gate in topological ordering. I mean, when the input variables are assigned values. Now, the corresponding search problem is very natural. We are given a circuit, and we would like to check whether it is possible to assign values to its variables so that the circuit outputs 1. This is a generalization of the satisfiability problem, where instead of a circuit, we are given just a formula. Note, however, that a CNF formula can also be represented as a circuit in a very natural way. Just to give an example, consider the following formula in conjunctive normal form. Here we have two clauses, x or y or not z and y or not x. We can represent it as a circuit as follows. So first we need to compute the value of the first clause. We do this as follows. So we compute x or y. This is computed at this gate, and then we compute x or y or z. Okay, so this corresponds to the first clause. Then we need to compute the value of the second clause. For this, we first compute the negation of x. It is computed at this gate, and then we compute the logical OR of the negation of x and y. And finally, so this gate computes the value of the second clause. Finally, we take the logical AND of these two clauses. So clearly, this circuit computes exactly the same as this Boolean formula in conjunctive normal form. What we need to do now is to reduce circuit SAT to its special case, namely circuit SAT to SAT. For this, we need to do the following. We need to design a polynomial time algorithm which takes a circuit and transforms it in polynomial time into a formula in CNF which is satisfiable if and only if the initial circuit is satisfiable. To do this, we're going to do the following. For each gate of the initial circuit, we introduce a new variable. So this variable is going to be assigned to this gate. So in total, we are going to have variables that correspond to inputs of this circuit, and also one Boolean variable for each gate of the initial circuit. Then we are going to write down a bunch of clauses. For each gate of our initial circuit, we are going to write a few clauses that will somehow encode the relationship between the inputs of this gate with the value computed at this gate. We now explain how to write down these clauses. We start with the case when the current gate G, for which we are going to write down these clauses, is labeled with the negation sign. So consider such a gate. So it is labeled with the negation sign, and the corresponding variable is G. Assume that its predecessor is marked with label H. Then we write down the following two clauses of length 2. So what does these two clauses mean? Well, what essentially they say is the following. If H is equal to 1, then G must be equal to 0. Right, so this is forced by the second clause. Indeed, if H is equal to 1, then in the second clause, this literal is already falsified, which means that the only way to satisfy the second clause is to set G to be equal to 0, right? And vice versa, if H is equal to 0, then G must be equal to 1. This is forced by the first clause. So if H is equal to 0, then in the first clause, the value of H is already falsified. So the only way to satisfy the first clause is to set G to be equal to 1. Which means that in any satisfying assignment of a formula that contains the following two clauses, H and G always have the opposite values. Which in turn means that G always equal to H negated. And this is exactly what we need to encode in our CNF formula. Now consider an AND gate. Assume that G is an AND gate and its two direct predecessors are H1 and H2. We then write down the following three clauses. Let's again see what do they encode. The first clause says that if H1 is equal to 0, then the only way to satisfy the first clause is to set G to 0. So if H1 is equal to 0, then G is equal to 0. This is exactly what we need. If H1 is equal to 0 here, then the resulting gate G also computes 0, right? Because this is a conjunction or logical AND of H1 and H2. Okay, the second clause tells us that if h2 is equal to 0, then also g is equal to 0. Right? Finally, the last clause says that if h1 is equal to 1 and h2 is equal to 1, in this case, these two literals in the last clause are already falsified. So the only way to satisfy the last clause is to set g to be equal to 1. Once again, this just means that if we have a formula in which we have these three clauses, then in any satisfying assignment to this formula, the value of g is equal to the value of h1 and h2. And this is exactly what we need to encode in our CNF formula. OR gates are handled similarly. Namely, if g is an OR gate, we write down the following three clauses. The first one says that if h1 is equal to 1, then this literal is already falsified, then g must be equal to 1. If h2 is equal to 1, then g is equal to 1. This corresponds to the second clause. Finally, if h1 is equal to 0 and h2 is equal to 0, then g is also equal to 0. Again, in any satisfying assignment for a formula that contains the following three clauses, g is equal to h1 or h2. Finally, for an output gate, for the output gate, there is a single such gate in a circuit. We write down a clause containing just one variable or just one literal corresponding to this gate. This corresponds to the fact that we would like this gate to be equal to 1. We would like our circuit to output the value 1. The reduction is now complete. We constructed a CNF formula out of a given circuit with the following property. In any satisfying assignment of the resulting CNF formula, the value of the variable g corresponds, it just equals to the value of the gate g on the corresponding truth assignment of the inputs to this circuit. This in turn means that the resulting formula is satisfiable if and only if the initial circuit is satisfiable. In particular, given a satisfying assignment for the CNF formula, just by reading the values of the inputs of the variables that corresponds to the inputs of the circuit, we get a satisfying assignment for the initial circuit. It is also clear that the running time of this reduction is polynomial, because we just consider all the gates of the initial circuit, and for each such gate we write down at most three clauses. Now, our goal is to reduce every search problem, every problem from the class NP to the circuit SAT problem. For this, consider a particular search problem A. Note that we don't even know whether the instances of this problem are graphs, or Boolean formulas, or Boolean circuits, or just numbers, or systems of linear inequalities. The only thing that we know is that A is a search problem. So this is the only thing that we can use to construct this reduction. By definition, this means that there is an algorithm C, which for any instance I of the problem A and for any candidate solution S in time polynomial in the length of I checks whether S is indeed a solution for I. In particular, we require that the length of a candidate solution S must be upper bounded by a polynomial of the length of I. Now, a simple but crucial observation is that a computer is also a circuit, a Boolean circuit, which on low level operates with bits, with Boolean values. Moreover, each particular computer is actually a circuit of fixed constant size, right? Now let's run our algorithm C on inputs I and S on some computer. We know that this computer is going to perform the number of steps, which is polynomial in the size of I. Now let's replace each of these steps by the corresponding circuit. In this case, we have a sequence of circuits such that each of these circuits in this sequence uses the values computed by the previous circuits in this sequence and computes some values. Assume that this is a circuit corresponding to our computer, so it uses some bits corresponding to instance I and some bits corresponding to the candidate solution S. Then it computes also some values, and we plug it into the second circuit, and so on. We have polynomially many such circuits polynomially in the size of I. And in the end, our algorithm outputs 1 if and only if S is indeed a solution for I. So our circuit outputs 1 if S is a solution for I. So once again, what we get is a circuit which has polynomially many in the length of I, polynomially many gates, which outputs 1 if and only if S is a solution for I. Now, when we constructed such a circuit, we can use it as an input to our black box algorithm that solves the circuit SAT problem in polynomial time. Namely, we do the following. Consider the circuit that we just constructed. Recall that this is a circuit whose input variables encode instances I of our search problem A, and also solutions, candidate solutions to our search problem A. And this circuit outputs 1 if and only if the given candidate solution S is indeed a solution for an instance I. What we're going to do is the following. For a particular instance I, let's plug the constants for these input bits that encode this solution. What is left is a circuit whose input variables encode different candidate solutions for this input instance I. And this circuit outputs 1 if and only if there is a solution for this instance I. Now we can just use our black box algorithm that solves the circuit SAT problem to find such a solution, right? Which means that we finally reduced our search problem A to the circuit SAT problem. Once again, if we have an algorithm which finds a satisfying assignment for any given circuit, that we can use it to solve any search problem A, also in polynomial time. So the reduction is complete. To summarize, what we did is the following. We first reduced the independent set problem to the vertex cover problem. We then reduced the 3 SAT problem to the independent set problem. Then we reduced the satisfiability problem to the 3 satisfiability problem, and then we showed that every problem from the class NP reduces to SAT. We did this actually via the circuit SAT problem. This ensures that all these problems here on the picture are in fact NP complete. That any search problem is reduced to these 4 problems shown here on the slide. We conclude with showing how to use SAT solvers in practice. Namely, we give a toy example, a toy application. We are going to use SAT solvers to implement a very simple Sudoku solver. Recall that there is a huge gap between theory and practice of SAT solving. Namely, currently we do not know how to prove that SAT can be solved in less than 2 to the n steps. Namely, we have no example of an algorithm with the running time polynomial in the size of the formula times 1.99, for example, to the n, where n is the number of variables of the input formula. It is on one hand. On the other hand, we have state-of-the-art SAT solvers that can handle instances that arise in practice that contain thousands and even millions of variables in less than 1 second. This suggests the following way of solving hard combinatorial problems in practice. First, you might want to reduce your problem to the satisfiability problem. The structure of the satisfiability problem allows to do this very naturally for many problems arising in practice. We will see this on an example of solving Sudoku puzzle. Then just use one of the efficient programs, efficient SAT solvers that are already implemented. There are many of them, and as I said, they are very efficient. Let me now recall you what a Sudoku puzzle is. So in this case, we're given a 9 by 9 grid, which is partially filled by digits from 1 to 9. And our goal is to fill it in, is to fill all the vacant places with digits so that each row, each column and each of 9 3 by 3 blocks contain all the digits from 1 to 9. This is an example of such a puzzle, and this is a solution that we are looking for in this case. So note that, for example, in this row, we have all digits from 1 to 9, and also in this column, and also in all of these 9 3 by 3 blocks. So given a Sudoku puzzle, we are going to construct a satisfiable CNF formula such that from its satisfying assignment we can construct a solution for the initial puzzle. For this, we're going to use the following Boolean variables. There will be 9 by 9 by 9 of them. Namely, for each possible values of I, j, and k, where I, j, and k are at least 1 and at most 9, the variable x, I, j, k is equal to 1 or is equal to true if the cell ij contains the digit k. Okay, so these are Boolean variables. There are 9 by 9 by 9 of them, which is roughly 700. In our reduction, we will need a few times the several technical thing. Assume that we have a few literals and we need to state a formula which expresses the fact that exactly one of these literals is true. We show here how to do this for 3 literals, but it generalizes easily for arbitrary number of literals. So assume that we have 3 literals and we want to express the fact in a CNF formula that exactly one of them is true. So first we write down a clause that says that at least one of them is true. This says L1 or L2 or L3. Then we need to say also to constrain the value of these variables to satisfy the following property. At most one of them is true. Namely, we need to forbid any two of them to have value 1 simultaneously. We do this just by adding a bunch of clauses of length 2. Namely, for any 2 different literals from our set, we add a 2 clause containing negations of these 2 literals. For example, this one, the first clause says that it is not possible to assign the value 1 to L1 and L2 simultaneously. The second one says that we should not assign the value 1 to the first and the third literal. And finally, the last one says that we should not assign the value 1 to the second and the third literal. So finally, when we write down such a formula, then in any satisfying assignment to this formula, exactly one of L1, L2, and L3 is true. And also this generalizes easily to any number of literals. So we first write down a long clause containing all the literals, and then so that it will contain k literals. And then we write down roughly k squared literals, namely k choose 2 clauses that contain all pairs of literals, of negated literals. We now write down the corresponding constraints. First of all, for every values of I and j from 1 to 9, we state that in the cell ij there is exactly 1 digit. So it looks as follows. So this is the cell ij in our grid. And we say that exactly one of the variables xij1, xij2, and so on xij9 should be equal, should be assigned the value true. So if xij, for example, if xij4 is equal to true, this means that we are going to put the digit 4 into this cell. Then we need to state that for each values of k and I, the row I contains exactly 1 occurrence of k. This is done as follows. We state that for each I and k, exactly one of the following variables is true. So it is either xi xi1k or xi2k. So this corresponds to the fact that either the first column in the ith row contains k, or the second column, or the last column. Namely, if this is the ith row, either this cell contains k, or this cell contains k, and so on. The last cell contains k. Then we do the same for column j. And namely, for each values of k and j, we state the fact that the column j contains exactly one occurrence of k. We then need also to state that each of 9 3x3 blocks contains one occurrence of the digit k. Again, we use the corresponding 9 variables to say that exactly one of them is equal to true. Finally, the last type of constraint is that when some cell is already filled, if we have an instance where the cell ij already contains the digit k, then we need just one clause stating that the corresponding variable is already must be equal to true. We know that it is already true, so we just add a single unit clause. So the resulting formula contains about 2 to the 700 variables. So the search space of all possible candidate solutions in this case contains roughly 10 to the 200. So this is a huge search space. It is certainly not possible for modern computers to go through all possible candidates for a solution in this case. At the same time, modern SAT solvers solve the resulting formula in blink of an eye. We will see now. We are going to use the Minisat SAT solver for solving our Sudoku puzzle. Before writing down the reduction, let me show you the input format for this SAT solver. So the formula is given in the following simple format. The first line here shows that our formula has 2 variables and 3 clauses. Then each of the following 3 lines define a clause. The first clause contains 2 variables, x1 and x2. The second clause contains the variable x1 and the negation of the variable x2. So minus x2 means the negation of the second variable. Finally, the last clause contains 2 variables, the negation of x1 and the negation of x2. Okay? So now let's call Minisat on this formula. So it reports immediately that it is satisfiable. Now let's make it unsatisfiable. So for this we add the fourth clause. -1 to 0. Okay. Let's call Minisat again. Yeah, in this case, the formula is unsatisfiable, of course. Now, finally, let me show you the code of an actual reduction that produces a CNF formula, then calls a Minisat solver, and then reads the solution for a given Sudoku puzzle from a satisfying assignment to this formula. So this is a simple code on Python. This gives the initial Sudoku puzzle. Then we create a list of all clauses. Then we just use a variable digits which contains all the digits from 1 to 9. The following method just returns a unique integer number for every variable. We need this in order to give a formula to a Minisat solver. Then we have a method which, given a list of literals, writes down clauses that express the fact that exactly one of these literals is equal to true. Namely, we first add a clause that contains all the literals in the list literals. Then for all pairs of literals, we add a clause containing two negated literals from this list. As we've discussed already, this expresses the fact that exactly one of them is equal to true. We then start writing down clauses expressing that each cell contains exactly one digit. Namely, for all pairs of digits, we write down a clause stating that at least for all pairs of I and j, we write down the clause saying that the cell ij contains exactly one digit. So the corresponding variable xijk is equal to 1 for exactly one value of k. Then we say that k appears exactly once in row I. For this we consider all possible values of I and k and state that exactly one of the variables I, j, k is equal to true for all possible values of j. Then we say the same for columns, and then we say the same for blocks. Namely, we consider all possible starting position of blocks 1, 4, and 7, and then for each such block we state that and for each k we state that each such block contains exactly one occurrence of k. Then we read the input puzzle. Namely, we read all the cells, and if the corresponding cell is specified, then we just add a unit clause containing exactly one corresponding variable. Finally, we write down all the clauses. Namely, we open a file tmpcnf. In the first line, we write pcnf followed by the number of variables. In our case, it is roughly 1000, and then the number of clauses. Then for each clause which is currently in our list of clauses, we first append 0 to satisfy the format which is accepted by the Minisat, and then we just write down this clause. Then we call the Minisat sat solver, give it the formula tmpcnf, and also indicate the file tmpsat where it will write down the satisfying assignment. Okay, then we open the satisfying assignment file and read the first line. If it is unsat, we just report that the formula is unsatisfiable. If the first line is sat, we know that the formula is satisfiable, and we know that then the second line will be followed by a satisfying assignment. At this line, we read the corresponding satisfying assignment, and then we parse it. We just see that if the corresponding variable in this assignment, we print it. Okay, so and this is basically all. This completes the whole reduction. So let's see what happens if we call this Python script. It will immediately find an answer. So this is an answer for our initial puzzle. Let me also make a small sanity check. Let me tweak a little bit this puzzle. Let me put 5 here. Then the corresponding puzzle will be for sure unsatisfiable, just because now the first line contains 2 occurrences of 5. So it is not possible to complete this puzzle. Okay. Now let me call it once again. So in this case, the corresponding formula is unsatisfiable, and our script reports that there is no solution. As you can see, it works just in blink of an eye, and you can feed your favorite Sudoku puzzle into this script to see how fastly the Minisat sat solver will solve this puzzle. Hello and welcome to the next module, in which we are going to consider various ways of solving NP-complete problems. Before we proceed to actual algorithms, imagine the following situation. At your job, you are given a task to implement an efficient program that solves a certain search problem. Well, with some probability, your problem can be solved with some of the known techniques, like dynamic programming or linear programming or graph algorithms. But even if this is the case, usually it is not easy to realize this, and at least it takes time. And unfortunately, this happens very rarely. So in about 2 weeks of trying to apply some of the known techniques to your search problem, you come to the office of your boss and say, I can't find an efficient algorithm for this problem. I guess I'm just too dumb. One of the reasons why you cannot design an efficient algorithm for your problem might be that there is just no efficient algorithm for your problem. This would allow you to say to your boss, I can't find an efficient algorithm because no such algorithm is possible. Note, however, that currently we do not know how to prove that for any search problem, we do not have any example of a search problem for which we can prove that it cannot be solved by a polynomial time algorithm. In particular, if we had such a proof, we would resolve the P versus NP question, right? What we can do on the other hand is to show that some search problems are the hardest search problems. So what you do is you show that your problem is the hardest one. That is, you show that your problem is NP complete. This in turn allows you to say to your boss, I can't find an efficient algorithm, but neither can all these famous people. Okay, you have proved that your problem is NP complete. This in particular means that it is very difficult to design a polynomial time algorithm for it. But at this point, unfortunately, the problem doesn't go away. Your boss still wants you to solve it. So on one hand, you need to design an efficient algorithm for your problem. On the other hand, you know that designing such an algorithm is as hard as resolving the famous Millennium Prize problem P versus NP. Okay, should you give up at this point? No, not at all. In this module, we will learn a few techniques that allow you to solve NP-complete problems efficiently in practice. This is an outline for the rest of this module. We know already that if P is not equal to NP, then for any NP-complete problem, there is no polynomial time algorithm that finds an optimal solution in all cases. Note that there are three requirements on an algorithm in this statement. So first, we want our algorithm to have polynomial running time. Second, we want it to return an optimal solution. And third, we want it to do so in all cases. To solve an NP-complete problem in practice, you might want to relax one of these conditions. For example, there are algorithms that solve an NP-complete problem in practice, but not in polynomial time, but not in all cases, but only in some cases. Such algorithms are called algorithms for special cases. So they have polynomial time, they produce optimal solution for a problem, but not in all cases, but just in some cases. Also, it is possible sometimes to design an algorithm that works in polynomial time, and in all cases it returns a solution which might not be optimal, but it is guaranteed to be close to optimal. We will see examples of such algorithms, and finally, we can design an algorithm which always finds an optimal solution in all cases. But we cannot prove a polynomial upper bound on its running time, but still it works well in practice. For all these three types of algorithms, we will see examples in the next parts. In this lesson, we will consider algorithms that solve NP-complete problems in special cases. The main message of this lesson is the following. The fact that your problem is NP-complete does not exclude the possibility of a very efficient algorithm that solves your problem in some special restricted cases. So once again, the fact that the problem is NP-complete means that it is difficult to design an efficient algorithm that works for all possible cases. But it might be the case that for some special cases there exists a much more efficient algorithm. Our first example of such a problem is two-satisfiability problem. For this problem, we will see a surprising connection between Boolean formulas in 2CNF and graphs. Namely, we will apply the depth-first search algorithm to solve a special case of the satisfiability problem just in linear time. The input of the two-satisfiability problem, which is also abbreviated as just 2SAT, is a set of clauses, each of which contains at most two literals. Recall that a literal is a Boolean variable or a negation of a Boolean variable. And what we need to find is to check whether we can assign Boolean values to the variables of this formula to satisfy all these clauses. So what we need to return is either a satisfying assignment, or we need to report that there is no such satisfying assignment. Let me give you a few examples. So this is a formula in 2CNF. In 2CNF, so all clauses contain at most two literals, and it can be satisfied with the following assignment. Let's check it. If x is equal to 0, y is equal to 1, and z is equal to 0, so then in the first clause is satisfied by the literal y, which has value 1. The second clause is satisfied by the negation of z. So z has value 0, so negation of z has value 1. And finally, the last clause is satisfied by the negation of x. Okay? This is another formula in 2CNF, and it is unsatisfiable. To see this, note that we have two clauses of length 1 here. So this is the first such clause, and it forces us to assign z the value 0. So z must be equal to 0 if we would like to satisfy this formula. Similarly, we need to assign the value 0 to y because of the last clause, right? Then what is left is these two clauses. Y and z, the literals y and z, are already falsified in these two clauses. So essentially what is left in these clauses, in the first clause we have x, in the second clause we have not x. And of course it is not possible to satisfy both these clauses by assigning x. Okay, so this formula is unsatisfiable. The last example of is also an unsatisfiable formula where we have two variables, and it is not difficult to see that it is also unsatisfiable just because these four clauses actually forbid all four possible ways of assigning the values x and y. For example, if we try to assign the value 1 to x and the value 0 to y, then we get the following clause. So which one? This one, which is unsatisfied. And no matter how we assign two values for these two variables, we always get an unsatisfied clause. Consider a true clause of our input formula. Say it contains literals L1 and L2. Basically what it says us is that we should not assign simultaneously the value 0 to both L1 and L2, because in this case this clause will be clearly falsified. In other words, if we assign the value 0 to L1, we must assign the value 1 to L2, because this is the only way to satisfy this clause when L1 is already equal to 0. And vice versa. If we assign the value 0 to L2, we must assign the value 1 to L1. So this is a kind of implication, and in fact, implication is a well-known binary operation. It is defined by the following truth table. So it is equal 1 in all cases except for the following one. When x is equal to 1 and y is equal to 0, the implication from x to y is also equal to 0. In all other cases, it is equal to 1. Put it otherwise, it says the following, that falsity implies everything. It is shown here. If x is false, then it implies both the truth and the falsity. Okay. However, if x is false, if x is true, it only implies the truth. The implication from x to y when x is equal to 1 is only equal to 1 when y is equal to 1 too. This observation brings us to the following so-called implication graph. It is defined as follows. Given a 2CNF formula, we first introduce, for each variable of this formula, we introduce two vertices, one labeled with this variable and one labeled with its negation. Then for each two clause that contains two literals, say L1 and L2, we introduce two directed edges. The first one goes from the negation of L1 to L2, and the second one goes from the negation of L2 to L1. Okay? And finally, for each clause of length 1, which contains just some literal L, we introduce an edge, a directed edge again, that goes from the negation of L to L itself. Okay, so in a sense, this graph contains all implications that are imposed by our input formula. To give an example, consider the following 2CNF formula consisting of 3 variables x, y, z and 4 clauses of length 2. To construct its implication graph, we first introduce 6 vertices. 2 vertices for each input variable. Okay, this gives us the following 6 vertices: x not x, y not y, and z not z. Then we start introduce edges. The first clause gives us the following 2 edges, namely an edge from x to y, this edge, and an x from not y to not x. Once again, it corresponds to the following clause. Let's understand once again why these 2 edges correspond to this clause. Well, what essentially this clause says us is that if if not x is equal to 0, which means that x is equal to 1, then y must be equal to 1. Well, this is essentially what is given to us by this implication, right? It says that if x is 1, if this is 1, then this also must be 1 to satisfy this implication. The other edge says that if this edge, if not y is equal to 1, this actually means that y is equal to 0, then not x must be equal to 1. And this is indeed true. If y is equal to 0, then this literal is falsified in this clause, which means that the only way to satisfy it is to set not x to be equal to 1, right? Then we continue in the same manner. For the second clause, we introduce the following two edges. For the third clause, we introduce the following two edges. And finally, for the last clause, for the fourth one, we introduce the following two edges. Now we have an implication graph. Now consider some specific assignment of Boolean values to the variables of this formula. For example, when x is equal to 1, y is equal to 1, and z is equal to 1, all the clauses are satisfied. It can be easily seen just by observing that each clause in our input formula contains a positive literal. By saying positive, I mean a variable with no negation. So, for example, here y satisfies this clause, here z satisfies this clause, here x satisfies this clause, and the last clause is satisfied actually both by z and y. Also, we can see that each edge in this graph is also in a sense satisfied. Now let's consider another assignment that actually falsifies the input formula. If we assign the value 0 to x, y, and z, then the first three clauses are satisfied. The first one is satisfied by x, the second one by not y, the third one by not z, but in the last clause both the literals are equal to 0. Okay, and we see also that the corresponding two edges in the graph are also falsified. By saying falsified, I mean that the beginning of this edge has the value 1, so z is equal to 0, so not z is equal to 1, while the end of this edge is equal to 0, right? So 1 does not imply 0. So truth does not imply falsity. And the same for this edge. In this case, y is equal to 0, so this vertex has value 1, while the end of this edge has the value 0. And this is exactly the situation when the implication is falsified, when it says that the truth implies falsity. Our goal then, given this graph, our goal is to assign the values to all the variables of our input formula so that all the edges are satisfied. And as we discussed already, an edge is satisfied if and only if, well, it is easier to say what it means for an edge to be falsified. An edge is falsified when its beginning is labeled with 1 and its end is labeled with 0. So we need an assignment to all the variables of our input formula such that no edge is falsified. Before we proceed to an algorithm, let's state a few important properties of the implication graph. The first one says that the graph is skew-symmetric. Formally, it means that if there is an edge from a vertex labeled by literal L1 to a vertex labeled by a literal L2, then there is also an edge from the negation of L2 to the negation of L1. This is just by definition of this graph, right? So if we introduced an edge from L1 to L2, then at the same time, we introduced an edge from the negation of L2 to the negation of L1. And this also generalizes to paths in graph. If there is a directed path from L1 to L2, then there is a directed path from the negation of L2 to the negation of L1. This follows directly from the previous property about edges. To see this, let's consider the path from L1 to L2. So it contains several edges. It starts with L1 and ends with L2. Now consider the last edge. Denote the vertex, the beginning of this edge, for example, by V. So we know that there is an edge from V to L2, which means that there is also an edge from the negation of L2 to the negation of V. Then consider second to last edge. Assume that it is from U to V. The fact that there is an edge from U to V means that there is an edge, oh I'm sorry, so there should be a negation of V. There is an edge from the negation of V to the negation of U. And so on. By continuing in the same manner, we will finally reach the negation of L1. So once again, if there is a path from L1 to L2, then there is also a path from the negation of L2 to the negation of L1. The second property, in a sense, says that the implication is transitive. Namely, if A implies B and B implies C, then A also implies C. More formally, the lemma says the following. Assume that there is a path from L1 to L2 in our graph. Assume also that we have a truth assignment that satisfies all the edges of our implication graph. Then L1 in this assignment, the value of L1 must imply the value of L2. That is, it cannot be the case that the value of L1 is 1 and the value of L2 is 0. To prove it, assume for the sake of contradiction that in our graph and in our assignment, L1 is assigned 1 and L2 is assigned 0. We know that there is a path and all the edges are satisfied, so all the edges of this path are also satisfied. So we have a path where all the edges are satisfied and its beginning is labeled with 1 and its end is labeled with 0. This means that actually there is a transition on this path where we go from 1 to 0, right? So there is some edge such that its beginning is labeled with 1 and its end is labeled with 0. But this means that this edge is not satisfied, it is falsified. Again, recall that 1 does not imply 0, which leads us to a contradiction. The transitivity property that we've just proved implies the following additional property. If we have two literals that stay in the same strongly connected component of the implication graph, then they must be assigned the same value in any satisfying assignment. Why is that? We'll consider two literals, L1 and L2. Assume that they stay in the same strongly connected component. So this is a strongly connected component of the implication graph. Assume for the sake of contradiction that there is a satisfying assignment which assigns the value 1 to one of them and the value 0 to the other of them. For example, assume that L1 is assigned the value 1 and L2 is assigned the value 0. The fact that they lie in the same strongly connected component means that there is a path from L1 to L2. But this contradicts to the fact that L1 must imply L2, right? So L1 and L2, if they stay in the same strongly connected component, must be assigned the same value. This in turn implies that if in the implication graph there is a strongly connected component that contains some literal together with its negation, then this formula is unsatisfiable, because we cannot assign the same value to a literal and its negation. Right? So if a strongly connected component of the implication graph contains a literal together with its negation, we stop immediately and return that the formula is unsatisfiable. It turns out that this is the only case when the input formula is unsatisfiable, and we will prove this in a minute. As we've just discussed, the input formula is satisfiable if and only if its implication graph, does not contain a strongly connected component which contains a literal together with its negation. We still need to prove this property, but using this property we're already ready to write down an algorithm. So the algorithm proceeds as follows. Given a 2CNF formula f, it first constructs the implication graph G of this formula. We then find the strongly connected components of this graph. Then we check whether some of the strongly connected components contains a variable together with its negation. If there is such a strongly connected component, we return immediately that the formula is unsatisfiable. This is because we know already that in any satisfying assignment, all the literals lying in the same strongly connected component must be assigned the same value, and we cannot assign the same value to X and to its negation. In the remaining case, we know that the formula is satisfiable. So the remaining part of the algorithm just constructs the corresponding satisfying assignment. For this, we first find a topological ordering of all strongly connected components. Recall that the so-called metagraph or condensation or graph of strongly connected components is always a directed acyclic graph, which means that we can find its topological ordering, some topological ordering of all its strongly connected components. Then we process the strongly connected components in reverse topological ordering. So we first place them on a line such that each edge goes from going from one strongly connected components to some other, goes from left to right, and then we proceed the strongly connected components from right to left. For each strongly connected component, we consider the literals of the vertices staying in this strongly connected component. If they are not assigned yet, we assign them the value 1 and we assign the value 0 to all the negations of these literals. This way we assign all the variables. And in the end, we just return the corresponding satisfying assignment. We still need to prove that this algorithm is correct, but we already know that the running time of this algorithm is linear in the size of the input formula. Why is that? Well, because we can assume that M is the number of clauses in our M is the number of clauses of the input formula, clauses, and N is the number of variables. Okay, then the first step clearly takes time n plus m, right? Because, well, we first introduce 2n vertices, and then for each of m clauses we introduce 2 edges. The second, so what we get is a graph on 2n vertices and 2m edges. The second step is also linear. We know that the strongly connected components of a graph can be found by just 2 calls to the depth first search in linear time. This is also a linear step, right? So we just go through all variables, and for each variable we check whether this variable and its negation lie in the same strongly connected component. The topological ordering of a graph can also be found in linear time, right? Finally, here we just process all the strongly connected components, and at this step we consider also all vertices of the initial graph, so this step also takes linear time. So overall, the running time of this algorithm is linear. We now need to prove that our algorithm is correct. For this, we need to show that our way of assigning values to all the variables satisfies all the edges. Recall that an edge is not satisfied in the only possible case, when its beginning is assigned the value 1 and its end is assigned the value 0. So we want to prove that our algorithm avoids such cases. Well, intuitively, it happens to avoid such cases, we do the following. We process all our edges going from right to left, namely in reverse topological ordering. And we always assign ones to the rightmost available vertex. So we process them. We process the vertices, namely the strongly connected components containing our vertices from right to left, and we always assign the last available vertex the value 1. This way we guarantee that basically we have zeros on the left and ones on the right. Well, very hand-wavy. More formally, we prove that when a literal is set to 1, then all the literals that are reachable from it, well, namely all the literals that are reachable from it stay on the right of it. They are already assigned the value 1. And similarly, when a literal is assigned the value 0, all the literals that this literal is reachable from have already been assigned the value 0. Well, to be more formal, let me draw a little bit. So we would like to show that our algorithm, when assigning the values to all the variables, our algorithm avoids the following thing: that this variable is assigned 0, this literal is assigned 0, this literal is assigned 1. Okay, let me denote them by U and V. So consider a situation when v was assigned 0 by our, at a point of time when v was assigned 0 by our algorithm. This means that at that point, not v was assigned 1, right? Then we were processing all the strongly connected components from right to left, and we've assigned 1 to the literal not v at this point. And this forced us to assign the value 0 to v. But now the skew symmetry of the graph implies that there is also an edge from v to not u in our graph. And the fact that we processed all the edges from left to right means that not u was assigned 1 also, right? But this means that u cannot take value 1. It was assigned the value 0, in fact. This is a contradiction. Okay, so this completes the analysis of this algorithm. Once again, we've just proved that our way of assigning the values to all the variables of the input formula satisfies all the edges and hence also satisfies the input formula. The next NP-complete problem that we're going to solve is called independent set. And the corresponding special case for which we're going to design a linear time algorithm is when an input graph is actually a tree. A real-life application of this problem is the following. Assume that you are organizing a company party and you would like to invite to this party as many people as possible with a single constraint. You know that no person is going to enjoy your party if he or she is invited to this party together with his or her direct boss. The mathematical model of this problem is the following. You are given a tree and you would like to find in this tree a subset of vertices of maximum possible size such that no two of them are adjacent. Okay, such that there is no edge between any two of them. So to give an example, consider the following toy tree. In this tree there is an independent set of size 5, shown here on the slide. There is also another independent set of size 6, and an independent set of maximum size is shown here, and it has size 7. So our goal is to find efficiently an independent set of maximum possible size in any tree. As we've discussed before, this problem can be solved with a simple greedy algorithm. The corresponding safe move in this case is the following. Take into a solution all the leaves. To prove that this algorithm is correct, we need to show that this step is indeed safe, namely that there always exists an optimal solution that is consistent with this step. In other words, that there exists a solution which contains all the leaves. To prove this, we usually argue as follows. We can take any solution and we will transform it without decreasing its size so that to get a solution which contains all the leaves. In particular, if we start with an optimal solution, I mean with a solution of maximum size, we will transform it into a solution whose size is at least the size of the initial solution, which means that this new solution is optimal, and it is also a valid solution. This will prove that the statement is correct. Well, to explain how to transform it, we, as usual, consider a toy example. So consider such a solution. So the blue vertices here are selected into an independent set. So we see that there are 3 leaves that are not included into our solution. So let's just take them into our solution. This will force us also to exclude all the parents, but the crucial observation is that this does not decrease the size of the current solution, and the current solution is still a valid solution, because for each of these leaves we excluded their parents. So this way we get a solution of the same size that includes all the leaves, and this proves that taking all the leaves into a solution is a safe move. The corresponding algorithm is quite simple. So given a tree, you repeat the following while the tree is not empty. You take all the leaves into a solution, then you remove from the tree all the leaves together with all its parents. In the end, you return the constructed solution. The running time of the corresponding algorithm is linear if it is carefully implemented. In particular, you might want to do the following. For each vertex, you keep track of the number of its children. You actually do not remove anything from the tree itself, but you keep track of the current number of children for each vertex. So when you remove a vertex, you decrease by 1 the number of children of its parent. And you also maintain a queue that contains the vertices of that do not have any children currently. So at each iteration, you know all the leaves of the current tree. These are exactly the vertices with no children. Now let's generalize the problem. Assume that you are still organizing a company party, but now instead of maximizing the number of people at the party, you are going to maximize the total fun factor of your party. Namely, each person is assigned some non-negative fun factor, and you would like to maximize the total fun factor of all the invited people. The mathematical model now is the following. You are given a tree with weights on vertices, and you would like to find an independent set in this tree whose total weight is as large as possible. Okay? To give an example, again, consider the following tree. One independent set in this tree is shown here in the slide. Its total weight is 17, and an optimal one has total weight 18. As you see, it doesn't include all the leaves. So this problem cannot be solved by the same greedy algorithm, and we need to design a new algorithm for this problem. The new problem can be solved with the dynamic programming technique. When we have a problem on trees, it is very natural to try to define sub-problems for sub-trees of this tree. And this is what we're going to do. For vertex v, denote by d of v the maximum weight of an independent set in a tree rooted at the vertex v. Then there are basically two cases. Either we include v into our solution, or we do not include it. If we include it, we get it contributes the weight of this vertex to the total fun factor, and we also cannot take any of its children into a solution, because otherwise it will not be an independent set. However, we can take anything from the subtrees rooted at its grandchildren, and in particular we are maximizing the total fun factor, so we would like to solve the problem optimally for all these subtrees. So if we included what we can get, the maximum total fun factors that we can get is the weight of the vertex v plus the sum of all the optimal solutions for overall grandchildren w of v. On the other hand, if we do not include v into a solution, then we can solve the same problem independently for all its children. So the second case corresponds to the situation when we do not include v into our solution, and in this case, so this is our vertex v, and this is, we do not include it into a solution, then we can just solve it optimally for all its subtrees, and we can then take the sum of all these vertices. So since they stay in the independent subtrees, the resulting union of all the vertices that we get from our subproblems is also an independent set in the whole tree. We're going to use dynamic programming with memoization to implement the corresponding algorithm, which uses the recurrence relation that we've just discovered. Namely, the function fun party for the vertex v is going to compute the optimal answer for the subtree rooted at v, when we only going to compute it if we haven't computed the corresponding value before. This is checked in the first if loop. So if d of v is still equal to infinity, so at this point we assume that initially d of v is equal to infinity to all vertices. So if we haven't computed this value before, we start computing it. Then we check whether the vertex v is a leaf. If it is a leaf, then the answer is obvious. Then the obvious good thing is to take this vertex into a solution. So the optimal answer is just the weight of this vertex. Otherwise, we need to compute its value recursively. We do this through grandchildren and children of the current vertex. The first case is when we take the vertex v into a solution. So first we initialize the variable m1 with the weight of the current vertex, and then we iterate through all grandchildren of the vertex v. This is done in these two loops, and we add to m1 the optimal answer for each grandchildren. We then proceed to the second case when we do not include v into a solution. So m0 is initialized as 0, and then for all children u of, vertex v, we need to add the optimal value for the corresponding children. This is done here. Okay, then we just select the maximum of the resulting two values and assign this value to d of v. And finally, we return d of v. The running time of this algorithm is also big O of the size of the tree. And this is why. For each vertex, there is just one serious call to FunPaTI. By serious, I mean a call which actually is inside this if loop, which gives rise to some computation. Because after the first time when we are inside this loop for the vertex v, we will store the value in d of v, and then for any further call for FunPaTI of v, we just return the value immediately. We just return it here. Note also that the value of d of v is important for us only when we compute only when we solve a subproblem corresponding to its parent and to its grandparent, meaning that we will have only a constant number of calls to FunPaTI of v for each vertex v. We now show the result of applying this algorithm to our previous example. So in this tree, we start to fill it in from the leaves to the root. So for each leaf, the value is computed in an obvious way. For example, for this leaf, for this subtree, the answer is 1. For this subtree, the answer is 2. And for this subtree, the answer is also 1. For this subtree, we need to make a decision. Either we take this vertex in which we gain 7, or we don't take it. In which case we can get 1 from here, 2 from here, and 1 from here, which gives us 4. 7 is better, so an optimal independent set in this case has total weight 7. For this vertex, the optimal value is 2 because it is a leaf, and for this vertex, again, we need to select whether to take this vertex into a solution or not. If we take it, then we cannot take the vertices 7 and 2, its children, so the value of the solution will be 6 plus the values of its grandchildren, which are these. So the values of its grandchildren are 1, 2, and 1, so 6 plus 1 plus 2 plus 1 gives us 10. So this corresponds to the case when we take the root of the current subtree into a solution. On the other hand, if we don't take it into a solution, then the maximum that we can achieve is 7 in this subtree and 2 in this subtree, which gives us 9. 10 is better than 9, so 10 is the optimal answer for this subtree. In a similar fashion, we get 5 here and we get 3 here. Now for this vertex, again, we need to select whether it is better to include it into a solution or it is better to avoid it. If we include it into a solution, then the maximum that we can get is 3 plus, in this case, if we include it into a solution, we cannot use its children, but we can use anything in the subtrees rooted by its grandchildren. So we can get 2 plus 3 plus 7 plus 2. So this gives us 3 plus 2 plus 3 plus 7 plus 2, which is equal to, I guess, 17. Right. If on the other hand we do not include it, then we can get anything we want from the subtrees rooted at its children. This will give us 5 plus 3 plus 10. 5 plus 3 plus 10 is 18, which is better, so we conclude that 18 is the best we can do for this toy example. Okay, so this concludes the lecture for the special cases of NP-complete problems. Let me remind you the main idea once again. The fact that your problem is NP-complete does not exclude a possibility that some special cases that arise in practice of this problem can be efficiently solved. And we've just seen 2 such examples. Despite of the fact that the satisfiability problem is difficult in the general case, its special cases, namely if all the clauses of a formula contain at most 2 literals, can be easily solved in linear time. The second example was about independent set. this problem is hard in general. So given a graph, it is difficult to implement an algorithm which always find an optimum size independent set of a graph. But if you know that all the graphs that arise in your application are trees, then it is easy to implement a linear time algorithm that will find an optimal answer quickly. Welcome to the next lesson of coping with NP-completeness module, in which we are going to design exact algorithms for NP-complete problems. Exact algorithms are also called sometimes intelligent exhaustive search, as opposed to brute force search algorithm, which to find an optimal solution just enumerates all possible candidate solutions and selects the best one. Instead, we are going to find an optimal solution without actually going through all possible candidate solutions. The first problem for which we illustrate such an algorithm is three satisfiability problem. Recall that the input of this problem consists of a CNF formula, and it is three satisfiability, so each clause contains at most three literals. So this formula is in three conjunctive normal form, in 3 CNF. And our goal is to find out whether it is possible to assign Boolean values to all the variables of this formula so as to satisfy all the clauses. Let me quickly show you once again two toy examples. So the first formula here is satisfiable because we can set, for example, the value 1 to x, y, and z, or the value 1 to x and the value 0 to y and z. And the second formula is unsatisfiable. We cannot set the values of the variables x, y, and z to satisfy all these 5 clauses. A naive brute force search algorithm for the three satisfiability problem does the following. It just goes through all possible candidate solutions, that is, truth assignments to all the variables of a formula, and checks whether any of them satisfies the input formula. If n is the number of variables of an input formula f, then the running time of this algorithm is proportional to the length of f times 2 to the n. Because we have 2 to the n truth assignments, and for all of them we need to scan the formula to check whether all of the clauses are satisfied or not. In particular, if your formula is unsatisfiable, then your algorithm will be forced to check all these assignments. So its running time will be 2 to the n. So our goal for this module is to avoid going through all possible 2 to the n assignments and still to check whether the input formula is satisfiable or not. The first technique that we're going to use for this is called backtracking. So this is a well-known technique which proceeds as follows. You construct your solution piece by piece. And then at each step, when you realize that your current solution cannot be extended, your current partial solution cannot be extended to a valid solution, you backtrack, you go back. This idea is used in many situations, for many combinatorial optimization problems and for many puzzles and games. So imagine, for example, that you are playing a game and you are staying in some room and you are in a maze and you are looking for an exit from a maze. And in the room that you are currently staying, there are 3 doors leading out of this room. So you use one of these rooms and you enter another room for which you see that there are no other doors. So you are in a deadlock. So you then go back, so you backtrack and you decide to use some other room. So this is a way of solving a combinatorial problem. It is called backtracking once again. We now show on a toy example as usual how this technique, namely backtracking, is used to check the satisfiability of Boolean formulas. So consider the following formula. Well, we need to find a satisfying assignment and we don't know what to do, so let's just try to assign the value 0 to x1. What happens in this case is that, well, x1 disappears from this clause because it is already falsified. On the other hand, this clause is already satisfied, so this clause disappears entirely. x1 also disappears from this clause and it becomes just x2 or negation of x3. Then x1 disappears also from this clause and this clause is left untouched. We then proceed as follows. Now let's try to assign the value 0 to x2. what happens is that, well, this clause is satisfied. x2 disappears from this clause because it is falsified already from this clause and from this clause. So what we get is x3 or x4, and then the negation of x3, and then the negation of x4. Then we try to assign the value 0 to x3. What is left? So this clause disappears, x3 disappears from this clause. So what is left is one clause containing x4 and one clause containing the negation of x4. We then try to assign the value to x4. If we assign the value 0 to x4, then we falsify this clause. So this clause disappears and this clause becomes empty, meaning that there is no satisfied literal in this clause, that there is no way to satisfy this clause anymore, right? The same happens if we assign the value x4 to the value 1 to x4. In this case, we satisfy this clause, but at the same time we falsify this clause. Once again, this clause becomes empty, which means that there is no way at this point to satisfy this clause. So at this point, we backtrack further. We just realized that it was a wrong move to assign the value 0 to x3. It leads to an unsatisfiable formula. So we now try to assign the value 1 to x3. So now we returned back here and we are trying to assign the value 1 to x3. But in this case, we falsify this clause. This clause becomes empty, which means that the whole this formula is unsatisfiable, which means that it was a wrong move to assign the value 0 to x2, and now we need to try to assign the value 1 to x2. We do this, but we immediately falsify the following clause, right? So in all other clauses, we have x2, so all of them are satisfied, but what is left is an empty clause which cannot be satisfied. So at this point, we backtrack back to the initial formula, and at this point, we know already that we must assign the value 1 if we want to satisfy this formula. So we do this and we see again that there is an empty clause. So at this point, we conclude that the initial formula is unsatisfiable. Note the following important fact. So we realized that it is unsatisfiable without considering all possible 16 truth assignments to our 4 input variables, right? This is how the pseudocode of the corresponding algorithm looks like. So we first check whether f is empty or not. So if f has no clauses and we have nothing to satisfy, then we just return that the formula is satisfiable. We then check if f is not empty, we check whether it contains an empty clause. As we've discussed before, an empty clause means a clause which cannot be satisfied. So all the literals in this clause have already been falsified. In this case, we return that the formula is unsatisfiable. Otherwise, we take some variable which is still present in the formula f, so x is some unassigned variable of f. And then we try two cases. We first try to assign the value 0 to x. So this notation means that we assign the value 0 to x. When assigning the value 0 to x, we remove all the clauses which contain the negation of x. All such clauses are already satisfied, and we remove all occurrences of x without negation from all other clauses, because x is already falsified. If this formula turns out to be satisfiable, we return immediately that the whole formula is satisfied. Otherwise, we backtrack. We try to assign the value 1 to x. Again, so we first assign the value 1 to x, meaning that we remove all the clauses that contain x from the formula, and we remove the x negated from all other clauses. If it is if the recursive call returns that the formula is satisfiable, we return that the initial formula is also satisfiable. In the remaining case, we just report that the formula is unsatisfiable, because no matter how we assign the value to x, the resulting formula is unsatisfiable, meaning that there is no way of assigning the value to x to get a satisfiable formula. So as we've seen in our toy example, such a strategy allows to find a satisfying assignment or to conclude that the formula is unsatisfiable without actually checking all possible 2 to the n truth assignments, 2 to the n optimal, 2 to the n candidate solutions. I'm sorry. So we do this as follows. We build each solution piece by piece. We try to extend each partial solution. And whenever we see that this is a dead end, that the current partial solution cannot be extended to a valid solution, we backtrack immediately. We cut the corresponding branch of a tree, and we do not extend it further. So this is a technique which is used in many modern and state-of-the-art SAT solvers. We did not prove any upper bound on the running time of the present algorithm. Well, as you expect, the running time of this algorithm might be exponential, because if we prove that it is polynomial, we would show that SAT can be solved in polynomial time, and this would resolve the P versus NP question. However, this technique is very useful in practice. However, in practice, SAT solvers also use complicated heuristics for simplifying formula and for selecting the next variable for branching, and even selecting the next value for branching. So in practice, this idea, improved by various heuristics of simplifying a formula, choosing the next variable and choosing the value for the next variable, lead to very efficient algorithms that are able to solve formulas with thousands of variables. Another commonly used technique is called local search, and this is the technique that we will consider in the next part. The next technique that we are going to consider is called local search. This is also a widely used in practice technique. It is used both for search problems and for optimization problems. Its main idea is roughly the following. You start with some initial solution. Then you iteratively do the following. If your current solution is not good enough, you try to change it a little bit somewhere to get a new solution which is in some sense better, or which fixes something. So pictorially it looks as follows. You go from one solution to a solution which is close to it, which results from the current solution by some small change, then to some other solution and to some other, until you get a solution which is good enough for you. So this is a very, very vague explanation of this technique. We will now give a more concrete explanation of a local search algorithm. So this is how a local search algorithm might look like for the 3 satisfiability problem. Consider a formula in 3CNF and denote its variables by x1, x2, and so on, xn. So it has n Boolean variables. So a candidate solution for such a formula is just a truth assignment for all these variables. So in other words, this is just a vector in 0, 1 to the n, right? Since we are going to apply local search, that is we need to change each candidate solution a little bit to go to another solution in its neighborhood. We need to define the notion of distance between two different candidate solutions. So let alpha and beta be 2 such candidate solutions, that is vectors in 0, 1 to the n. We define the distance between them as the number of bits where they differ. So more formally, the distance, which is called also Hamming distance, the distance between alpha and beta is the number of such indices I, where alpha sub I is not equal to beta sub I. Consequently, by a Hamming ball with a center at an assignment alpha and with radius r, we denote the set of all assignments that are at distance at most r from alpha. To give a concrete example, for example, the Hamming ball with radius in this Boolean assignment, with center at this Boolean assignment and radius 0, so this is alpha, this is r, contains just exactly the same Boolean assignment, right? The Hamming ball with radius 1 and center at the same Boolean assignment contains 5 different assignments. So in this case, by the way, n is equal to 4. So first of all, it contains the center of this ball. It also contains 4 Boolean assignments that result from our initial assignment by changing just 1 bit, right? So in the first one, we change the first bit, here we change the second bit, here we change the third bit, here we change we changed the fourth bit. Finally, the Hamming ball with the same center and with radius 2 contains the following assignments. So this is an assignment at distance 1. These are 4 assignments at distance 1. I'm sorry, so this is an assignment at distance 0. These are 4 assignments at distance 1. And these are 6 assignments at distance exactly 2. This is a crucial lemma for our local search algorithm, which checks satisfiability of a given 3CNF formula. Assume that we are given a formula f, and we, together with this formula f, we are given a Hamming ball with center alpha and radius r, for which we know that it contains a satisfying assignment of a formula f. Then we can find a satisfying assignment in this ball in times 3 to the r times the length of the formula. The satisfying assignment that we are going to find might coincide with beta or might be a different one. But in any case, if we know that this Hamming ball contains a satisfying assignment, then we will find some satisfying assignment in this running time. This is how to do this. We first check whether the assignment alpha, namely the center of our current ball, satisfies the formula f. If it satisfies, we just return alpha immediately. Otherwise, there is a non-satisfied clause which contains at most 3 variables. I assume that this clause looks as follows. It is xi or negation of xj or xk. We know for sure that alpha assigns the value 0 to xi, the value 1 to xj, and the value 0 for xk, right? This is just because this clause is unsatisfied under the assignment alpha. Let's then do the following. Let's consider 3 different assignments: alpha I, alpha j, and alpha k. Alpha I differs from alpha only in the i's bit. Alpha j differs from alpha only in the j's bit, and finally alpha k results from alpha by flipping the k's bit. So what we know about these 3 assignments is that at least one of them is closer to beta, right? So we don't know which one, but we know for sure that at least one of them is closer to beta than alpha. Why is that? Because beta satisfies the currently considered clause. So in beta, either xi is equal to 1, or xj is equal to 0, or xk is equal to 1. So in at least alpha I or alpha j or alpha k, we fixed the right bit, the one that has the same value in beta. So at least one of them is closer to beta. Probably 2 of them, or probably 3 of them, but it doesn't matter at this point. What is important is that at least one of them is closer. So we start with alpha, and then we consider 3 different assignments: alpha I, alpha j, alpha k. For each of them, we make the same step. For each of them, we also consider three different assignments. And we always know that at least in one of the branches, we get closer to beta. Since we know that the distance between alpha and beta is at most r, just because beta lies in the Hamming ball with center alpha and radius r, we conclude that in the corresponding algorithm, there are at most 3 to the r recursive calls. This is how it looks pictorially. So we have a Hamming ball with center alpha and radius r. So the radius of this ball is at most r. We know that somewhere in this ball there is a satisfying assignment beta. We don't know which one. Of course, we're only looking for a satisfying assignment, but assume that there is a satisfying assignment beta in this case. Then at each step we do the following. So we select an unsatisfied clause, and from alpha we move to one of, we try all these 3 satisfying assignments that differ from alpha in just one bit. We don't know in which direction we need to go, but we know that in at least one of these directions we get closer to beta. Then for all of these 3 assignments, we repeat this procedure, and in turn for all of them, we again repeat this procedure. So eventually, if we make r steps, we will find an assignment beta, or we will stop before this if we find another satisfying assignment. The crucial observation is that to eventually find beta, we need at most 3 to the r recursive calls. This is just because the distance between alpha and beta is at most r, and at each iteration, in at least one of these 3 branches, we get closer to beta. This is the pseudocode of the resulting algorithm. It is given a formula f, also an assignment alpha, and a radius r, and then it checks whether it tries to find a satisfying assignment in a ball with center alpha and radius r. We first check whether alpha satisfies the formula f. If it does, we return alpha immediately. Then we check whether the current radius is equal to 0. If it is equal to 0, we return that the current ball does not contain a satisfying assignment. So we return not found. So recall that if r is equal to 0, then the corresponding ball contains the assignment alpha itself. Then we take any unsatisfied clause and we denote by xi, xj, and xk the variables from this clause. Then we construct three different satisfying assignments: alpha I, alpha j, or alpha k. They all differ from the assignment alpha only in i's, j's, or k's positions respectively. We then make three recursive calls. More precisely, we first make the first recursive call with parameters f, alpha I, and r minus 1. If it finds a satisfying assignment, we immediately return. If not, we make a second recursive call for f, alpha j, and r minus 1. If it finds a satisfying assignment, we return immediately. If not, we make a third recursive call. So if none of them finds a satisfying assignment, we return not found. Okay, now we need to show how to use this procedure which checks whether a ball contains a satisfying assignment to check whether the given formula is satisfied. Well, assume that our initial formula, our formula f, is satisfiable, and there is a satisfying assignment beta. Well, there is a simple observation. Assume that there are more ones than zeros in the assignment beta. Then I claim that its distance from all ones assignment is at most n over 2. Well, this is clear. If there are more ones than zeros, then the number of ones in this assignment is at least n over 2, which means that the distance to the all ones assignment is at most n over 2. Otherwise, the distance of this assignment to the all zero assignment, that is an assignment which assigns zeros to all the variables, is also at most n over 2. This means that to check the satisfiability of the formula f, it is enough to check whether two huge balls contain any of two huge balls contain a satisfying assignment. Once again, if there is a satisfying assignment beta of a formula f, then it is contained either in a ball of radius n over 2 with center in all ones assignment, or in a ball with radius n over 2 whose center is in all zeros assignment. So if none of these recursive calls finds a satisfying assignment, then the initial formula is unsatisfiable for sure. The running time of this algorithm is big O of the size of the formula times 3 to the n over 2. This is just because we make two calls to check for two balls of radius n over 2, and each of these calls takes time roughly 3 to the n over 2. So this is roughly 1.733 to the n. So this is still exponential, still not acceptable in practice. However, note at the same time that this is exponentially faster than a brute force search algorithm, because the brute force search algorithm runs in time 2 to the n, and our algorithm runs in time 1.733 to the n. This is roughly 1.15 to the n. So it is exponentially faster. Already for n equal to 100, for example, our algorithm is roughly 1 million times faster than the brute force search algorithm. So this algorithm works well in theory, and local search heuristics and local search ideas, but in a slightly different form, are also widely used in modern SAT solvers. The next problem we are going to design efficient algorithms for is the traveling salesman problem. Using this problem, we are going to show the main ideas of the dynamic programming technique and the branch and bound technique. Well, recall that the input in the traveling salesman problem is a complete graph with weights on edges. We usually assume that the weights are non-negative, together with a budget b. And our goal is to find a cycle that visits each vertex exactly once and have total length at most b. It will be convenient for us to assume that the vertices of our graph are numbered with 1, 2, and so on, n, and that the start of the cycle and also the end of our cycle is at vertex 1. To give a toy example, as usual, consider the following graph with 5 vertices. Already for this small graph, it is not so easy to find an optimal cycle. There is, for example, a cycle going from 1 to 2 to 3 to 4 to 5 and going back to 1. Its total length is 15. There is another cycle whose length is 11, and an optimal cycle in this case has length 9. It is shown here on the slide. So note that a brute force search algorithm just goes through all possible n-1 factorial cycles. Why n-1 factorial? Well, because initially we start at vertex 1. From vertex 1 there are n-1 choices where to go next. For all of these n-1 vertices, there are n-2 choices where to go next, right? n-2 because we cannot go back to 1, and so on. So it is n-1 times n-2 times n-3 and so on. This gives us n-1 factorial. And this is the running time of an algorithm which is n-1 factorial, or roughly n factorial, is extremely bad. It is extremely small. It is even worse than 2 to the n, even slower. So already for n equal to 10, it is already infeasible, not to say about n equal to 100, for example. So our goal in this lecture is to design an algorithm whose running time is roughly n squared times 2 to the n. It is, of course, an exponential algorithm, but it is at least much better than going through all possible candidate solution. It is at least better than n factorial. In particular, if we consider the following fraction, n factorial divided by 2 to the n times n squared, then already for n equal to 100, this fraction is about 10 to the 120. So which means that already for n equal to 100, the algorithm that we are going to design is going to be 10 to the 100 roughly times faster than a brute force search solution. As we've mentioned already, we are going to apply the dynamic programming technique to design a faster than a brute force search algorithm for this problem. Since we are going to use the dynamic programming, this means that instead of solving one large problem, we are going to solve a collection of smaller problems. Usually sub-problems that we are going to solve represent just some partial solutions, right? And what is a good partial solution in case when we are looking for a cycle that visits each vertex exactly 1? Well, this is some initial part of a cycle, right? So when we have some initial part, we need to try to extend it somehow. And what information do we need to be able to extend it? Well, at least we need to know the last vertex of this initial part of this cycle. And we also need to know the set of all cities or the set of all vertices that we already visited. Right? So we know the last vertex of a path, and we know all the vertices that were already visited. And then we can consider all possible extensions of this path and select the best one. This way, we will eventually construct an optimal cycle. So let's formalize this idea. For a subset of vertices S, containing some vertex I and also the vertex 1, we denote by C of Si the length of a shortest path that starts at the vertex 1, ends at the vertex I, and visits all vertices from the set S exactly once. So namely, C of Si is the length of a shortest path that looks like this. So it goes from the vertex 1 to the vertex I, and all the vertices that it visits are from the set S. And also it visits all of these vertices exactly once. In particular, we assign C of the set containing just vertex 1 and vertex 1 to be equal to 0, because this is just an empty path, right? And for any other S that contains, that is of size at least 1, we assign C of S1 to be equal to plus infinity, because a path cannot end in the vertex 1. Okay? Then we need to find a recurrence relation expressing C of Si through solutions for smaller problems. For this, consider the following thing. So we need to go from vertex 1 to vertex I and visit all the vertices from the set S. And we would like to find a shortest possible such path. Consider the second to last vertex on this path. So this is vertex J. So the last step in an optimal path which we're looking for is from J to I. What can we say about the following path? So first of all, of course, it must also be a shortest possible path from the vertex 1 to vertex J. But also we know exactly the set of vertices that it visits. It visits the vertices S minus the vertex I, right? So these are exactly all the vertices except for the last one. So this allows us to express the solution for the set S and the city I through solutions for smaller subproblems as follows. We just go through all possible values of J except for J equal to I, and we select the minimum among the following expression. So it is stated otherwise, an optimal path going through all cities from the set S and ending in the vertex I is some optimal path that goes through all cities except for I and ends at some vertex J, extended with an edge from J to I. We do not know the exact vertex J because we're only looking for this path, but we just select the minimum over all such possible values of J. We are almost ready to implement the corresponding dynamic programming algorithm, so the only technical thing is the order in which we are going to solve our subproblems. This order should satisfy the following simple property. When computing the value of C of Si, we already need the values of all the subproblems it depends on to be computed, right? All such values are of the following form. It is C of S minus the CTI, comma J. Okay? So in particular, S minus I always have size less than the set S. So if we just go through all subsets in order of increasing size, then we are safe. This gives us the following algorithm. So given a graph, we first initialize C of 1, 1 to be equal to 0. So this just reflects the fact that if we need to find an optimal path that starts at vertex 1, visits just the vertex 1 and ends at vertex 1, then this is just an empty path, right? We just stay at the vertex 1, so it is equal to 0. Then we go through all possible sets of vertices denoted by S, and we do this in order of increasing size. So we gradually increase the parameter small s from 2 to n, and for all subsets S of size S, we do the following. First of all, we assign the value plus infinity to C of S1, because we need to visit each vertex exactly once. So we just mean that this is an infeasible path. It is equal to plus infinity. We start at vertex 1, so we should not end at vertex 1. Okay? Then for all I that lie in the set S, we need to compute the value of C of Si. For this, we consider all possible candidates to be the second to last vertex on an optimal path. So this is done here. The second to last vertex should not be equal to the vertex I itself. So we compute the minimum between among the current value and the following value. So this actually says that we first visit all the vertices except for the vertex I and then end in the vertex J, and then we append the edge from J to I, so the total length is increased by the weight or by the length of this of this last edge. Finally, we need to return the best such possible path, and we do this by just finding the minimum of the following expression. That is an optimal cycle that starts in the vertex I and ends in the vertex 1, and end in the vertex 1 is the following. It first visits all the vertices in the graph and then ends in the vertex I. And all these values are stored in the following cells in our table. Right? So since we don't know the last vertex in this cycle, we just select the minimum, and we also end the last edge in such a cycle. So finally, we compute the result using this expression. There is one technical remark left. In the algorithm, we need to somehow iterate over all subsets of our n cities. This can be done as follows. There is a natural one-to-one correspondence between integers from 0 to 2 to the n minus 1 and subsets of the set containing integers from 0 to n minus 1. So when implementing this algorithm, it is more convenient to consider integers from 0 to n minus 1 instead of integers from 1 to n. Namely, this correspondence is defined as follows. If you have an integer k from the following range, namely an integer which is at least 0 and at most 2 to the n minus 1, then we can then the corresponding set is defined by the positions where this integer has ones in binary representation. This is probably easier to show by an example, so consider the following two examples. Here we consider subsets of 3 elements of 0, 1, and 2, and for this we consider all integers from 0 to 7. So the binary representation of 0 is 0, 0, 0, right? So this corresponds to an empty set. The binary representation of 1 is 0, 0, 1. So we have 1 in the least significant bit, 0 in the next bit, and 0 in the most significant bit. So this corresponds to just subset containing just an element 0. Or for example, 3 is represented in binary as 1, 0, 1, 1. So it has 1 in the least significant bit and 1 in the next bit. So this corresponds to the subset 0, 1, right? So this way, instead of using C of Si, we can use just C of Ki, right? Where K is an integer from 0 to 2 to the n minus 1. The last operation that we need to do with the set S is that we need to exclude the element j from the set S. That is, since we are going to represent the set S as an integer, we need to find the corresponding integer. So what does it mean to extract S from the set? This means actually to flip the j's bit of the corresponding integer from 0 to 1. And this in turn means that we are going just to compute the bitwise parity of our current number k and the number where we have just 1 in the j's position, right? So if we compute the parity of these two numbers, let me probably write it as follows. So assume that this is our number k, and this is the position g where we have 1. And what we need to get is the following, right? So this corresponds to S, and this is S minus the element j. It looks like as follows. So to get this number, we just need to sum this number with the following number. Just the number which have 1 only in position number j, right? And this is, in turn, this is 2 to the j, right? So most modern programming languages allow to do this just in one line. Namely, you do this as follows. You take a number k, then you compute 2 to the j as follows, and then you just take this bitwise parity. So this gives you exactly the set S without the J's element. So now you are completely ready to implement this algorithm. The next general technique, whose main ideas we are going to illustrate on a toy example of solving the Trell-Salison problem, is called the branch and bound technique. It is quite similar actually to the backtracking technique, but backtracking is usually used for solving decision problems, while the branch and bound technique is usually used to solve optimization problems. Its main idea is as follows. Again, we are going to grow a huge tree, which in the end is going to represent the search space, that is the space of all candidate solutions. So we are going to grow these solutions piece by piece, but at each step, instead of doing this naively, in each point in this tree, we check whether the current branch, whether the current partial solution that we have has any chances to be extended to a solution which is better than the one that we currently found, which is better than the best one that we've currently seen. If it has no chances, we cut this branch immediately. We do not continue it if we realized that it cannot be extended to a solution which is better than the best one found so far. We illustrate the main idea of the branch and bound technique on a toy example. So consider the following graph consisting of 4 vertices. The graph is complete, meaning that there is an edge between any pair of vertices. One way to solve this is to consider all possible cycles. For this, we consider the following tree. So we start at vertex 1. From vertex 1, we can go to either of the following 3 vertices, to the vertex 2, to the vertex 3, or to the vertex 4, right? From the vertex 2, we are allowed to go either to vertex 3 or to vertex 4. We are not allowed to go back to the vertex 1 because we need a cycle that visits each vertex exactly once, and so on. So we then try to extend each possible partial solution with each possible variant. So from vertex 3, we actually need to go to vertex 4, and from vertex 4, we have no choice but to return to vertex 1. So when we see that there is that this is a full cycle visiting each vertex exactly 1, we compute its total length. So in this case, it is 19, and we do this for all possible cases. Here we have 7, here we have 18. Here we have 7 again, 18 again, and 19 again. So we have actually pairs of equals numbers here because the corresponding leaves, for example, this leaf and this leaf, they actually correspond to the same cycle, but traversed in 2 different directions. We can either go this way or this way. This gives actually the same cycle, of course, but with the same total length. Now let's do it in a more smart way. Let's grow the same tree, but let's try to compute the total length of our current partial solution on the fly, instead of computing this at the leaf. Namely, initially we stay at the vertex 1, so the total length is 0. Then we go, for example, to the vertex 2. At this point, the total length is 1. From vertex 2, we try to go to vertex 3. This gives us total length 6. So this is our current path. We go from 1 to 2, and then from 2 to 3. The current total length is 6. We then try to go to vertex 4. This is the only actually possibility. So our total length is 9, and then we return back to the vertex 1 because we already visited all other vertices. So this is the first full cycle that we discovered. So its total length is 19. So we marked that the best total length that we've seen so far is 19. Then we go back, then we backtrack actually to consider other possibilities. The first vertex the last vertex on our path when there was some possibilities is the vertex 2. Instead of going to vertex 3, we might want to go to vertex 4. This gives us the current length is 3, then we continue, now the current length is 6, and finally, when we get to the leaf of this tree, we see that the current that the current cycle gives us total length 7. So we update our variable which is responsible for the best solution found so far. It is 7. Okay, then again we backtrack. Now the last vertex where there is still a possibility to go to another vertex is the root of this tree. So we try to go from 1 to vertex 3, but not to 2. So the length of the current solution is 1. Then from 3 we go to 6. From 6 we go to 4. And now we see that the length of the total of the current partial solution is already greater. So 8 is greater than 7. So our current solution is not going to be extended to something which is better than something that we found so far. So there is no sense to extend the current branch further. So we just go back. So we return back to this vertex and we try to go from 3 to another vertex, namely to 4. Then when we go to 4, we discover another copy of the same cycle. So its length is 7. Then it doesn't update our variable, so we just backtrack, we go to the root and we try to visit the vertex 4. But already when we go from 1 to 4, we see that we already traversed the edge of length 10, right? The length of this partial solution is already 10. It is already worse than the solution that we found before of total length 7. So there is just no sense of extending this branch and we cut it immediately. So if we do this a little bit smarter, then we do not need to go through all possible candidate solutions. So this is the one small branch that we cut, and this is another small branch that we don't need. Okay? So in general, it can save a lot of time. In our toy example, we consider it probably the most simple lower bound for estimating the size of any extension of a partial solution. The modern TSP solvers that are able to handle graphs with thousands of vertices use smarter heuristics for lower bounding an optimal solution in a given graph. We provide 2 examples which are still simple enough and not so smart as used in state-of-the-art solvers. So the first lower bound says that in any graph, the total length of any travel and salesman cycle is at least the following expression: 1/2 times the sum of all vertices, where for each vertex we compute the sum of 2 edges of minimum distance adjacent to this vertex. Well, why is that? Well, for this, consider an optimal cycle. Note that if we just consider edges in this cycle, then the total length of this cycle just equals to this expression, where instead of 2 minimum length edges for each vertex, we use just 2 edges that are adjacent to it. Right? Just because in this expression, each edge in this sum, this edge is counted exactly twice. For example, this edge is going to be counted once for this vertex and once for this vertex. For this reason, we have 1/2 here. So if we just use, instead of 2 adjacent edges in an optimal cycle, we use 2 edges of minimum distance, of minimum length in the initial graph, this is obviously a lower bound for the length of an optimal cycle, and it already can give good results in practice. Another lower bound is that in any graph with non-negative edge weights or edge lengths, the total length of an optimal cycle is at least the length of the minimum spanning tree. Why is that? Well, this is just because if you have an optimal cycle and then you remove some edge from it, then what you get is a path in this tree, and this path is a spanning tree in this graph, right? So, but it is not the minimum spanning, probably not the minimum spanning tree. So the weight of this path is at least the weight of the minimum spanning tree, which means that the length of the cycle, or the weight of the cycle, is at least the weight of the minimum spanning tree. Well, this concludes our module, our lesson on exact algorithms. In the next lesson, we are going to consider approximate algorithms. So these are algorithms that work in polynomial time and return solutions which might not be optimal, but they are guaranteed to be close to optimal. Hello and welcome to the next and actually the last lesson in the coping with NP completeness module. In this lesson, we're going to design approximation algorithms. Such algorithms work in time polynomial in the size of the input, and what they return might not be an optimal solution, but it is guaranteed to be a solution which is close to optimal. The first problem for which we're going to design an approximation algorithm is called the vertex cover problem. The input of this problem consists of an undirected graph, and what we would like to find is a subset of its vertices of minimum total size which touches or covers every edge. To give a specific example, consider the following graph of 8 vertices. Well, for any graph, we can take all the vertices into a cover. This is clearly a vertex cover. It touches every edge. On the other hand, in this graph, we can also take the following 6 vertices. It is not difficult to see that each edge is touched by green vertices. And an optimal vertex cover in this case consists of the following 3 vertices. Again, it is not difficult to check that for each edge, at least one of its endpoints is green. For example, for this edge, it is covered with this vertex. For this edge is covered with 2 green vertices, and there are no vertices that are both not green that are connected by an edge. So the green set of vertices indeed touches every edge. The approximation algorithm for this problem that we're going to consider is surprisingly simple. Namely, it works as follows. Initially, our vertex cover is empty. So we initialize C as an empty set. Then we repeat the following while the set of edges of our graph is not empty. We select any edge denoted by UV of the current set of edges, and then we add both these vertices to the set C. Then we remove from the graph all edges that are already touched by U and V. So we remove all edges that are adjacent to U or V. So we repeat this while there is at least one edge in E, and when E is empty, we just return C. Let me illustrate this on our previous graph. So first assume that we select this red edge. Then we add its 2 vertices to a solution, and then we remove from the graph all edges adjacent to these green vertices, because they are already covered. We do not need to cover them. Then we select some other edge, for example this one, we add to its endpoints into a solution, and we remove all edges that are adjacent to these 2 newly added green vertices. So this leaves just one edge in our graph, so we select it, and we add 2 vertices into a solution, and we get the following solution consisting of 6 vertices. So just to show that it is indeed a solution, let me show you the initial edges of the graph. So we see that green vertices, the 6 green vertices, indeed cover all the edges of our initial graph. We are now going to prove that the presented algorithm is too approximate. This means that the running time of this algorithm is polynomial, and also that the solution which is found by this algorithm is at most twice as large as the optimal solution. Well, the fact that the running time of our algorithm is polynomial is clear just from its implementation. In fact, its running time is linear. So we proceed to show that it returns a solution which is at most twice as large as an optimum one. First, observe that the set of edges selected by our algorithm it forms a matching. This means that all the endpoints of edges selected by our algorithm the endpoints of all the edges are disjoint. Why is that? Well, assume that this is the first edge selected by our algorithm. So this is UV. Recall that after selecting this edge, the algorithm discards all the edges adjacent to U and V, which means that for this algorithm, neither this endpoint coincides with U or V, neither this one. This also means that any vertex cover must take at least one vertex from each of these edges, which in turn means that any vertex cover of our graph must have size at least the cardinality or the size of M, right? Note at the same time that we know the size of the vertex cover returned by our algorithm. It equals to just 2 times the size of M. This is just because the size of M is the number of edges in the set M, and each edge has 2 vertices, 2 endpoints. So this allows us to conclude that the size of the vertex cover found by our algorithm is equal to M precisely, and we know that M is at most the optimum value, the size of the optimum vertex cover. So 2M is at most 2 times opt, which justifies that what our algorithm returns is a vertex cover whose size is at most twice the size of an optimum vertex cover. Let me also show you the set of edges selected by our algorithm in the previous example. So it selected the following 3 edges, and you can see that indeed all these 3 edges form a matching. So the endpoints of these three edges are disjoint, and this also means that to cover these 3 edges we must take at least 3 different vertices. So we must take either this vertex or this vertex to cover this edge, and this will not help us to cover any of the other red edges, right? So we also must take either this vertex or this vertex, and then either this vertex or this vertex. At least in total, at least 3 vertices. Let me emphasize here the following thing. So we've somehow managed to prove that the size of the vertex cover constructed by our algorithm is at most 2 times the optimum value. At the same time, note that we do not know the optimum value. We do not know how to compute it in polynomial time. So our algorithm runs in polynomial time. So we don't know how to compute opt in polynomial time. So our algorithm doesn't compute opt. However, what it computes is, we know for sure that it is at most twice times the optimum value. So how it can possibly be that we've proved some upper bound on C in terms of opt without knowing the exact value of opt? Well, this is because we know some lower bound on opt, and it is the size of the matching that we constructed. So the size of M gives a good lower bound on opt. Moreover, the matching M can be used to construct some vertex cover. Namely, just by taking all the endpoints of these M edges, we get a vertex cover whose size is twice the size of M. So this gives us the final lower bound. So C is equal to 2 times M, which is in turn at most 2 times opt. So this allows us to prove an upper bound on C, not in terms of some quantities that we don't know, namely opt, but in terms of the size of M, which we can compute quickly and which we can use to construct a vertex cover. Let me conclude this video with a few remarks. So first of all, the bound that we've proved that our algorithm is too approximate is tight. This means that there are graphs for which our algorithm will return an answer which is exactly twice as large as an optimum vertex cover. And this can be viewed as follows. Let's just consider a full bipartite graph. Or we can just consider the following bipartite graph. Okay, assume that we have n vertices here and n vertices here. So our algorithm is going to do the following. So with each step, it will select one vertex, one edge, and add the both vertices to the solution. So in the end, it is going to return a solution of size 2n. Right? At the same time, all the edges of this graph can be covered just by one of its parts. So there is a solution of size n, but our algorithm returns a solution of size 2n. The last remark is that surprisingly, this algorithm is almost the best one that we know. In particular, we do not know how to find an approximation of this algorithm with a factor 1.99, for example. The next problem for which we are going to design an approximation algorithm is the Trevelyan-Salmonsman problem. More precisely, it is a special case called metric TSP. So the word metric means that our input is an undirected graph whose edge weights are non-negative and they satisfy the following triangle inequality. For any 3 vertices u, v, and w, the distance from u to v plus the distance from V to W is at least the distance from U to W. Okay, so for this graph, we need to find a cycle that visits each vertex exactly once and has minimum possible total length. Okay, as with the case of a vertex cover, we are going to design an algorithm which is going to return in polynomial time a cycle which might not be optimal, but it is guaranteed to be at most twice as long as the optimal cycle. So we're going to return cycle C, whose length is at most 2 times the length of optimal cycle. Again, we do not know the value of opt, but we're going to construct something which is at most 2 times opt. 2 times something, the value of which we do not know. Again, we are going to do this by providing a good lower bound. So we're going to show that opt is at least L for some value of L. And then we're going to show that C is at most 2 times L. So what is the value of L in our case? So we're going to use the minimum spanning tree as the lower bound for the optimal value of the Trevelyan-Salesman cycle in the graph. So it is stated here in the lemma, and the lemma says that for any graph, for any undirected graph with non-negative edge weights, so in this case we don't even need the graph to be metric, so for any such graph, the length of the minimum spanning tree is at most the length of the Trevelyan-Salesman problem cycle in this graph. So why is that? This is just because, once again, if we consider an optimal cycle, so we discussed this already, assume that this is an optimal cycle. So the length of this cycle is equal to TSP of G. Then let's return any edge from this cycle. Let me just erase it. Okay, so we've just removed some edge. So what is left is some path, and it is in particular a spanning tree in this graph, right? It is some spanning tree. So the minimum spanning tree has total length at most the length of this path, and this path, since all edges are non-negative, this path has length at most the length of the Trevelyan-Salesman cycle in this graph. So we get that the minimum spanning tree of G is at most the length of this path. Let me denote it probably by P, and P is at most TCP of G. We are now ready to present an approximate algorithm for the metric version of the Trevelyan-Salesman problem based on the lower bound that we've just discovered. So the first step is to construct the minimum spanning tree T of the graph G. Okay, when it is constructed, we do the following: we double every edge in T and denote the resulting graph by D. In the graph D, the degree of each vertex is even, so there is an Eulerian cycle in this graph. So we find one and denote it by C. Okay, and then finally, what we do is we remove so the cycle C visits every edge of the graph D exactly once. In particular, it visits every vertex of our initial graph, but probably not just once. So we just remove duplicates from the sequence of vertices and return the resulting cycle. In other words, we return a sequence of vertices in order of their first appearance in the cycle C. So let me show you schematically how it works, and then we will proceed to some concrete example. So assume that we have, for example, just four vertices in our graph. So the first thing to do is to construct a minimum spanning tree in this graph. Assume that it looks as follows. The second step is to double every edge. Let's do this. Now this graph is Eulerian. Namely, the degree of this vertex is 2, the degree of this vertex is 2, the degree of this vertex is 2, the degree of this vertex is 6. This means that this graph contains an Eulerian cycle, and we know already that an Eulerian cycle can be found in linear time. But in case when we have a tree whose each edge is double, this is particularly easy to find. So let me again schematically explain this to you. If we have a tree, let's consider this as a rooted tree. Assume that this was our tree. Here we have some subtrees. And then we doubled every edge in this tree. And also we doubled everything inside these subtrees. So how to construct an Eulerian cycle in this doubled tree? Well, we can do this just recursively. We start at the root. We then go we go into this subtree. Then we find an Eulerian cycle recursively in this subtree, and then we get back using this edge. Then we go to the second subtree, find an Eulerian cycle that traverses all edges inside this subtree, and then we return back using this tree. Right, and then we proceed to the third subtree, find an Eulerian cycle, and get back. For example, for our previous for this tree shown here, an Eulerian cycle will look like as follows. So let's start from this vertex. Then we first traverse this edge, then we traverse this edge, then this edge, then this one, then this one, and finally this one. So we traversed all 6 edges. This is our cycle C. Now we need to return a cycle that visits every vertex in this graph. For this we are going to do the following. Let's start in the same vertex. We first use the same edge. Then we use the second edge in our cycle C. But then the third edge in our cycle C visits the same vertex that was already visited. Instead of doing this, we go directly to vertex 4. Now from this vertex, the 5th edge of our cycle goes to the vertex which we already visited. So instead of this, we go to the initial vertex. So the metric property of our graph implies that when instead of edges 3 and 4, we used this, just the direct edge from 3 to 4, then we can only decrease the total length of the resulting cycle. Okay, we now proceed to a more concrete example. In this example, our vertices are just points on a plane, and we assume that the distance between 2 vertices is just the distance between the corresponding points on a plane. In this case, of course, the edge weights or the edge distances satisfy the triangle inequality. So in this case, we are given endpoints which define implicitly a complete graph on n vertices. So the first thing to do is to construct a minimum spanning tree in this case. It looks as follows. Now we double every edge. Now it looks as follows, and now we find an Eulerian cycle in the resulting graph. For example, we start from this vertex, and then we start traversing it like this. So this is the first edge, the second one, the third one, the fourth one, the fifth one, and so on. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and we return back to the initial vertex. Now, this algorithm visits this cycle. Visits this edge, this vertex, for example, several times, and also this vertex several times. So what we're going to do is we're going to bypass some parts of this cycle. Namely, this is the final cycle that was constructed by our algorithm. Let me show you how it was constructed. So from here we go to here, because this vertex was not visited before. From here we go to here, from here we go to here, and from here we go to this vertex. But now, instead of using the 5th edge, we go directly to this vertex, because the 5th edge visits the vertex that was already visited by our cycle. Then we go here, because this vertex have not been visited before. Then we go here, then we go here, and then again, instead of using the edge 10, 11, 12, 13, and so on, we go directly to the initial vertex. And now we visited all the edges. Okay, on the next slide we will prove that this algorithm is too approximate. We now prove that the algorithm is too approximate. So this follows from 2 or 3 simple observations. First of all, the total length of the minimum spanning tree T is at most the optimum length of a travel and salesman cycle in our graph. So we proved this already. When we doubled each edge of the tree T, we get a graph whose total weight is at most 2 opt, right? And then when we transform this Eulerian cycle in this graph into a Hamiltonian cycle, namely into a cycle that visits each vertex exactly once, we can only decrease the total weight of this cycle. And at this point, we use essentially the fact that the edge weights of our graph satisfy the triangle inequality. Namely, when we replaced, if our Eulerian cycle goes as follows, and then we go directly from one vertex to the other, then we know for sure that the length of this edge is at most the sum of the length of all these edges. Because again, the length of edges in our graph satisfy triangle inequality. Let me conclude this part with a few remarks. First of all, it is known that the same version of the travel and salesman problem, namely metric TSP, can be approximated with a factor 1.5. The corresponding algorithm is known as Christofides algorithm, and it is actually the best known approximation to date. It is also interesting to note that the general version of this problem cannot be approximated within any polynomial time computable function if p is not equal to np. In fact, if you design an algorithm that, for example, finds 10 approximation for the general version, or 10 or n squared, or even 2 to the n approximation for the general version, then it can be used to solve the Hamiltonian cycle problem in polynomial time. So if you design a good approximation algorithm for the travel and salesman problems, then you solve in polynomial time also another NP-complete problem, which is actually related, of course, to the travel and salesman problem, which is called the Hamiltonian cycle problem. So if p is not equal to np, then no good approximation for the general version is possible. We now describe a local search heuristic for the travel and salesman problem. We've already seen the main idea of the local search algorithm, but let me describe it once again. So to solve an optimization problem with a local search heuristic means the following. We usually start with some initial solution S. Then we repeat the following procedure. For a current solution S, we look into some neighborhood of this solution, and we try to find a solution in this neighborhood, a solution S prime, which is better than the current solution S. If there is some solution, such a solution S prime, then we replace S with S prime and repeat this. And we stop when S is the best one in its neighborhood. So first of all, the first thing to note is that this algorithm might return a suboptimal solution, because the only thing which we can guarantee about the return solution, it is the local optimal, not the global optimum. So namely, it is optimum in its neighborhood. But also, the quality and the running time of this algorithm depends on how we define the neighborhood, actually. For example, we might define the neighborhood of some solution as the search of all possible solutions. Then this algorithm in one iteration will need to go through all possible candidate solutions and to find the best one. So this algorithm will be actually the same as the brute force search algorithm. How do we define the neighborhood in case of the travel and salesman problem? Well, for this we first need to define a distance between two solutions. Recall that in case of travel and salesman, a candidate solution is a cycle that visits each vertex exactly once. So assume that we have two such cycles, S and S prime. We say that the distance between them is at most d if we can get S prime from S by first deleting d edges, at most d edges from S, and then adding probably some other d edges to the resulting structure. Okay? Then we can define a neighborhood again as a ball, as in case with satisfiability algorithm. Namely, we define a neighborhood of S with radius r as all the cycles that we can obtain from S by changing at most r edges. To give a specific example, consider the following graph containing of 8 vertices, and again we assume that the vertices here are just points on the plane, and the distance between any two vertices is just equal to the distance between the corresponding points on a plane. Assume that our initial solution looks as follows. It is clearly suboptimal, but just changing the two edges in this solution makes it optimal. So instead of using these two edges, we use the following two edges. This gives us an optimal solution. Sometimes, however, just changing two edges is not enough to improve a solution. For example, consider the following situation. Again, it is not difficult to see that this solution is suboptimal. In particular, it is clear that instead of visiting this vertex from this one, instead of using this path, it would be much better to use this path. However, changing just two edges, we cannot improve this. So in this case, to improve this solution, to find a better solution in its neighborhood, we need to allow changing three edges. In particular, instead of these three edges, we want to use the following three edges, right? So as we can see, there is a trade-off between the quality of the returned solution and the running time of a single iteration. Namely, when we increase the size of the ball, the size of the neighborhood, we increase our chances to find a better solution in a current ball, but we also need to go over all these solutions inside this ball, right? In any case, it is not excluded that the total number of iterations of your algorithm will be exponential in this case. Even if we use large enough R, it is not excluded that from this solution we go to that, to that, to that, to that, and so on, and we always improve it a little bit, and the total number of steps, of iterations is exponential. And at the same time, it is not excluded that the quality of the final solution will be poor. But on the other hand, this heuristic usually works well in practice, but probably with some additional tricks. For example, an obvious additional trick that it is reasonable to use is to allow your algorithm to restart. Namely, not to use just one initial solution, but to use one solution, then do some local search, and then to restart from some completely different point, and probably to select many such points, probably at random or not at random, and then return in the end the solution which is the best one that you've seen in this process. So to conclude the whole module, let me repeat the main message. When you face an NP-complete problem in practice, don't give up. There are several possibilities. First of all, it is not excluded that all the instances of your NP-complete problem are some special cases for which there exists an efficient algorithm. Also, it might be the case that you can implement an algorithm which have no theoretical upper bound on its running time, but still it works well in practice because it intelligently searches for the space of all candidate solutions. And finally, you might want to implement an algorithm which returns not an optimal solution, but something which is close to an optimal solution. For some applications, it might be good enough.
Hello, my name is Michael Kaprilov. In this lecture, I will talk about finding heavy hitters in data streams. So this lecture is about an algorithm in the so-called streaming model of computation. I will start by defining the streaming model of computation for you, and I will define the problem that we want to solve, that is the heavy hitters problem. I will talk about some of the applications, and then proceed to the actual technical content, that is design a very space-efficient algorithm for this problem. Well, the streaming model of computation is quite old by now. It was first defined in a foundational paper of Alon, Matthias, and Szegedy in the 1990s. In this model of computation, we think of the algorithm as observing a very long stream of data items. And data items could be anything. They could be IP packets, tweets, search queries, whatnot. So as the algorithm is scanning this very long stream of data items, its task is to maintain a small space summary of the stream seen so far. From this small space summary, we're supposed to be able to query some basic statistical properties of the stream. Now, formally, we think of the algorithm as having a single pass over a stream of data items. We will denote the data items by I1, I2 through IN. Capital N will be the length of the stream, and we will assume that the length of the stream is known. We typically think of a streaming algorithm as having small or sublinear storage capacity. So the space available to the algorithm is substantially smaller than the stream that it's working with, and we typically think of this as n to the alpha for some small constant alpha less than 1, or, which is the setting that we're in for this lecture, as polylogarithmic in the length of the stream. Okay, well, when I talk about storage capacity or space available to the algorithm, what exactly do I measure space or storage capacity in? Well, we could use bits, bytes, words to measure storage capacity. In some settings, we could also use points or data items. Okay, so the streaming algorithm has to have sublinear space complexity. At the same time, we also want streaming algorithms to be fast. That is, we want to have small processing time per element. It turns out that in many cases, and for many problems, it is necessary to use randomization in order to achieve sublinear space complexity. And indeed, this is the case for the problem that we're considering today. So today we will talk about the so-called heavy hitters problem. And formally, this problem is defined as follows. The algorithm is given a single pass over a sequence of data items, I1, I2, I3 through I capital N. So N is the length of the stream. After the algorithm processes the entire stream, its task is to output the k most frequent items that occur in the stream. So these k dominant most frequent items in the stream are known as k heavy hitters. Now, of course, we want our algorithm to have small space complexity. It cannot just store the entire stream and find the top heavy hitters. Specifically, in this lecture, we will design an algorithm for the heavy hitters problem with space complexity on the order of k times log n, k times the logarithm of the length of the stream. So for example, if the number of heavy hitters that we're looking for is small, say k is equal to 1, then the space complexity of our algorithm is logarithmic in the length of the stream, which is exponentially better than what the trivial solution that just stores the entire stream would have to use. Storing the entire stream, of course, takes space linear in the length of the stream. Let me give you an example for this problem. And here's a representation of the stream that I will use in the rest of the lecture. So on the slide, at the bottom of the slide, you see the data items arriving one after another in a stream. We'll associate data items with numbers between 1 and some large number n. Now, for my examples on the slides, I will use numbers between 1 and 10. So the bottom line on the slide shows the data items arriving in the stream. In the middle of the slide, you see the frequency histogram for these data items being updated on the fly. So for example, at this point, item 3 arrived twice, so we see frequency 2 in the histogram, and items 4 and 6 appeared only once. So our algorithm is observing this very long stream of data items, and at the end of the stream, needs to output the most frequent item that it has seen so far. And in this particular example, the most frequent item is item 3. It occurred 6 times in the stream, whereas all the other items occurred at most 5 times. In the next video, I will talk about some of the applications of this heavy hitters problem. And the applications will be to monitoring network traffic and estimating query statistics. So this is the problem that we would like to solve. It is the heavy hitters problem. We're given a single pass over a stream of n data items, I1, I2 through IN. We would like to design a small space algorithm that will scan the entire stream, and at the end of the stream will tell us the top k most frequent items that occurred in the stream. We also want this algorithm to have very low space complexity, and we're shooting for space complexity on the order of k log n. Okay, so this is definitely a very nice and clean mathematical problem to consider. But are there good applications of this problem? Now, it turns out that there are quite a few. So I would like to mention 2 of them in this lecture. The first one that I will talk about is to estimating network traffic. Now, for this application, think about a switch. as pictured on the slide, and think about the traffic, the IP traffic that goes through that switch. Well, this traffic can be quite conveniently visualized using the so-called traffic matrix, pictured on the slide. The rows of this matrix correspond to source IP addresses. The columns correspond to destination IP addresses. And the entry in ijth element of this matrix is exactly the number of packets that IP address I sent to IP address j that went through our switch over a period of time. Now note that the amount of traffic that goes through a typical internet switch is immense. At the same time, these switches tend to have fairly limited memory. On the other hand, it would be very useful to have statistical estimation primitives that would let us analyze the network traffic through the switch. And one particular question that we would like to ask is, well, whether or not some IP flows that go through that switch actually contribute the bulk of the traffic. The reason for this is that if a certain source IP address talks a lot to a certain destination IP address and occupies the bulk of the switch, this could be an indication of a denial of service attack or some spamming activity going through that switch. So we definitely would like to design algorithms that are able to operate using the memory available to the switch and detect such situations and find such source-destination pairs. These pairs are known as dominant or elephant flows. Let me show you an example. So the switch is observing internet traffic going through it. So basically, packets go from various sources to destinations, and every packet updates an entry of the traffic matrix. So as shown in this example, it could be that at the end of the day, the number of flows, the number of source IP destination pairs that send packets through the switch is immense. But on the other hand, a handful of these flows contribute the bulk of the traffic that goes through the switch. This is exactly the situation shown on the slide. Here, we have 6 flows, or 7 flows going through the switch, and 2 of them contribute a bulk of the traffic. One contributes 4, and the other contributes 5. Well, we would like to be able to detect such situations and find these dominant flows. On the other hand, if you think about the trivial solution to this problem, this would need a lot of space, because the trivial solution would just remember all the source IP destination pairs that ever sent a packet through our switch over a period of time, and the space is linear in the number of such pairs, which is very large. So in this lecture, we will design an algorithm for solving this problem approximately, that is, for detecting the dominant flows through a network switch, using space only logarithmic in the total number of source IP destination pairs that are sending traffic flow through our switch over this period of time. And the improvement from n to log n is exponential. This is great savings. Okay, the other application that I would like to talk about, so this one was to estimating network traffic, is to estimating query statistics in search engines. And for this application, think of our data stream as a stream of queries on a search engine, think of, say, google.com, over a period of time. So here's an example stream. 3 queries: Geneva to New York, coffee in Geneva, Geneva to New York. So it could have been me searching for flights from Geneva to New York, wanting to go to a conference, and despairing and thinking that this is a very hard process, going for a coffee and then coming back to search for flights again. So the question of finding the heavy hitters in this stream of 3 items is exactly the problem of figuring out which one occurred the most. And if we want to find the one heavy hitter here, the answer is Geneva to New York, because this query occurred twice and the other query occurred only once. Now, of course, this problem of finding heavy hitters in search logs is more interesting than the example that's shown on the slide. So if you think of solving this problem at scale, that is, think of queries on google.com over a period of time, then this becomes a very hard problem because the length of the stream is much, much longer than 3. So again, the trivial solution would amount to just storing all the distinct search queries that we see over this period of time, and the space complexity is linear in the number of such queries. Now, the solution that we will see in this lecture, known as the count sketch algorithm, has space complexity logarithmic in the length of the stream. And that's, again, an exponential improvement. Well, this is great. So I'm claiming exponential improvements from linear space to order log n, but there's big O notation on the slide. So the natural question to ask is, are the constants actually small? So are these algorithms practical? Now, in fact, it turns out that a lot of the algorithms that have been developed in the streaming literature actually are, including our algorithm in this lecture. But let me give a specific example that relates to a somewhat different problem. This is the so-called distinct elements problem. Given a stream of data items, count approximately how many distinct queries did you see. For this problem, we have a very theoretically efficient algorithm, and we also have an extremely good implementation known as hyperlog-log. To put things in perspective, this algorithm hyperlog-log can be used to estimate the number of words in Shakespeare's vocabulary using only 128 bits of memory. So the constants in big O notation are actually quite small. Okay, so as a consequence of that, a lot of the algorithms that have been developed in the streaming literature are in fact now widely used in practice for scalable data algorithms. So we definitely want to study these algorithms, and so enough motivation. So let's get to the actual problem. So in the rest of the lecture, we will design a small space algorithm for our heavy hitters problem. That is, given a single pass over n data items, I1 through In, output at the end of the day the k most frequent items that occurred in the stream using a small amount of space. So we would like to solve the heavy hitters problem in a data stream. So we want to design a small space data structure that can scan a stream of data items, I1, I2 through In, and at the end of the stream, output the k most frequent items that occurred. We also want this data structure to have a small space complexity. We want space requirements at most order k log n. Well, formally, we would like to design a small space data structure that solves the following problem. We call it find top. Find top scans an input stream S of items and has a parameter k in hand. At the end of the stream, it outputs the top k most frequent items that it saw in the stream. Well, it turns out to be useful to first design a primitive for the following related problem. We call it point query. Point query is a small space data structure, hopefully, that scans the stream S, and at the end of the stream gets a query I is a data item, and in response outputs the frequency fi, that is the number of times that I occurred in the stream. Well, for simplicity, we will assume that the data items are ordered in descending order of their frequency of occurrence in the stream. So item 1 is the most frequent item 2 is somewhat less frequent, etc., etc. What we want to design is a data structure that can solve point query, that is, scan the stream and then answer queries at the end. And we want this data structure to use small space on the order of k log n, where k is the number of items we will be ultimately looking for in the stream. Well, unfortunately, this turns out to be impossible in general. And this is because, as stated, we require this point query and find top to output exact answers. Well, imagine a stream where every data item occurs with roughly the same probability, or rather roughly the same frequency. It seems very hard to design a small space data structure to figure out which items were exactly the top k, and this can be proved formally that one essentially needs to store the entire stream. So what we definitely need is a notion of approximation if we want to get sublinear space complexity. To that effect, we define the following approximate version of the problem. We call it find approximate top. So this has two parameters, k, the number of items that we're looking for, and a precision parameter epsilon. At the end of the stream, this procedure needs to return a set of k elements such that for every data item I that we report at the end of the stream, the frequency that I occurred with in the stream is not much smaller than the frequency of the actual kth most frequent element. So fi should be at least 1 minus epsilon times fk, where fk is the number of times the kth most frequent element occurred. Now again, it turns out to be very useful to design a procedure for the following approximate version of the point query problem. So here, we want to scan the stream. At the end of the stream, if given a query I, we want to report an approximation f hat I to the number of times item I occurred in the stream. This approximation should be off by at most an additive epsilon fk term, where again fk is the number of times the kth dominant element occurred. Okay, so this looks better. At least we have a notion of approximation. Now, unfortunately, as stated, this is still a hard problem. And indeed, if we still imagine a stream where all the items occur roughly with the same frequency, maybe up to 1 plus minus epsilon, this is still a hard problem to solve. One essentially needs to store most of the stream. So in fact, in this lecture, we will design a small space primitive for both of these problems that will allow us to find these top k elements, top k most frequent elements in the stream, assuming that they actually contribute a bulk of the stream in a certain sense. And we will see the formal formulation of what this means to contribute a bulk of the stream later in this lecture. I have said that if we would like to design an approximate data structure for finding the top k elements in the data stream, it is useful to first design a data structure for approximate point query. So now let me make this statement precise and give a formal reduction. I will show that if we have a data structure for point query, then an exact data structure for find top follows. And similarly, if we have a data structure for approximate point query, an approximate find top follows as well. And I'll do this in a few steps, and I'll start with the simplest possible case. Suppose that we want to find the top one, the most frequent element in a data stream, so k is 1. Now we're assuming that we have a data structure for exact point query. We want to get a find top data structure for k equals 1. Good, so we're given a stream S as a sequence of data items, I1, I2 through In. We will maintain a data structure for point query. Besides that, we will maintain two other variables. One is the current maximum, the current most frequent element in the stream so far. The second one is its frequency. We initialize them to null and 0 initially. And then we look at every position p between 1 and n in the stream. We look at the data item that arrives in position p. We call the point query data structure to get the count of this item so far. Let's call it f. Now we check if the current maximum is the data item that we're looking at, and we simply update its count and proceed. If we're not actually storing any of the data items, which only happens at the very beginning of the stream, then we store the item IP and initialize its frequency to 1. Now, otherwise, we compare the frequency of the item that we're storing to the frequency of our current item as reported by point query. And if one is smaller than the other one, then we just swap them. Okay, so why does this work? Well, because in each position in the stream, the current maximum, the variable that we're storing, is either null or actually contains the current most frequent element so far. Good, so this was a very simple reduction. Now, does it generalize from k equals 1 to k bigger than 1? Well, yes, it does. And it works as follows. Again, we assume that we have an exact point query data structure, which is a somewhat unrealistic assumption, but it's useful for our development. Now we're given a stream of data items. We maintain the point query data structure, but now instead of just two variables, we maintain a heap H of at most k elements by count, by their count so far in the stream. Good. So for each position p between 1 and n, we look at the current data item. We ask point query to give us the frequency of this data item so far, call it f. If the heap contains our data item already, we simply update its count and continue. Otherwise, if the heap contains fewer than k elements, we just add our item to the heap with the current count. Now, if the heap actually contains exactly k elements, then we look at the minimum, the least frequent element that we're currently storing in the heap. If that element is less frequent than the one that we're holding in our hand, IP, then we evict the least frequent element from the heap and insert our current element with the count as given by point query. Okay, so why does this work? Well, it is not hard to see that the following is true. But for simplicity, let's assume that the set of top k most frequent items is actually unique. The argument is very similar without that and is left as an exercise. So in this case, for every item I in the top k, let pi denote the last position in the stream where I occurs. Well, notice that then at position pi, our element I will be inserted into the heap if it wasn't there before, and after that it will never be evicted. And so the reduction actually works. Good. So this is the reduction that we got. If we have an exact data structure, a data structure for maintaining exact point query, then we can find the top k items quite easily. Well, the question is, why is this useful? Because before we argued that exact point query is unrealistic. We need to pretty much store the entire stream. Well, it turns out that the exactly same reduction works for the approximate version of the problem. If we have a small space data structure for approximate point query, and that's something that actually exists and we'll construct it at the end of this lecture, then we can approximately find the top k elements using essentially the same pseudocode. Just whenever we look at an item IP, the current data item arriving in the stream, we ask our approximate point query to give us an estimate of the count, and use that estimate just as if it was the exact thing. Okay, so the proof of this is very similar. One can check that if we have a procedure, a data structure approximate point query, that for every element I at every point in the stream returns an estimate of I's count so far, which is off by at most fk, which is the final frequency of the kth dominant element, times epsilon, then we can get a data structure for approximate top k. Okay, so now that we have this reduction, in the rest of the lecture, we will concentrate on designing a small space data structure for solving the approximate point query problem. So we want to design a small space data structure that observes the data items in the stream, and at the end of the stream can be queried to give an approximate answer to the number of occurrences of any given data item so far. What we will have to specify are the actual parameters of our data structure. So how much space do we use? What is the quality of approximation that we provide? And what is the success probability with which we work? This will be done in the rest of the lecture. In this video, we will design a very simple and basic version of our approximate point query algorithm. So the procedure that we design in this part of the lecture will not be strong enough to solve our final problem. Nevertheless, it will serve as a building block for our final algorithm. Well, to simplify notation, in this part of the lecture and after that, we'll make the following assumption. We will assume that the elements in our data universe are ordered in descending order of their frequency in the stream. So we think of element 1 as being the most frequent in the stream, element 2 being the second most frequent, etc., etc. So the stream looks like this. Again, at the bottom of the stream, we see data items arriving in the stream one by one, and a frequency histogram is updated on the fly. So this is the stream that our algorithm is processing, and at the end of the stream, we see that the elements are ordered in descending order of their frequency. Our final goal in this lecture is to design a small space data structure that at the end of the stream will let us output the top few most frequent items that we have seen. So for example, if we were looking for the top 4 most frequent items, we would like to output these items shown in green on the screen. And we will refer to these items as the head of the stream because they contribute a bulk of the mass. The other items are shown in red, so these are the items that don't occur very frequently. We will refer to those as the tail of the stream. Okay, so our goal for now is to design a very basic estimate, a very basic version of our approximate point query primitive. This version that we design in this part of the lecture will have excellent space requirements. It will only use a constant amount of space. The problem with it will be in its precision. Nevertheless, later on, we will show how to use it as a building block for the final algorithm. Our basic estimate works like this. Well, we start by choosing a uniformly random hash function S that maps our universe of data items. And remember that we associate our data items with numbers, integers between 1 and m. Our hash function maps integers from 1 and m to -1 and +1 independently. Now the algorithm, our data structure, is very simple. It only maintains a single counter that we call C. At the beginning of the stream, we initialize the counter to 0, and then the update procedure upon receipt of a new data item I is extremely simple. We basically just increment the counter by the sign of I. So in fact, if the sign of I happens to be a plus, the counter is incremented, and if it's a minus, the counter is decremented. Now the processing of the stream now becomes very simple. For every position p in the stream between 1 and n, we run the update procedure, which simply increments the counter by the sign of the current data item I sub p. At the end of the stream, if we're asked to return an estimate for the frequency of item I, what we do is we take the counter and multiply it by the sign of I and return that as the estimate. Okay. So this is a very simple algorithm, and indeed it is somewhat hard to believe that this will have the right precision, and it will not. But it will have very interesting properties, and it will provide non-trivial precision that we will later boost into our final algorithm. Okay, so we want to analyze the precision of this estimator. This is a randomized estimator, so the first question that we need to ask is, well, how does one actually argue that a randomized estimate works? So we have a random variable, which is the counter times the sign of a fixed data item I that we want to query. We want to prove that this random variable is close to the true answer, which is the frequency of I, with high probability. Well, typically, such proofs go as follows. They proceed in 2 steps. Well, first, we look at our random variable, the counter times the sign of I, and we want to prove that in expectation, this random variable equals the true answer fi. Another way of putting this is saying that our estimator is unbiased. That is, it has the right expectation. If we're able to do this, then the next step is to show that our estimator, in fact, is close to its mean with high probability. One way to do that is to bound the variance of our estimator. If we're able to show that the variance is appropriately small, we get the result by standard concentration inequalities. Okay, so let's proceed, and we'll proceed to step 1. We would like to bound the mean of our randomized estimator. Now, before we take any expectations with respect to our sign function, I want to look at our estimator, which is the counter times the sign of I. I want to write it in a somewhat more convenient way. Okay, well, by definition, the counter times the sign of I can be written as the summation over all positions in the stream, from 1 to n, of the sign of the item that arrives in position p times the sign of I. Well, we can equivalently write this as a summation over all data items j in existence of the frequency of data item j in the stream times the sign of data item j times the sign of I. Well, since we're estimating fi, it is convenient to extract from this summation the contribution of item I itself. So we get the frequency of I times the sign of I squared, which is nothing but 1, plus some contribution from the other data items, namely a summation over j in m minus I, data items j other than I, the frequency with which j occurred, times the product of signs, sj times si. Okay, and this is already looking great, because what we see is that our estimator can be written as the true answer plus some contribution from the other elements in the universe that hopefully we can say looks like noise. And indeed it does, as we will see in the rest of this lecture. Good. So our first step should be to show that the expectation of this other contribution that we hope to say is noise is 0. So let's just take expectations of both sides of this equality. I want to take the expectation of the counter times si with respect to the sign function. Of course, the expectation of fi is fi. Fi is a deterministic quantity. Now here we can take the expectation inside the sum, And now because the sign of j and the sign of I are independent random variables when j is distinct from I, we get the product of the expectation of the sign of j and the expectation of the sign of I. But both of these quantities have mean 0. Each data item was mapped to -1 and +1 with equal probability. So indeed, the contribution of this noise-like term in expectation is 0. This means that the mean of our randomized estimate is exactly correct. The mean is fi. So this is great. So our next step, and this is what we will do in the next video, is to estimate the variance of our estimator and show that it's small. This will show us that the estimator is actually close to the true answer fi with high probability. Well, now that we have been able to show that the expectation of our randomized estimate for fi is exactly fi, we would like to bound the variance and show that our randomized estimate for fi actually is close to fi with high probability. So one way to show this is to use Chebyshev's inequality, which is a quantitative version of the law of large numbers. Chebyshev's inequality says the following, that if we have a random variable x with mean mu and variance sigma squared, then the probability that this random variable deviates from its mean by more than a factor t times its standard deviation sigma is at most 1 over t squared. So our plan is as follows. We would like to apply Chebyshev's inequality to our randomized estimator. So we want to let x, the random variable, equal the counter times the sign of I, where I is a fixed data item. And to do that, we need to bound the variance, because we know that the mean is fi already. So let's bound the variance. For that, we want to recall the expressions that we have for our estimator. We know that the counter times si can be written as fi plus the contribution from the other data items j distinct from I. Fj times its sign times the sign of I. We also know that the expectation of the counter times si is exactly fi, so what we want to bound is the variance of our estimator, which is nothing but the expectation of the sum over j different from I, that is contribution from other elements in the universe, of their frequency times their sign times the sign of I, the entire quantity squared. Now it turns out that this is not too hard to compute, which we will now do. Before we apply the expectation, I want to design a somewhat simpler form that will be easy to apply the expectation to. So the counter times si minus fi, the entire thing squared, can be written as a summation over j, different from I, j prime, different from I, of the product of the frequencies, fj and fj prime, times the product of signs times the sign of I squared. Now, of course, the sign of I squared is nothing but 1, so what we get is a double summation over a pair of items j and j prime that are distinct from I, of the product of their frequencies and the product of their signs. So now if we take the expectation of this quantity, we'll see that the following happens. If we look at a term in this double summation that corresponds to j different from j prime, then the expectation of the product of the signs is exactly 0, by the same token as in our mean analysis. So what we get is that all terms with j distinct from j prime are 0 in expectation. And so the variance is exactly the summation over all other data items in the universe, other than I, of their frequency squared. Okay, so we have been able to construct a randomized estimate for the frequency of any fixed item I, and we have been able to bound its variance. So we would like to now conclude that by Chebyshev's inequality, our estimate is good, meaning that our estimate is close to its mean, the frequency of I, with high probability. But in order to do that, we need to check that the square root of the summation over other data items j of their frequency squared is actually small compared to the frequency of our item I. Now, this is not generally true. This depends on the actual stream and on the actual item that we're trying to estimate. So let's look at some examples, because these examples will show when our estimate works well and when it does not. This will inform us in using our basic estimate that we just constructed as a building block for the full algorithm in the rest of the lecture. Okay, so this is our expression for the variance. And again, think of item I as fixed. This is the item that we're trying to estimate. Now, suppose for a second that our stream of data items has the following frequency histogram shown on the slide. In this histogram, item number 1, which is the most frequent item in the stream, dominates the stream. Well, if that is the case, and if we're trying to estimate item 1, then our estimate should work fairly well. Indeed, our estimate works well exactly when the frequency of item I is larger than roughly the square root of the sum of squares of other frequencies. On the other hand, if this is our stream, and instead of estimating item 1, we're trying to estimate our item 6, our estimate is quite poor, because the error in estimating item 6 will include a contribution from item 1, and that item dominates the stream, so that is a problem. So to summarize, this very simple basic estimate that we constructed works really well if we're trying to estimate elements that dominate the stream, and works quite poorly when we're trying to estimate elements that don't, especially in the presence of very large elements in the stream. Okay, and so now our final algorithm, our full version of approximate point query, and the final count sketch algorithm will fix these deficiencies of our basic estimate. The way our algorithm works is as follows. In order to find the top k elements approximately, what we will do is this. Well, first, given our data stream, we will hash the data items in our universe into k buckets. Now, this can be viewed as the process of constructing substreams. Now, we will run our basic estimate that we just designed on every substream that is obtained via this hashing process. Now, finally, to boost the confidence of our estimates, we will repeat this procedure a logarithmic number of times. And this will be our algorithm. The main intuition for why this works is exactly this. This hashing process will allow us to ensure that when we're estimating a large item, then most of the substreams that we estimated from will look like the one on the top of the slide. We'll show that our count sketch algorithm will be estimating the large items mostly from substreams that are dominated by these large items. Now, if we want to estimate a small item, we should also be able to figure out that this item has a small frequency. The algorithm, as we will show, actually estimates the small items mostly from streams that look like this, that don't have any of the large items contaminating the estimate. And in the next part of the lecture, we will see the details of the algorithm and some of the main ideas behind the analysis. In the rest of the lecture, we will put together the ideas that we developed for our basic version of the approximate point query data structure to get a full-fledged approximate point query, and finally the count sketch algorithm that gets good results, good approximations to frequency counts with high probability and small space. I will start by providing the intuition for the improvements that we have to make to the original version of approximate point query. Then I will define the algorithm itself, and finally give some intuition for the analysis and the parameters. Okay, well, recall that our basic version of approximate point query suffered from two issues. Well, first, the precision of our estimates depended on the variance of a certain estimator, and that variance sometimes was bad. For example, when several dominant coefficients were present in the same stream. To fix this deficiency, what we do for our final algorithm is run our basic estimator that we already designed on subsampled or hashed version of the stream of data items that we get as input. The reason why this works is that this operation, as we will show later, reduces variance of our estimates. Now, the second problem with our basic version of approximate point query was that the success probability was fairly low. It would only succeed with high constant probability. On the other hand, our final algorithm has to provide good estimates for all data items that appear in the stream simultaneously. So to fix this deficiency and make the algorithm run with high probability, we introduced the idea of repeating our estimates independently many times and taking medians of answers that they report to boost our confidence. Okay, So the main idea of this algorithm, and the first idea that makes this work, is the idea of hashing the input stream into a number of buckets. So again, here's our data items. We associate them with integers between 1 and some large number. For our examples, we use 1 through 10. What we do is we choose a hash function that maps the data items to a number of buckets. So in this particular case, on the slide, you see a random mapping of data items 1 through 10 into 8 hash buckets. So B is the number of hash buckets, is equal to 8. The mapping is shown as the arrows. So for example, element number 1 is mapped into bucket 3. And element number 1 also happens to collide with element number 6 in bucket 3. Element 10, on the other hand, is residing alone in bucket 2. It doesn't collide with any other element. Good. Now this idea of hashing lets us define the notion of hashed streams. In particular, for every item I, we will say that the hashed stream of item I contains all the other elements that collide with I under hash function h. To give an example, the subsampled or hashed stream of item 1 under this particular hash function shown on the slide consists of 2 items, item 1 itself and item 6, because they collided in bucket 3. The subsampled or hashed stream of item 5 consists of 2 items, 5 and 7, because 5 and 7 collided in bucket 5. Now, it is important to note that we are hashing the universe of data items into a number of buckets and not positions in the stream. Let me give a specific example. So this is the stream that we started with at the beginning of this lecture. So it contains occurrences of items from 1 to 10, and here's the frequency histogram. Under the hash function from the previous slide, the subsample stream of item 1, which is the heavy hitter, one of the dominant items, the most frequent item in the stream, is shown at the bottom of the slide. It consists of all the occurrences of 1 in the original stream and all the occurrences of 6. The frequency histogram for the stream is shown at the bottom of the slide. A crucial observation is that this frequency histogram looks exactly like the good case for our basic estimator from the previous part of the lecture. Indeed, if we were to estimate the value, the frequency of item 1 from this particular stream, then the error would only be contributed by the item number 6, which means that we would actually get a good estimate because item number 1 dominates the subsampled or hashed stream. Okay, but item number 1 was a heavy hitter. It was the most frequent item in the stream. Let's see what happens for other items. So for example, if we look at the subsampled or hashed stream of item number 5, well, that consists of 2 items, 5 and 7. Just all occurrences of these items. So 5 occurs twice and 7 occurs once. The frequency histogram, again, is shown at the bottom of the slide. So note that if we were to estimate item number 5 from this particular stream, we would actually get a very good estimate, because this estimate would not be contaminated by occurrences of any of the heavy hitters in the original stream. And this is the basic idea for why our new version of the algorithm will actually work well. Well, we're now in a position to state the final algorithm for approximate point query and hence the count sketch algorithm. The algorithm proceeds by first choosing 2 parameters. We choose a parameter t, which is the number of repetitions of a hashing scheme that we'll perform to boost the confidence of our estimates, and one should think of t as logarithmic in the length of the stream. We will set these parameters later in this lecture. The other parameter is b, which is the number of buckets that we will hash our universe of data items into. And b should be thought of as a large constant times k, the number of heavy hitters that we would like to approximately find. So the algorithm starts by selecting t uniformly random hash functions that map our universe of data items into b buckets, and also t uniformly random sign functions that associate uniformly random signs with every data element in our universe. Now this can be conveniently visualized as an array C shown on the slide. This array contains t rows corresponding to the t independent repetitions. We will index the rows by a parameter r, little r, and b columns. Every column corresponds to a hash bucket. Now the pseudocode for the algorithm is as follows. the algorithm will maintain this array C of numbers, of counters, and every cell in the array C will correspond to an invocation of the basic approximate point query primitive that we just designed. Specifically, the update process looks like this. Given a data item I, we run over all the rows R from 1 to T, and for each row R, we use the rth hash function to figure out the column that our element I has to contribute to. And we increment the corresponding counter, that is the cell in rth row and h of ith column, by the sign that the rth sign function assigns to our element I. Now, the pseudocode is given on the slide, and it should be noted that this simply amounts to running for each row R our simple approximate point query primitive that we just designed on the stream of data items that hashed into the same bucket as I itself. Okay, so this is the update process. Now, the estimation process works as follows. At the end of the stream, if we're given an item I whose frequency we want to approximate, what we do is we run over all the R rows in our hash table, and for each row, we take the product of the counter in row R and the column that I hashed to with the sign of R under the rth sign function, which is exactly the estimator that we designed for our basic approximate point query primitive, except that now we have R independent copies of these approximate primitives, and we take the median of the answers that they output as the final result. So for example, the data item 5 hashes into 3 distinct buckets in every of the 3 rows of the array C shown on the slide, so it will contribute to these 3 buckets when we perform the update process, and then the answer will be computed as a median of the 3 values found in these buckets multiplied by its sign. Okay, well, this is the algorithm. Now the question is, why does this algorithm provide precise estimates for every single data item in the stream with high probability? Well, the first observation here is that by our previous analysis of the basic estimation primitive, basic version of approximate point query a few slides back, the mean of every of these T estimators that we use, that we take the median of in our new version, is exactly correct. The mean of every of these estimators for every R between 1 and T is exactly the frequency of the ith item. Okay, well, this is reassuring, but as of now, this doesn't mean that our algorithm is any better than the basic primitive that we designed before. The distinguishing factor comes in the variance of our estimate. Recall that the variance of the basic primitive that we designed before was equal to the summation over all data items j that were different from I, of the frequency of the jth item squared. Now, it is possible to show that the variance of our new estimator is the summation only over those data items j different from I that hash to the same bucket as I of their frequency squared. Now, our hash functions map the data items to B buckets, so we should expect the variance to be a factor of 1 over B smaller than before. And indeed, it is possible to prove that this is the case. Now, what this means is that if we choose the number of buckets that we hash into to be sufficiently large, we can drive the standard deviation of every of those T estimates to below our precision parameter epsilon times the frequency of the kth most frequent item, fk. Now, this is exactly the additive precision of our estimates that we're shooting for our approximate point query primitive. So choosing the number of buckets large enough fixes the precision issue. Now, we also have to ensure that our estimates work with high probability for all data items, and this is what we fix by taking medians of a logarithmic number of independent estimates. Okay, so the formal statement about the precision and success probability of our scheme is given by the following lemma. This lemma says that if we choose the number of buckets to hash into to be at least the following quantity, which is the maximum of 2 numbers. Well, first, the number of buckets has to be bigger than a large constant times k, which is the number of heavy hitters that we're shooting for approximating. At the same time, it also should be larger than a large constant times the following ratio. This is the ratio of the L2 squared norm of the frequencies of the tail of the stream divided by epsilon squared times the frequency of the kth largest element squared. Okay, so if the number of buckets B is chosen to be sufficiently large in the following way, and if we choose the number of repetitions of our hashing scheme to be logarithmic in the length of the stream, then we have that our median estimator is at most epsilon times fk far from the true answer for every data point I and from every position in the stream. Okay, now this is exactly the additive precision that we wanted to get, and it remains to understand what our sample complexity is. Now recall that the algorithm stores this array C, which has t rows and b columns. Now the parameter t was chosen to be logarithmic in n, and the parameter b, however, depends in non-trivial ways on the actual structure of the stream. So now the question is, how large is b? Is it possible to show that for every stream, b is on the order of k over epsilon squared, for example? This would be very nice. Now, unfortunately, this is not true. Indeed, imagine a stream where every item appears exactly once. Then all of the fj's are exactly 1, and we get that we need to set b to be omega of n over epsilon squared. Okay, now this is really terrible because in space order n, we could have stored the entire stream anyway and solved the problem exactly. However, note that in the important case where the stream is actually dominated by the top k elements, b turns out to be very small. Specifically, suppose that if we sum the frequencies squared over all the elements j in the tail of the signal, or rather of the stream, and divide this by k, so think of summing the squared frequencies over the tail of the stream and then spreading this equally among the top k elements, the heavy hitters, then if this turns out to be on the order of the frequency squared of the kth largest element, then hashing into b on the order of k over epsilon squared buckets turns out to be sufficient to find the heavy hitters. And this is exactly the sense in which we said that we're going to solve the problem for streams where heavy hitters dominate the stream in a certain sense. And the actual formal sense is the L2 sense shown on the slide. Now, of course, in practice, we don't know what the stream looks like, so we cannot choose B according to this formula. What we can do, though, is choose B as large as possible, subject to space constraints, because hashing into more buckets only improves the precision guarantees of our algorithm. Okay, so now I would like to spend a little bit more time talking about the number of buckets that we have to hash into, and showing that actually this number is surprisingly small for some very interesting cases. And for simplicity, let's think of k equal to 1. That is, we have a stream, and we want to find the most frequent element in the stream. Now suppose further that this most frequent element, and by our assumption it's element 1, appears square root n times in the stream, and all the other elements appear exactly once. So there are n minus root n elements in the tail of the stream. Okay, so now this means that f1 is equal to square root n, and for every I between 2 and n minus root n, fi equals exactly 1. So all the other elements appear once. Now the lemma shows that if we set b to be the following quantity, the sum of frequency squared over the tail of the signal divided by epsilon squared fk squared, then we're able to find our heavy hitter. Now all the fj's in the tail of the signal are 1, so the summation of their squares is bounded by n. On the other hand, f1 is equal to root n, so f1 squared is n as well. Now what this means is that setting b to be a constant divided by epsilon squared suffices to find our heavy hitter, the most frequent element in the stream. And I would like to stress that this is a very remarkable result, because if we think about this, the element 1, that is the heavy hitter, appears only in square root n positions in the stream. So that's a vanishingly small number of positions. So if we were to sample a constant number of locations, we would never see this element. This means that the algorithm that we have just constructed is quite powerful. Okay, well, to summarize, we started this lecture with the goal of designing a small space data structure that can scan a stream of data items arriving one after another, maintain a small amount of space, and at the end of the stream, output an approximation to the top k most frequent coefficients seen in the stream. We showed that this problem can be reduced to the problem of designing a different data structure, which we called approximate point query. This data structure, again, uses a very small amount of space, scans the stream of data items one after another, and at any point, this data structure can be stopped and asked to return a good approximation to the number of times any given data item has been seen so far. Now, we gave a very powerful primitive for the approximate point query data structure that gives very precise estimates with high probability for all data items. Now, this primitive also uses a small amount of space on the order of k log n, assuming that the top k elements actually dominate the stream in a certain L2 sense. Now, putting these two pieces together gives us the count sketch algorithm. In this part of the lecture, we will prove our main lemma on the precision guarantees of the final version of our approximate point query primitive. Now, this lemma is shown on the slide. It says that if the number of hash buckets that we hash into is chosen to be sufficiently large, and if the number of repetitions is logarithmic in the length of the stream, then our approximate point query primitive gives an approximation to the frequency count of every data item in the universe at every position in the stream that is correct up to an additive epsilon times fk term, where fk is the frequency of the kth most frequent item in the stream. Okay, well, the failure probability in this statement will be inverse polynomial in the length of the stream. Now, because of that, instead of proving the lemma for every point p between 1 and n in the stream, it in fact suffices to prove it for the last position in the stream, because after that, we can apply the lemma to every prefix of the original stream and get the lemma from the previous slide. Okay, so this is the statement that we would like to prove. Well, let us start by observing that in fact, for every row I of our array C, that is for every of the t hash functions, hr, that we chose, by the basic analysis of our basic version of the approximate point query primitive, we have that every single one of the estimators that we're taking the median of has the right mean. That is, for our data item I, which we consider fixed from now on, for every r between 1 and t, the expectation of the rth estimator is exactly the frequency of the ith item. Now, this is very good, it is reassuring, but doesn't tell us that this estimator is actually better than the basic version of the estimator that we had before. And the distinguishing feature of our new estimator comes in reduced variance. Specifically, by the analysis of our basic estimator applied to every single one of the little t estimators that we're taking the median of, we have that for every I and for every fixed r from 1 to t, the variance of our rth estimator for the frequency fi is equal to the following quantity. It is the summation over all other data items j, different from I, that hashed into the same bucket under the rth hash function of the frequency fj squared. Now note that the summation goes only over those j's in the data universe that hash to the same bucket as I. Now, okay, so our hash functions were hashing the data universe into b buckets. So we should expect the right-hand side to be about a factor of 1 over b smaller in expectation than in our basic analysis. And this is where our gains will come from. Okay, so we would like to show that the variance is small, and we would like to show that it at least reduces by roughly a factor of b. In fact, we'll be able to do a bit better than that. Now, specifically, we consider the variance of our estimator, and we separately consider the contribution of the head elements of the stream to this variance, and the contribution of the tail elements. So we write the sum over all data items j different from I that hashed under the same bucket under the rth hashing, and we think of r as fixed from now on. We write the summation as two separate summations. The first one is a summation over data items j in the head of the stream, think of the heavy hitters, that are different from I and again hash into the same buckets, of fj squared. So recall that the head of the stream is exactly the top k most frequent elements in the stream. The second term is the summation over the tail of the stream, so the less frequent elements that occur in the stream, of fj squared, and this is again only over those j that hash to the same bucket as I under the rth hash function. Now our plan is as follows. We would like to bound these two terms. What we will do is for each fixed I and for each data item I, we consider both fixed from now on, we will define the following three events. The first event is an event that we will call no collisions of R and I. This event occurs if and only if our data item I does not collide with any of the top k most frequent elements in the stream, that is the head of the stream, under hashing R. The second event is a small variance event. Again, it is indexed by the hash function index R and I itself. This event happens if and only if I does not collide with too many of the tail items under hashing R. So note that the first event, if it occurs, implies that the first summation above is just 0. There are no other events in the head that I collides with. And the second event would ensure that essentially the second summation is fairly small. After that, we'll also need a third event, which we denote small deviation of R and I, and this is essentially the success event from our basic analysis from the outcome of Chebyshev's inequality. What we will show in the next few minutes is that, in fact, for every R and every data item I, all three of these events on the slide hold simultaneously with probability strictly better than 1/2. And after that, we will later show that this implies that if we take a logarithmic number of independent trials, the median estimate will give us a good estimate with high probability. So we need to define the no collisions, the small variance, and the small deviation events. Let's start with no collisions. And we think of I and R as fixed. We'll let the no collisions of R and I event denote the event that under hash function HR, none of the head elements j, distinct from I, collide with I or are hashed to the same bucket. Now note that this definition makes sense for any data item I, whether or not it belongs to the head or the tail of the stream. Okay, well, why does this event hold with rather high probability? Well, recall that our hash function was chosen uniformly at random. So for any two distinct elements, I and j, the probability that they collide under the hash function is at most 1 over the number of buckets that we hash into. And in fact, it's equal to 1 over the number of buckets, but we only need inequality in this case. Good. Well, by the assumption of the lemma, the number of buckets was chosen to be at least a large constant times k, the number of heavy hitters. So now by union bound over all j in the head of the stream, we have that the no collisions event occurs with probability at least 1 minus k over b, which is at least 7/8 by our assumption. Great. So let me remind you that we wrote the variance of our estimator as the contribution from the head of the stream and the contribution from the tail. And conditioned on the no collisions event that we just defined, the first contribution is exactly 0 because the summation is over the empty set. So we now need to handle the second sum. To that effect, we define the small variance event. Formally, we say that the small variance of R and I event occurs if the following condition is true. If the summation over elements j in the tail of the signal that are distinct from I and also hash into the same bucket as I under the rth hash function of their frequency squared is at most 8 over b, the number of our hash buckets, times the summation over all j in the tail of the frequency of j squared. Well, why does this event hold with high probability? Well, again, recall that our hash function is uniformly random. So for every pair I and j that are distinct, the probability that I and j collide is at most 1 over b. What this means is that we can take the expectation of the left-hand side of this equation, and we can write it as follows. The expectation of the left-hand side can be written as the summation over all j in the tail of the signal, distinct from I, of fj squared, times the probability of j and I colliding. And that is at most 1 over b of the entire sum. Okay, so now, but this is only the expectation of the left-hand side. Why is the left-hand side actually with rather high probability at most 8 times higher than its expectation? Now that's by Markov's inequality. Markov's inequality says that for every non-negative random variable x with mean mu, the probability that x shoots over its mean by a factor of k is at most 1 over k. So now what we do is simply apply Markov's inequality to the left-hand side of our expression with k equal to 8. Good. So we just proved that the expectation of the left-hand side of our inequality is at most 1 over b times the summation over all j in the tail of the signal, their frequency squared. By Markov's inequality, the probability that the small variance event occurs is at least 1 minus 1 over 8. That is at least 7/8. Okay, so we wrote the variance of our estimator as the contribution from the head of the stream and the contribution from the tail of the stream. Then we defined 2 events, the no collisions event and the small variance event, such that conditioned on both of these events, the first contribution is just 0, because the summation is over an empty set, and the second contribution is at most 8 over b times the sum over all data items j in the tail of the stream of their frequency squared. At this point, we need the very last piece, the small deviation event. The small deviation event occurs by definition if the squared deviation of our estimator from its mean is at most 8 times its variance. Now, by Chebyshev's inequality, this happens with probability at least 7/8. Okay, well, at this point, we actually already have a basic version of our lemma, from which the full version will follow by standard concentration inequalities. Now, to state this basic version of the lemma, it is convenient to introduce a parameter gamma, defined at the top of the slide. We let gamma be the square root of 1 over b of the sum of frequencies squared over frequencies in the tail of the stream. Now that we have proved that the 3 events that we defined occur simultaneously with probability 5 over 8 at least, we actually have the following claim, stated as the lemma on the slide. If the number of buckets b that we hash into is at least 8 times k, then for every data item I and for every r between 1 and t, the probability that rth estimate for the frequency fi is 8 gamma close to the true answer is at least 5 over 8. And this can be verified by substituting gamma into our expressions. Okay, so this is very good. There are 2 things that we need to understand. Well, first, the success probability is only 5 over 8 for a fixed data item I and for a fixed r, whereas we need our estimate to work with high probability for all data items I. We need to fix that, and then we need to relate the precision guaranteed by this lemma to the precision that we want to achieve. That is additive epsilon times fk error term. So let's fix the success probability first. And I'm claiming that using standard concentration inequalities, that is Chernoff bounds, and I will not get into the details here, one can show, starting from the lemma on the previous slide, that if we take a sufficiently large logarithmic number of independent copies of our estimator, then the following will be true. For every data item I, with all but, say, 1 over n to the 4 probability, the median of our estimators will be 8 gamma close to the true answer. Now this follows by standard concentration inequalities, Chernoff bounds, but I will not give the formal proof here. Okay, well this is very good, because we have just been able to show that our estimator succeeds, that is, gives an answer that is 8 gamma close to the truth, for every fixed data item I with probability at least 1 minus 1 over n to the 4. So now we can take a union bound over all data items in the universe, of which there are at most n, those that appear in the stream, and conclude that in fact our estimator is correct for all data items simultaneously, with probability at least 1 minus 1 over n cubed. So we know that for all data items now, with high probability, the estimator is 8 gamma close. To get a proof of our final lemma, all we need to understand is how does this 8 gamma relate to the additive error term of epsilon times fk, the frequency of the kth largest element that we wanted to achieve. And this can be verified by direct substitution. Recall that the number of buckets b was chosen to be appropriately large, where large depends on the actual statistics of the stream. This was the assumption of our lemma. One can verify by direct substitution into the expression for gamma that 8 gamma turns out to be less than epsilon times fk. And this concludes the proof of the lemma.